Hello everyone, welcome to Simplilearn's YouTube channel. If you are here to learn the data science algorithms, then you are at the right place. This data science algorithms video will cover the most important algorithms that would help you in real life scenarios. Also, if you are a tech geek in a continuous hunt for latest technological trends, then consider getting subscribed to our YouTube channel. We have daily updates on multiple technologies. And don't forget to hit that bell icon so that you can never miss an update from us. So without further ado, let's dive into the agenda for today's discussion. So we will be learning the data science algorithms today by going through the following docket. At first, we will learn the logistic regression in R. Then we will move ahead and know what is a decision tree. Followed by that, we will understand what is clustering. Next, we will learn divisive clustering. Later, the support vector machine. Advancing ahead, we will have the k-means clustering. And lastly, we will wind up the session by learning time series analysis. I hope I made myself clear with the agenda. Now, escalating over to our training experts.
Hello and welcome to Logistic Regression in R. My name is Pete Ferrari and I am with the Simplilearn team, and today we're going to cover logistic regression in the R programming language. Logistic regression is kind of a misnomer in that when most people think of regression, they think of linear regression, which is a machine learning algorithm for continuous variables. However, logistic regression is a classification algorithm, not a continuous variable prediction algorithm. Logistic regression is also sometimes called logic regression. In this video, we are going to learn why we would use regression as a predictive algorithm, what is regression, the different types of regression. As I've already mentioned, some regression algorithms are classification algorithms and some are continuous variable algorithms. Why use logistic regression? What is logistic regression? And then we'll look at a use case, a college admission using logistic regression. So why would we use regression? Well, let's say we had a website and our revenue was based on the traffic that we could drive to that website, whether through R&D or marketing, and we wanted to predict the revenue based on site traffic. And the website traffic would be related to the revenue we could generate. The more traffic driven to our website, then the higher our revenue, or at least that's what we would intuitively assume. And so we need to predict the revenue based on our website traffic. Here we have the plot of revenue versus website traffic. Traffic would be considered the independent variable and revenue would be the dependent variable. Often the independent variable or variables, if we had more than one, could be called the explanatory variables, and the dependent variable would be called the response variable. However, we typically refer to them as independent and dependent variables. So our intuition tells us that the independent variable drives the dependent variable, and if there is some relationship between the two variables, then we would say that there is a correlation between the two variables. And then we may be able to use the independent variable to make predictions about the dependent variable. If you look at the chart on the right, you'll see there is a clear trend between website traffic and revenue. As website traffic increases, the revenue increases, and we could draw a line to show that relationship. And then we could use that line as a predictor line. So for example, what will revenue be if our traffic is 4.5K? And we see that when the traffic is around 4,500, the revenue is around 13,000. And if we could draw a perpendicular line from 4.5K on the axis, on the x-axis, the traffic axis, up to the orange regression line, sometimes called the line of best fit, then we could draw another line over to the y-axis, the revenue axis, and we could see where it lands, and that would be the prediction. So in this example, when the traffic is around 45,000 hits, the predicted revenue is around 13,000. Normally, we wouldn't actually draw those lines. We would generate an equation, and we would call that equation a model, and we could plug the independent variable into the equation to generate the dependent variable output, which we would call our prediction. So what is regression? Regression is a statistical relationship between two or more variables where a change in the independent variable is associated with a change in the dependent variable. It's important to note that not all variables are related to each other. For example, a person's favorite color may not be related to revenue from a website. Here, the change in one variable, height, is closely associated with the change in the other variable, age. This makes intuitive sense. As you get older, from when you're born, you get taller. And it seems to make sense if we plot that data, we would see those green points on the graph, up to some certain age where growth would taper off. In the plot in the middle of the screen, we see the clear linear relationship between age and height, which is indicated by the solid red line. We sometimes call that line a trend line or a regression line, or the line of best fit. And we see that the height is the dependent variable and age is the independent variable. Of course, you might ask, doesn't height depend on other factors? Of course it does. But here we're looking at the relationship between two variables, one independent and one dependent, age and height. There are various types of regression: linear regression, logistic regression, multiple linear regression, polynomial regression, and there are others: decision tree regression, random forest regression. But linear regression is probably the most well known. And by definition, when there is a linear relationship between a dependent variable, which is continuous, and an independent variable, which is continuous or discrete, we would use linear regression. When the y value in the graph is categorical, such as yes or no, true or false, they voted, they did not vote, they purchased something, they did not purchase something, it depends on the x variable. Logistic regression is when the y value in the graph is categorical in nature. For example, yes, no, purchased, don't purchase, voted, did not vote, and it depends on the x variable. Notice the trend line for linear regression and the line for logistic regression. They're different. More on that later. And there's polynomial regression as well, when the relation between the dependent variable y and the independent variable x is in the nth degree of x. Sometimes we say an nth degree polynomial of x. In this picture, you can see that the relationship is not linear. There's a curve to that best fit trend line. So why would we use logistic regression? And we need to understand why we would use logistic regression and not linear regression. Picking the machine learning algorithm for your problem is no small task, and it really behooves us to understand the difference between these machine learning algorithms. Linear regression answers the question, how much? So in our earlier example, if website traffic grows, then how much would revenue grow? Whereas logistic regression would answer what will happen or not happen. Linear regression, in general, is used to predict a continuous variable, like height and weight. Logistic regression is used when a response variable only has two outcomes, yes or no, true or false. Often we refer to logistic regression as a binary classifier, since there are only two outcomes. So let's try to understand this with an example. Let's say we have a startup company and we are trying to figure out whether the startup will be profitable or not. That's binary with two possible outcomes, profitable or not profitable. And let's use initial funding to be the independent variable. Here we have a graph that shows funding versus profit, and it appears linear. Once again, our intuition tells us that the more funding a startup has, the more profitable it will be. But of course, data science doesn't depend on intuition, it depends on data. But this graph does not tell whether the startup will be profitable, yes or no. It only states that with an increase in funding, the profit also increases. That's not binary. If we wanted to predict how much profit, then linear regression would be useful. But that's not what we are being asked. Hence, we need to make use of logistic regression, which has two outcomes, in our case, profitable and not profitable. So let's draw a graph again. The x-axis will be our independent variable, funding, and the y-axis will no longer be the dependent variable, profit, but it will be the probability of profit. For example, if you look at a company with a funding of, say, 40, then the probability that that company will be profitable is around 0.8 or 80% based on the best fit line called a sigmoid curve. In the example, we plotted several companies, some with 10, 15, 20, some with 50, 60, or 70, or 65, and we indicated whether they were 0, not profitable, or a 1, profitable, on the graph, and this is how we should think of logistic regression. In this example, given the amount of funding, we calculate the probability that a company will be profitable or not profitable, and if we use the threshold line of 50%, then we have our classifier. If the probability is 50% or higher, the company is profitable. If the probability is lower than 50%, it's not profitable. So what is logistic regression? This is a linear regression graph. So let's compare linear regression to logistic regression and take a look at the trend line that describes the model. It's a straight line, which is why we call it linear regression. But using linear regression, we can't really divide the output into two distinct categories, yes or no. To divide our results into two categories, we would have to clip the line between 0 and 1. If you recall, probabilities can only be between 0 and 1, and if we're going to use probability on the y-axis, then we can't have anything that is below 0 or above 1. Thus, we would have to clip the line. And once we clip the line, we see that the resulting curve cannot be represented in a linear equation. So for logistic regression, we will make use of a sigmoid function, and the sigmoid curve is the line of best fit. Notice that it's not linear, but it does satisfy our requirement of using a single line that does not need to be clipped. For linear regression, we would use an equation of a straight line. Y equals b sub 0 plus b sub 1 times x being the independent variable, y being the dependent variable. But as we've said, we cannot use a linear equation for binary predictions, so we need to use the sigmoid function, which is represented by the equation p equals 1 divided by the quantity 1 plus e to the minus y, e being the base of the natural logs. Then taking the log of both sides and solving, we get our sigmoid function. And graphing it, we get our logistic regression line of best fit. The applications for logistic regression are endless. Here, we might have a couple of gardeners or farmers, and one farmer says, I am planning to grow plants in my backyard, and I want to know whether my trees will get infested with bugs, which I'm sure is a huge problem. And these days, the fewer pesticides we use, the better off we are for health reasons. The young lady says, I can use logistic regression in a model to predict it for you. And the other farmer says, well, how is logistic regression going to help? But we know that healthy versus not healthy is a binary classification, and we can use a binary classifier like logistic regression to solve this problem, which is what the young lady has in mind. If we have the data, we can model the data and generate a sigmoid function that best fits our data, and then use the probability of a healthy tree versus a not healthy tree or an infested tree. Once again, we see our sigmoid line of best fit and some points that represent healthy trees and not healthy trees. Once again, we plot our sigmoid curve, scratch that. And once again, once our sigmoid curve is plotted and our threshold is set almost always at 50%, we can use the sigmoid curve and calculate the probabilities, and here the independent variable of width, which I assume is an application of pesticides or no pesticides, to determine whether or not the probability of healthy is greater than 50%, the threshold, or less than 50%, the threshold. And now let's take a use case of a college admission problem. Of course, we can't solve anything using data science if we don't know what the problem is. So we need a problem statement. And here, the problem statement is simple. We are given a data set, and we need to predict whether a candidate will get admission in a desired college or not, based on their GPA and college rank. So the very first thing we need to do is import the data set. And if it's a small enough data set and it can fit into our computer memory, then we are golden. Otherwise, we have some work to do. The data set that we were given is in CSV format, comma separated values. CSV files are easily imported into our environment. Once we import the data, we next need to select and import the libraries that we will need. Although R is a great programming language with a lot of built-in functions, it is easily and powerfully extended by the use of libraries and packages. Then we need to split the data set into a training set and a test set. It's important to note that the data set that we've imported, that we were given, has the GPAs and college ranks for several students, but it also has a column that indicates whether those students were admitted or not. So what we're saying is that the data set has the answers. And if you think about it, it must. How could we possibly train a model, have a model learn, if we didn't know the answers already? That's why it's called machine learning. So we train the model, and then we test the model. Once we split the data into training and test sets, we will apply our regression on the two independent variables, GPA and rank, generate the model, and then run the test set through the model. Once that is complete, we will validate the model to see how well it performed. So now it's demo time. So here we have our studio, my favorite IDE, or integrated development environment. And I have a script already composed to run our logistic regression on the problem at hand, which is our college admissions problem. So let's just walk down the script before I run it and talk about the various points in the script. So first, define the problem. Well, the problem was defined, and you really can't do anything in data science without a clear problem definition. Once the problem's defined, you can load your libraries, acquire your data, set the working directory. In my case, I'm on Windows. Explore the data, munge the data if necessary, and then prepare the data. Scale the data if necessary, split the data into train and test data sets. Then train the model using the training data and run the test data through the model, and then validate the model for accuracy and precision, etc. So here we are going to load our libraries. I'm going to use a package called CA Tools. And now that the library is loaded, I'm going to set my working directory. And if I come over here to the Files tab, you'll see that there is my working directory. In that working directory, there's a file called binary.csv, and that's the CSV, the comma separated value file that the college gave me. I'm going to ingest and then look at that data. And as you can see, it has 4 columns, GRE, GPA, rank, and then the answer column, admit, whether or not someone was admitted, which would be a 1, or not admitted, which would be a 0. And if we come over to the right, we can look and see some of the first few values of each of those 4 columns. Now let's split the data. We're going to take this my data frame and split it into 2, a training set and a test set. And the ratio we're going to use is 80-20. So 80% of the data will go into the training set and 20% will go into the test set. Now that ratio could be 60-40, it could be 70-30. Typically, it really depends on the size of your data, how much data you have. But this is, for our example and for our purposes, 80-20 is perfect. Next, we'll do a little data munging. In general, you munge the data early on after ingestion, and you really have to be careful. In this case, we don't have any missing values. We don't have any real outliers. Our data was pretty clean when we got it and ingested it. But in general, that's not the case, and a lot of work and a lot of attention needs to be paid to the munging process. Here, we're just going to take our data, the admission column and the rank column, and convert them to categorical variables. Right now, they're integers, as you can see on the right-hand side. And once I run these 2 lines, they will be converted to factors. And now the fun stuff. We're going to use the GLM function, the general linear model function, to train our logistic regression model. And the dependent variable is admit, and the independent variables are GPA and rank. And the little tilde sign here says the dependent variable will be a function of GPA and rank, the 2 independent variables. The data will be the training set, and the family will be binomial. And binomial indicates that it's a binary classifier. It's a logistic regression problem. There it is. We ran our model, and there's a summary of our model. You can see that there is some statistical significance in GPA and in rank by the coefficients and output of the model. So next, let's run the test data through the model. And once we have done all that, we can now set up a confusion matrix and look at our predictions versus the actual values. Again, this is important. We had the answers, and now we took and we predicted some answers. So hopefully our predicted answers match up with the actual answers. We'll run a confusion matrix. As you can see, the predicted values versus the actual values. And it's important here to note that if it was predicted false and it was actually false, and we see 189, or if it was predicted true and it was actually true, which is 27, we did well on those. But there are a few that were predicted incorrectly. Some were predicted true but were actually false. Some were predicted false that were actually true. And now we'll confirm what our percentage accuracy is, 72%. Not bad, but we could probably do better. How? We'll leave that to another video.
What is a decision tree? And here we have kind of a new looking front panel of a car driving down the street. And we have left or right. So you come into an intersection, you got to decide which way to go. Are you going to go left or are you going to go right? Wait or go. So do you go right away? We have a green light, so probably want to go right away after you check for cross traffic and make sure no one is asleep at the wheel or talking on their cell phone. Decision tree is a tree-shaped algorithm used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So another example is we have a shopkeeper, very nondescript shopkeeper, kind of a little spooky without the eyes. So we have a shopkeeper and he wants to organize his stall. So I must organize my stall, and he's looking around trying to figure out what the best way to stack all his goods are. And he has some broccoli, some oranges, and some carrots. This is kind of a nice example because we can see where some of the colors and shapes overlap where others don't. And so you can create a tree out of this very easily. You can say, is it colored orange? If it's not, well, it goes into one stack. Well, that happens to be all their broccoli. And if it is colored orange, then it goes into another stack. And you're like, well, that's still kind of chaotic. You know, people are looking at carrots and oranges, a very strange combination to put in a box. So the next question might be, is it round? And if it is, then yes, you put the oranges into one box, and no, that means it's carrots, we put it in the other box. And you can see that a lot of stuff we do in life easily can fall into like a decision tree. How do you decide something? You know, does it go left? Does it go right? Yes or no? And even with this, we even have a number of different end choices: broccoli, carrots, and oranges. So what kind of problems does this solve? What problems can be solved by using a decision tree? Classification. We're dealing with the classification, identifying to which set an object belongs. And from our example we just looked at, a carrot is orange while broccoli is green. I guess it's nondescript day. It's kind of without the faces. I love it. Because a lot of times when you're looking at data, you really don't want to know what exactly the data is, but you're sorting it. So, you know, like this kind of represents data that you really don't know exactly where it's coming from. Just kind of a fun thing. Regression. Regression is another problem that can be solved. Regression problems have continuous or numerical valued output variables. Example, predicting the profits of a company. So we have two different primary problems we solve for. We solve for classification, is it green or is it orange? And we solve for regression, which is a continual number. So, you know, if you're doing stocks, this would be a dollar value that ranges anywhere from 0 to thousands of dollars. How does a decision tree work? Terms you must know first. So before we dive into the decision tree, let's look at some of the terminology for the decision tree. We have nodes. Each internal node in a decision tree is a test which splits the objects into different categories. And continuing with our vegetable stand example, we have broccoli, no, it's not orange, and oranges and carrots are, and so on. So you can see right there where it splits, that's a node, where the oranges split and the carrots split into each of their own groups. And each one of the splits is a node. The very top node of the decision tree is called the root node. So the very first one we started off where we split it is it colored orange. And you can see that pointed out nice and neatly there. This is a root node at the top. Each external node in a decision tree is called the leaf node. The leaf node is the output. And you can see down here we have our broccoli and we have our carrots and our oranges. Each one of those is a leaf node. So to quickly rehash our terms, we have anywhere there is a split, that's a node. And if it's at the very top of the tree, that's the root node. And if you're at the very bottom of the tree where you have a final answer, that is the leaf node. So you have a root node, a leaf node, and then everything else is just a generic node. So one of the most important terms or concepts that powers a decision tree is entropy. Entropy is a measure of the messiness of your data collection. The messier or more random your data, higher will be the entropy. So we can see here we have broccoli, oranges, and carrots are all mixed together, and it's very chaotic. And you could say this collection has high entropy. And if we sort out the carrots out of here, and I guess just one of the broccoli, I don't know where the other broccoli went. You could say if we have just the oranges and the broccoli, this is a lower entropy. They say this collection has low entropy, but really it's higher and lower. One is higher or lower than the other one. And from entropy, we get information gain. Information is the decrease obtained in entropy by splitting the data set based on some conditioning. So we have our information 1, which we can there's actual computations. And so we have our E1, which is put in there for our entropy value at the base node or root node. And we have A2, which is a leaf node. And so we can actually calculate, there's calculations for entropy. And we actually look at those two values, the entropy, and we take that, we have E1 is greater than E2. Therefore, the information gain equals E1 minus E2. So here we have another example, and we're actually going to attach some values to this one in just a moment. So we're going to move away from the fruit, and we're going to go to everybody's favorite thing, organizing a child's closet. And here we have a young lady waving at us, "Hi, my cupboard is a mess. I must organize my stuff." And we're going to classify the objects based on their attribute set using a decision tree. We can look at it. We have a shape, a size, and a label, and a number. And I'm going to go ahead and look at the labels, because that's really what's key on this one. Is we have a couple balls in here, some books, cards, and blocks. And if you look at that, when you have something that's a ball, it's round, so it's a very different shape. The book, card, and blocks are all rectangular, but the books are a different size. So the books have like a size 6. I guess you think of them as very large. Cards a size 4, so they're not quite as big. And the blocks are little Lego blocks that looks like kind of fun to stack on there. And then we can actually quantify this, and we can actually say, hey, we have different numbers. We have 2 balls, 2 books, 1 card, 4 blocks. And we split at each level based on certain conditions on the attributes. So splitting aims at reducing the entropy. And we have a formula. Our first actual formula that you'll see happens in the background when we're running these different modules in R. And it looks a little complicated, but we can break that up and simplify that for you. So we see this formula, the negative sum of I of x equals the probability of 1 value of x times the log of 2 probability value of x. The term probability value of x, it's probably easiest to understand if we go ahead and put the numbers in there so you can actually see what we're looking at. And so we plug the numbers in there, we look at the probability of the value of x. Well, if we do the number of balls, there's 2 balls, and the total number of items is 9. So we have a probability of any one object being 2 out of 9. So that's pretty straightforward math. When you look at the numbers, you can actually see that very easily. And so we can calculate our entropy of 2 over 9 times the squared log of 2 over 9 plus 1/9 the log squared of 1 over 9 plus 4 over 9 times the log squared of 4 over 9. So our whole group is the sum of all the entropies. And so when we look at that, we have the entropy of the balls, which is the 2 over 9, rectangles 2 over 9, books 2 over 9, cards 1 over 9, and the blocks 4 over 9. And we can just plug those numbers in there, and we get a value of 1.8282. So what the heck does a module do with that number? Well, now we must find the conditions for our split. Every split must give us the maximum achievable information gain. And so we have our first entropy value, 1.8282, and it turns out when you compare all the different individual entropy values for the balls, for the books, for the cards, for the blocks, rectangles, you find out that the biggest split is going to be in the shape. And it's going to be, our first split will be on the shape that will directly segregate the balls out. So they'll split up a huge group from the other. And so when we compute that, we end up with E2, which is all of our rectangles, and then we have a leaf node, which is the balls. And so with our E2, we see that 1.3784 is much less than the 1.8282. And so our second split will be on the size, as that will directly segregate the books. And so when we do that, we can see that if the size is greater than 5, all the books go to one side, while the cards and the blocks go to the other. And again, we have our E3, which equals 0.716, which is considerably less than 1.3784. So our entropy is dropping each time we do a split. And of course, our third split we look at, and we'll see that we're left with size again, and we split it with 4 and 2. In this case, if it's greater than 3, it's going to be a block. If it's less than 3, it's going to be a card. And at this point, each of our objects is looped into similarity, so they all look the same, and we end up with an entropy of 0. And so you can see as we go down, the entropy continues to get less. And because it hits 0, we can say all our objects are now classified with 100% accuracy. If it was only that easy to clean the kids' closets. And you can see we have a nice drawing that shows you where all the leaf nodes are in this, in which case we have the balls, the books, the blocks, and the cards are part of the leaf node. And the root node is our first split when we have all the objects and we're splitting them by rectangle by shape. So we're going to dive into the use case. And in this case, we're going to get a little morbid. There I am behind my desk. That's definitely not me. I don't have that big of a chin. But I do usually have a cup of coffee, and it looks kind of like that. It's sitting next to me on my desk. So the use case is going to be survival prediction in R. And let's implement a classification of data set based on information gain. This is going to use the ID3 algorithm. Don't let that scare you. That's the most common algorithm they use to calculate the decision tree. There's a couple different ways they can calculate the entropy, but the formula is all the same behind it. So ID3 is most common in R. And then we'll be using the RStudio for our interface, for our IDE. So RStudio is free to download. There's the free version. Of course, there's an enterprise version, and there's all kinds of different choices in there. But one of the wonderful things about R is that it's been an open source for a very long time and is very well developed. And it's also very quick and easy to use on a lot of things. So this is going to be in the RStudio IDE. There's some other interfaces, but I would suggest using the RStudio. It's the most common one. And if you remember, I said this is going to be a little morbid because we're talking about how many people survived and died on these ships. So in this case, we have a nice vacation cruise ship going on there, or I'm not sure what that is with the tugboat. So we have a ship, and it had 20 lifeboats. The lifeboats were distributed based on the class, gender, and age of the passengers. We will develop a model that recognizes the relationship between these factors and predicts the survival of a passenger accordingly. So we want to predict whether the person is going to survive or die in a shipwreck. And we'll be using a data set which specifies if a passenger on a ship survived its wreck or not. So we're going to look at this data. And if you open it up into a spreadsheet, and don't forget you can always put a note on the YouTube video down below, and we will be monitoring that, and you can request the data set sent to you or more correspondence. You can also go to www.simplylearn.com and request this data set too. And it's just a simple CSV file we'll send out. And you can see right here we have survived. So 1 indicates a person survived the wreck. 0, they didn't make it. They were under the water. And the luxury class of the cabin, so if they were in, what value is like 1, 2, 3, depending on what luxury class they were. And then we have, this is kind of interesting, how many siblings they had. So it's kind of an interesting added statistic in there. Number of parents on board, and disembark location, so where the destination is. So here we've opened up RStudio. And if this is your first time in RStudio, you'll notice that it opens up standardly in 3 panes. The upper left is for text documents you're bringing in, and then the bottom left is the actual commands as they're processed. And then on the right-hand side, you have your environment set up on there. Now, I've zoomed in with my font a little oversized. In fact, we can even take that up one more size and see if we can get a larger setup view. Here we go. So I've set the font for 18, probably a lot larger than you need to work on a project. And the first thing I'm going to do is on the right-hand panel, we're going to be working with plots. So I'm going to click on the little plot tab up there. And I'm just going to collapse that over to the side for right now. And then I'm going to open up the bottom one. And you'll see on the top, I actually have 2 different tabs. Team in the back was really nice to set up the whole package for what we're working on here. And we'll go through this line by line. And then you'll see as we execute the different lines, they're going to appear down below. So I'll be flipping between these 2 left panels. And let me go backwards just for a second here. We're going to do this part. So let's take a look at the installs. And if you look at the installs, and I'm not going to actually run the installs because I've already run them on my computer. So these are already installed in my R packages, and I don't have to rerun them. We have a number of packages we're bringing into R because that's how R functions. And the first number of packages are all part of our decision tree. So our F selector, our R part, our caret with the dependencies equal true, and our dplyr and our R part plot. Ooh, that's a mouthful. You'll need to import all of these in your setup. And the first one, which is your F selector, computes your chi-squared, your information gain, your entropy. All of those formulas are part of the F selector. So when you bring it in, that's what that package is. The R part is your partitioning of your decision tree. So these are your primary 2 decision tree modules that we're bringing in. The caret is a part for actually splitting apart the data, because we always want to do a test set, a train set. So they built a package caret to kind of handle all those. You'll see caret used in a lot of other machine learning packages when you're doing the R. The dplyr is for mutating your data, so you can sum it, you can classify it, you can filter it. That's all part of the dplyr. And then our part has another piece called plot, and that's for helping us plot the data as we sort out the tree, because the R part creates the tree, but you still want to be able to plot it. And then we come down here and we have some additional tools. We're going to work with a spreadsheet. This is a Microsoft Access spreadsheet, so we're going to use the XLSX package to import it. And you might think that's a little outdated, because I know when I'm doing any new projects, I try to save my data into a comma-separated variable file or something more standardized. But a lot of times you'll end up with these old databases where they're exporting data, and their export comes in an Excel spreadsheet, and guess what? This is a time saver. Instead of opening up the spreadsheet, resaving it as a comma-separated variable file, you can just open it right up in R, which is really nice. And then we have our data tree, which goes right along with displaying the data. So we have our rpart.plot, and we're going to put that into the data tree so we have a nice visual. And finally, you need to install the package CA Tools. And CA Tools is another package used for general manipulation of your data and your vectors. So it also has a split function for training data. I know we have another package for that, but both those packages fit in there as far as the working with the data. So a lot of times you'll see these loaded in there together. And you'll see in a moment we'll import the elementary StatLearn package also, which is very generic, working with data setup as far as statistics and data processing. Now, because my Java setup is a little different because I use the developer package, well, the latest update of the developer package and the R are struggling to see each other. So I need to go ahead and add this in. Chances are you don't need to worry about this. But if you do get an R Java error, you'll need to go ahead and add in a line to set your environment. And I'm just going to set the Java home. I went ahead and looked up the last solid JRE folder, and you'll see under Program Files Java, you can look them all up to make sure it's the JRE and not the JDK. The difference between those is one is a standard executable, that's a JRE folder, that is a folder, not an actual file, and the JDK deals more with developer side on things. And I'm going to go ahead and run this. And if you're in R, you can run these lines individually by holding your control key down and hitting the enter button. So I've now loaded my workspace and set my environment here. And we can actually look and just make sure system.getEnvironment is the opposite one. And I can just look real quick and say, hey, what's my Java home set to? And if I run that, whoops, I forgot to put brackets around it. There we go. And if I do that, you'll see that it's set to the JDK 18025. And again, we're looking at the split screen. And let me just move this up here a little bit. And let me hit the enter key a bunch of times so it comes up on the screen. When I run it, and I'm running it line by line, the run text then appears down here, and this is what's actually being executed. So I could just as easily type it in down here as putting it up here on the top part. And that's just a little bit of RStudio and working with RStudio. So I've shown you the installs, and again, I've already installed it on my computer, so it takes a minute or two to install it. We need to go ahead and then bring those libraries in to work with. So basically, we're going through all the different libraries we're using. Element StatLearn is a standard R library, so it should already be installed. You don't have to install that one. And I can just go right down them, and you'll see as I install them that they show up on the bottom. And every time you go to run a new setup, you need to go ahead and install these, pull the libraries in. You got to tell your RStudio these are the libraries you're using. And you can see right down here that as it executes them, it has all the different things. One of them had like a couple different parts to it, so it loaded the lattice and the ggplot2. Really nothing to worry too much unless you see errors down here. So if you start getting error codes, then you might have to go troubleshoot and find out why it's not installing correctly, or did it install correctly. But it's pretty straightforward. We've covered all the libraries. And again, if you want a copy of this code, simply add a comment down below on the YouTube video, or visit www.simplilearn.com, and they'll be happy to send you a copy of the base code. The next step is we want to go ahead and load the Excel file after setting the working directory. So let's go ahead and set the working directory. SEWWD is a command for that in R. And then this is wherever you have downloaded your data to and your files to. A lot of times if you get the zipped framework sent to you, it will unzip all into one location. And then you got to look that location up and put that in here. A lot of times it automatically sets that for you if you're working in the same directory. In this case, you can see I've pasted in a very lengthy path because I have this as part of my documents, my business docs, and Simplilearn and marketing videos and so on. And I'll go ahead and do the Control Enter and run that. So now my working directory is set. And you can see down below it's executed this on the console down here. And if I open up that working directory, you can see I have a ship XLS file. That's the data we're going to look at. And we looked at that on the slide. You could also open this up, and I will want to go ahead and open it up with a notepad. By default, it'll open up as a spreadsheet. Oh, it is an Excel file, so I'd have to open it up as an actual spreadsheet. Wasn't thinking that one through. This is one of the problems with saving stuff as a proprietary ship file, even as something as widely used as Microsoft Excel spreadsheet. But when we open up the spreadsheet, you can see here the same data we looked at before. That's what's coming up in this file. And so I take this file, we can go ahead and let's create a variable. We'll call it add. And we're going to assign it. That's what the lesser than dash means if you've never used R before. And we're just going to assign it a ship XLS. And then I'll do my Control Enter and you'll see it run down here. Ship. Add is assigned ship.xls, or Excel spreadsheet on there. And then let's have another variable. We'll call it df for data frame. And we're going to assign this read XLSX. And that's from the library SLXX that we just imported. And we want to read the file add, because we just created that variable with the ship.xls. And I didn't catch this right away, but you'll see when we open it up in a spreadsheet, it might be hard to see in your video screen, it has the first sheet is called ship 1. So this data is on the page ship 1 in the Excel spreadsheet. And we got to make sure that we tell the reader to look for that. And so we can simply do that in our command line. Sheet name equals, and it was ship 1 on there. So we go ahead and hit the Control Enter and run this line, and it brings it down below and executes it. It's now reading in that data from that spreadsheet. That's what's going on. And it takes it just a moment to go ahead and read it in. And then with any data processing, we need to select the meaningful columns for the prediction. So this is important that we sort through our data and set it correctly so that whatever we're feeding it into can read it correctly. We can do this with df. We're going to reassign it, and we're going to select, and from there we're going to select df as our main data frame going in, and then list the columns that we want. And if we look at the data, we have survived, we have a class, we have a name, sex and age, and then there's siblings and parents. We really don't want to know the name because we don't need the name to run this on here. And then we got to decide which one of these we want to work with. And the guys in the back played with the data a little bit, and they came up with the following columns. Survived, which we need definitely, because that's what we're actually trying to figure out is whether we're going to survive or not. What class which class of the boat they're riding in, whether first class, second class. Sex and age. And we went ahead and dropped the rest of them, at least for this example. And so I can go ahead and do my Control Enter, and you'll see it execute down below. And now df equals these 3 columns, or 4 columns. Plus our answer is one of those. So I always think of it as 3 columns plus 1, but it is 4 columns. And then for the next step, we want to make sure the data is in the right format. So again, I'm going to reassign the df, and we're going to mutate the data. And that means we're going to take each one of these columns, and we're going to let it know what kind of data that is. So our first one is we got to put the database in, or the data frame in there, df. And then we want to go ahead and do survived equals a factor of survived. So this is a yes, no. It's letting us know that this is a 0 or a 1 on here. And then for the class and the age, those are as numeric. There's other ways to process class since it is a very restricted number on there, but for this we're just going to do it as a numeric value. Same thing with age. And you see we didn't do anything with sex. We're just going to leave that as male or female. And that's fine for this because it'll pick up on that when we run the decision tree. And we'll do our Control Enter. So now I've assigned the new df, and you can see it comes down below. as we run it on there. So this is now loaded, and DF now is a mutated data frame that we started with, and we've set it up with our specific columns we want to work with, in this case survived, class, sex, and age, and we've formatted 3 of those columns to a new setup. So one of them is factor, that's what we use for survive, so it knows it's a 0 and 1, and then we switched class and age to make sure that it knows that those are numeric values. Now that we have our data formatted, we need to go ahead and split the data into a training and testing data set. And by now, if you've done any of our other machine learning tutorials, you know this is standard. You need to have your data that we train it with, and then you got to make sure it works on data that it hasn't trained on. So we'll go ahead and do the splitting. Let's take a look and see what that looks like. And when you're dealing with splitting the data, we're doing a little randomness, so we'll just go ahead and set the seed to 1, 2, 3. You can set that to whatever number you want. That's just setting the random variable seed. And we'll go ahead and hit enter on there. And to do this, we're going to create sample, and we're going to go equals sample.split. So we're splitting up the data. This is actually creating a whole new column, trues and falses, and it's all stored in sample. And we want our data frame, and we use a $sign to denote that we're going to be working with one of the different columns. A nice thing you can do in R, and it actually shows my survived, so DF survived. And then our split ratio, I wanted to add a period in there, which it doesn't have. Our split ratio is going to be equal to, and we'll do 0.70. So we're going to take 70% of the data of those that have survived, and we're going to just randomly select which one of those we're going to use for training and which one we're going to use for testing it out later. And we'll hit our enter and load that sample in there. And then we'll go ahead and create our train and our test data set. So I'm going to set train equal to, and this is where it kind of gets interesting because we're going to do subset, and then we're going to do a subset of our DF where sample, and then we're going to use equals, since this is a logic gate. So wherever it sets sample equal to true, we're going to use that line in DF. And this is, of course, R, so it's all capitalized for true. So here's our trained data frame we're creating. So when I execute this and it shows up down below, it goes up and says, hey, this sample created a whole bunch of trues and false. And we're going to take those trues and falses, and wherever we've created a true, which is 70% of the data randomly selected, that's what we're going to train the data with. And then we need our test set, and that's a subset, just the same thing we just did. And we need our data frame, and this is where the sample equals false. And again, when I hit Control Enter, it goes down this line of code and it runs it down here in our terminal window. So now we've nicely split our data up. We have our training data set and our test data set. And this is, of course, where we get to the point of what we're actually trying to do, which is create our decision tree. And we're going to do that by training the decision tree as a classifier. This always gets me. You spend all this work sorting through the data, reformatting it, in this case mutating it and filtering it, and creating a train set and a test set. And so we're going to go ahead and create our tree, and we're going to assign to it the R part. That's the module we imported. And for the R part, we need to go ahead and do what's called a survived, and this is kind of a little complicated to look at, so let's just take a quick look at this, and I'm going to go backward on it. The first part is we're importing the data, so data equals train. And then what we want to know is who survived. So the first part we put in here is the column we're looking for is survived. And you'll see that we have added the squiggly mark in the period because we're looking just for this prediction. We just want to know who survived on these boats for programming our decision tree. And I'll go ahead and hit Control Enter, and we've now created the tree. That tree with all those values is now in there. And if you remember from before, we've taken from when we did the closet full of clutter, we've done the same thing where we have our entropy, and that one line computes the entropy and the increase in information, and it brings entropy down to 0. So it's the same thing, but instead of applying it here as we did visually to the closet, it's now applied it to the data on the ship. It's now looked at the survival of 0 or 1 based on female, male, what age they are, where the best split of the age is, and what class they were in. You can see we have first class. If we go down there, I think there's third, second. So I guess it's class 1, 2, and 3. But you can see that's how it's split it up. So it's used these different variables to minimize the entropy and maximize the information gain. And that's all done in that one line of code. Boy, we worked on all that theory, and computer does it for you in one line of code. It's important to understand the theory behind it so you know what's happening. Because as they make changes to these, or if you add special settings on it, you have to know what they're doing. But in this case, you can see that once we get it formatted, the computer does all the heavy lifting for us. And it never ceases to amaze me just how advanced machine learning has become these days, and how easy it is for people to get into it and learn the basic setups and be able to compute your different machine learning models. Once we've computed our decision tree and we built it on there, we want to go ahead and start doing predictions with it. And what are we going to predict? Well, you remember that we created our data with the train and test. So we have our training data, which we programmed the tree for. Now we want to see what it does with the test data. So let's see what that looks like. And we can wrap that into tree.survived.predicted. We'll assign that to our prediction. And this is nice because we have the command predict from one of the modules, the rpart module that we brought in. And I can simply put in here that we're going to use the tree. We have our test data and type. And this happens to be classification or class. And this would also be, if you were to distribute this tree, you could save the tree and send it someplace else to be used on new data. This would be the command line you would use to predict on here. Predict, you have your tree saved, you have whatever data you're putting through, and you let it know it's doing a classification on the tree. And we'll go ahead and run that. So now that's loaded up. And now that we've gone through, we've trained our tree, we run a prediction on our test data. Remember, the tree had never seen the test data till now. So we've already built the tree and we're just testing it out. And to do that, we're going to use a confusion matrix for evaluating the model. And let's see what that looks like. And that is simply confusion matrix. So once we have the confusion matrix, which came in from our caret, we need to compare the two different pieces of data. And the first one's going to be the value we generated up here. We have tree.survived.predicted. So I'm just going to copy that and paste it down here. And then the second one is the tree. We're comparing that to, let's see, survived. And it's not the tree. It's easy to get confused sometimes when you're moving these things around. We're going to compare it to test, the test group of data, specifically the survived column. And let's go ahead and run this and see what that looks like. And so let's go ahead and scroll up a little bit here to where it first executed the confusion matrix. And the most important part of this is that we have our prediction and our reference. And so 0 means they didn't survive, 1 means they survived. We had our prediction on here versus the actual. And that's what these two columns mean. And so when you read this little chart, we have 0, 0. So both the prediction and the actual reference said we agreed on 218 values for people who did not survive. A little grim there for data. Remember I talked about this is morbid data, talking about death rates of people on boats. And it says that they both agreed on 93. So 93 of them where we predicted the value that they would survive, and the reference came up the same. Likewise, the predicted, where it predicted 1, and the reference said, no, these people didn't survive, well, our prediction got 25 wrong. And where it says they didn't survive, and they actually did, it got 57 wrong. And we can come on down with the confusion matrix, and we can look at the accuracy. It comes up with the 0.7913 or 95% CI. So yeah, you're looking at pretty high accuracy. Information ratio, p-value. When you're in statistics, the p-value is one of the things we look at. Remember that there are certain values, if it's over 0.95, it's considered highly valuable variable. 0.5 means maybe. Anything less than that means it's probably not connected. You have to look up the p-value a little bit more on that. And then they just have more information down here, which you can go through and But the important part is that we have a very high accuracy. That's what we're looking at. This is a very accurate model. And again, always remember the domain you're working with. Certainly this is an example, and this is a good little piece of data you can play with. But if I was, say, betting money, and my accuracy came up as 79% or over 95% CI, I'd be like, yes, let's bet on that. That's a good bet. But if I was betting on a life or death situation, I might kind of rethink that a little bit if it's going to affect my life that way. You can also look at this as if you're trying to figure out where the boats go in this particular example and where to put the lifeboats. That's actually pretty good. Be able to say, hey, we can increase the chances of people surviving this accident by putting the lifeboats in the appropriate places. And then, this is always fun. Let's visualize the decision tree. One of the cool things you can do inside of R real easily. And if you remember, one of the modules we brought in has a rpart.plot. We're going to take that and we're going to dump that into the PRP for the tree. And let's go ahead and hit enter. And this is fun. Let me move this over so you can get a nice view. You can see how it actually split it up. And let me just rerun that again. Now that I expanded the right, you'll see right here where one of the biggest splits was whether the person was male or female. I didn't know that was probably one of the biggest breaks as far as lowering the entropy and increasing the information gain. And then once sex is male, it came down here and it said you're not going to survive. I guess the men were throwing themselves overboard on the boat. I don't know. Maybe they're being very gallant and letting the women and children survive, which is what I hope that means. So once you know that it's not a male and it's a female passenger, if you were in class 3 or above, you had a high chance of surviving. If you were less than class 3, class 1 or 2, then it was based on age. And so you can see where age was greater than 19. So anybody over 19 had a high chance of surviving, and then if they were, or less than 19, I'm sorry, if the age was, a little confusing on that one. But if the age was one side of 19, they probably survived. If not, then it said, hey, if your age is less than 60, you probably survived, and if not, people who are older probably didn't make it out of the boat in time. So elderly have a much higher risk, which you would expect. You'd expect that to be the case, that elderly would have a hard time getting off into the lifeboats. And they would probably step aside for the younger generation. I know I would. So that might be more of a social norm statistic as opposed to a survival rate. Let's go ahead and put this back on over here and see what else we can do with this data. If you're working with the shareholders, it's good to have a lot of tools as far as how to display. They'll want to see this number here where you say, hey, this is what the confusion matrix looks like, and we got a 0.79 accuracy. That would be like the number one thing you would talk to the shareholders about. Other data scientists care about the p-value and the information rate and information like that. But this is really the core right here. This is how much data, and this also shows them how much data was looked at. So you can actually just add these numbers together and you can see how many different people were in this particular data set, or how many lines in the data set. But we go ahead and visualize the 2D decision boundaries. And let's take a look at that. That's kind of fun. It's a little bit more complicated, so I'm not going to go into it in too much detail today. Now, the guys in the back put this code together for me, which is great. So I'm just going to paste that in, because like I said, we're not going to go into it in too much detail. I want to just show you that there's some other ways to display the data that is not just this nice little tree over here, which gives us a little bit more maybe view of what's going on. As you dig deeper into data, that becomes very important. It might not be something so simple where you can look at, in this case, 1, 2, 3, 4 nodes. So they have 4 major nodes that they split the data in. So when we're looking at this, we're going to go ahead and create a set test equal to test, comma, C241. We're just assigning color column to go with the data. Okay? That's what that is. And then we're going to take set and have it equal to test. And we'll do x1, and we're going to set that equal to minimum set of 1 minus 1, max set of 1 plus 1 by equals 0.01. They had to play with these numbers a little bit to get this to look right. So we're creating a sequence on here from the set we created, so our test set. And then x2 is also creating a sequence based on different values. And then we're going to put that all into a grid. So let's go ahead and run that through all the way down to the grid. And they'll make a little more sense when we add the column names to the grid, okay? So we'll set our test. We'll create our x1 sequence and our x2 sequence. Remember, a sequence is just like, in this case, starting with 0.1, it's like 0.01, 0.02, 0.03, 0.04. So we're going to create a grid with all these values separated by 0.01. So that's all we're doing right now. And let's go ahead and set that up. There's our grid. And then we want to go ahead and create some column names. And for our grid set, we're going to have our C class and age. So we're just doing the class and the age on here. Remember, we did sex also before, so it's just class and age on this chart that we're pulling out. And we're going to create a Y grid, and the Y grid is going to equal tree survived predicted. Okay, so here's our Y grid and our predicted values on there. Now we're actually going to do something. We're going to plot, and we're going to plot the Y grid. Oops, hold on, let me see what's in here. And let me go ahead and just run the plot. It's got to be the there we go. So let's take a look at this and see if we can make a little sense of this code and what's going on here, because there's a couple of things going on. What we've done is we've plotted a decision tree classification data set. We've done our plot, and we have our set. So our set's equal to our test data. And then we have our main. We went ahead and give it a name, decision tree. And then we have our xlab and our xlimit, and we've set those up as class with our ylab equals age, and our xlimit equals range x1 comma ylimit equals range of x2. And when you look over here, you can see that we have age on the left and class on the bottom. And so based on age and class, and so once we put in this nice graph here, we want to go ahead and add our contours and our points. So let's go ahead and run that, and I'm going to run all three of these so we can see all the colors come in on the graph. And this is actually going to take a little bit, because remember, you can make it go a little faster by changing a couple of the notes up here. When we did 0.01 from the min to max, by changing that to 0.1 or other values, you can actually, it'll run a little quicker. And we're going to create a nice little decision tree classification test set just to see what that looks like and how that data displays. Now, that was taking so long to run with 0.01, I went ahead and just did a 0.1. So instead of filling the whole page with different colors for a really pretty view, now I just have these different colored lines coming across. It gives us another model that we can show for whoever you're working with in this case, your shareholders of the company or the individuals who you're posting to the web for. And you can see where we have the green and the red, and we've set those up to identify from the decision who's going to make it and who's not based on age and class. Now, my favorite one on this, and I'm going to go back and just highlight this really quick, was, let me just rerun that, go back to PRP tree where we display the tree. And that's where we split it in part, because this information gives us some keys that we can then use in other models. So it's good to know that sometimes what you're taking comes out, and maybe you create a bucket for people under 19, between 19 and 60, and over 60, and different things like that, so you can actually put people in buckets in a class age split. Just a quick note on there. Again, lots of different things from which you can display the data, and you can see how we use the decision tree to figure out chances of somebody surviving based on their class and their age. What is a random forest? And welcome to Raphael's vineyard in, I don't even know how to pronounce that, in Alsace, France, the largest wine production region in the world. So they have centuries of wine production and data they've collected on how to make their grapes and grow them, and how to properly get the right grapes and ferment them. Like Raphael, winemakers around the world are facing a grave problem. So let's meet the man himself and try helping him out. What is a random forest? We're going to come back to the vineyard, but we're going to look at some other examples along the way too. Open up the door, and of course here comes Raphael. I'd probably look closer to Raphael than I do to the young lad with the beard. Hey Raphael, so tell us how it's going. Not as good as before. Not many people work in this profession anymore, so every stage of production has gone slower. If only we could somehow speed up the process. Well, lucky for you, I'm a machine learning engineer. How about we automate the quality prediction process for wine? Let me begin by telling you what machine learning and random forest is. Machine learning is the science of applying algorithms that allow a computer to predict the outcome without being explicitly programmed. Random forest is an ensemble machine learning algorithm. So we're bringing in different pieces and then putting those pieces together. It operates by building multiple decision trees. Remember I told you we don't want just a lone tree out there, we want a forest? They work for both classification. If you remember from part 1, we had our vendor with his broccoli and oranges. I think he also had carrots. And it also, the output given by the majority of its decision trees is the forest final output. So if you have a number of decision trees, you have 5 decision trees and 4 of them say it's broccoli, then it's probably broccoli. And you can also use it as a regression model. The output given by the majority of decision trees is the forest final output. Just like you do in classification, you can also come up with actual values and numbers as a regression model. Could you explain how a random forest works in layman terms? It's always a good thing to explore the information on something a little bit easier to understand and see. Sure, let's consider the case of Sam, a high school student. This so reminds me of my own high school student who's just started his first year in college, asking all his friends. So Sam is confused on which course to take up. So he's trying to figure out what his next class is going to be at school. Should he take music lessons, dance lessons, math, science, maybe social studies? So he decides to ask a couple of his friends for suggestions. And Sam approaches Jane first. So he comes up to Jane and says, hey, which of these classes should I take? And Jane asks Sam a few questions based on which she can suggest. Theoretical? Do you like theory? No, he doesn't like the theory part. Calculative? Do you like calculative? He goes, yes, I like doing calculations. And so Jane, based on a couple questions, goes, she has her little decision tree there going. She goes, mathematics sounds good. So Jane forms a decision tree based on Sam's response and gives her suggestion. And of course, this is based on Jane's views and her history and the data that she's collected over her years in high school. Next, Sam approaches Bella. Bella asks him, hey, do you like the field of science? And Sam goes, yes. And then Bella goes, do you like new in industry? You like new things coming up in industry? And Sam goes, yes. And Bella goes, you know, you should, similar to Jane, Bella also forms a decision tree based on Sam's response and gives her suggestion and says, hey, how about artificial intelligence? Sam's like, oh, artificial intelligence. So Sam next asks Terry for his suggestion. And Sam goes, do you like scoring things? And he goes, yes. And he goes, do you like theoretical? And he goes, no. And he comes up and says, mathematics. So you have 2 people saying mathematics and 1 person suggesting artificial intelligence. Since 2 out of 3 friends suggested math, Sam decides to take mathematics. And there's a lot of subtleties in this example. It's actually a really good example. Some of the things we run into in data science is when we collect data, and we collect from different sources, we might have data from one source that measures one thing or one set of instruments. And we might have data from another source that measures something else. We saw that with each of his friends are measuring different things and asking different questions. That's a little bit beyond the scope of this particular tutorial. So let's go back to our wine cellar. So you see, more the number of decision trees, more accurate will be the prediction. Random forests have a number of applications in market already. If you've been watching any of our other tutorials, you'll see that these are very common. We have in banking, it can be used to predict fraudulent customers. It is used to analyze symptoms of patients and detecting the disease. In e-commerce, the recommendations are predicted based on customers' activity. Stock market trends can be analyzed to predict profit or loss. Most recently, I was watching a review on weather here in the United States and the data they pull in for that. And one of the top weather places actually uses 5 different models. Random Forest was one of them, I believe. They use 5 different models to predict the weather, and depending on what the models come up with and what's going on, some of the models do better than others. I thought that was really interesting. It's important to note. So when you see us repeat the same things over and over, and you're looking at the different machine learning tools, you realize that we use multiple tools to solve the same problem, and we can find the best one that fits for that particular situation. So let's see how that fits back in our wine production. To help speed up the process of wine production, we will automate the prediction of wine quality. Suppose our random forest builds 3 decision trees. We have the first decision tree, which is going to divide everything by chlorides less than 0.08, and it's either yes or no, and then it's going to look at alcohol greater than 6, yes or no, quality equals high, quality not so good, and if the chlorides were greater than 0.08, quality equals low. So there's our first tree. And then our second tree is going to split it on sulfates less than 0.6, and pH less than 3.5. And again, we have it coming down here that if the pH is low and the sulfites are low, the quality equals high. If the pH is a little higher but the sulfites are low, it's not so good. And if the sulfides are greater than 0.6, we have a quality equal to low. And then we'll do a third decision tree. We'll split it based on pH. And we can see below how that tree looks like with our sugar less than 2.5. If not, it's a quality equals low. It's a real low quality. And if it is less than 2.5, then the pH decide whether it's going to be a quality high or not so good. And if we track one of our wines down the list, we'll look at it and we'll say, oh, 2 out of 3 decision trees indicate the quality of our wine to be high. The forest predicts the same. So this sounds promising. So let's go ahead and dive in and see what that actually looks like. So this is the data set that holds all the attribute values required to predict the wine's quality. And I'll pull this up in a spreadsheet in just a moment. But you can see here we have fixed acidity, volatile acidity, citric acid, all the way to quality. And then quality is like a 4, 5, 6, or 7, I believe. And this will be done in R. So let's go ahead and get started on our coding. We'll be using RStudio. Before we dive into RStudio, I always like to open up the data in the spreadsheet and look at the actual data that I have. And they've called it winequality-red.xls, so it's a spreadsheet, a Microsoft spreadsheet. And when we open it up, we'll see that it matches what we had before, as far as the slide was showing us. We have 12 different columns. The first 11 are our features, our fixed acidity, volatile acid, citric acid, things you always want to look at when you're looking at your data. And we've done this before in the part 1, but just a reminder, we want to note that we have decimal places here, float values in a lot of these things, especially the first number of columns. Our free sulfur dioxide looks to be an integer, but it varies a lot. So we have, I see some values all the way up to 51, 7, 4. So we'd probably keep this as a linear model kind of thing. Same thing with the sulfur dioxides, densities again, decimal places, sulfides, alcohol. Quality. I want you to note in the quality that we only have a few qualities here. This isn't like a spread between 0 and 100. It looks to be 3, 4, 5, 6, and 7. And so when we start looking at the process, we can have the option of either doing this as a series of integers or float values going from 3 to 7, or we can convert that to a categorical, 3, 4, 5, 6, and 7 being the categories. But we'll look at that in the coding here in just a minute. And finally, you'd want to go ahead and scroll down through the data and just look for missing data or anything weird. Obviously, working with big data, you wouldn't be able to do that. If this was spread across numerous computers and you had millions of rows. We have, 1,687 rows here, so it's a nice size spreadsheet, still considered a small data set. Let's go ahead and switch over, and let's take a look at this in the R. So here we are in our RStudio, and if you remember, it comes up automatically in 3 panels. I have my font on fairly large to help out. The upper left panel is a file that's open. You can have multiple files and tabs open, as you can see on mine right now. I'll probably close most of those in just a minute. And this is where you can put in your commands. Then you can execute these commands by either clicking on the run box or Control-Enter is the hotkeys for that. And all that does is then puts that down in the console and executes that line of command. You could just paste these directly in the console. I've certainly been known to do that if I'm loading up some data and I just want to take a quick look at it in R because I'm doing the coding in something else. Or if I just want to do a quick explore before I dive in and figure out what needs to be done. That's one of the tricks you can do. And then on the right hand side, we have our environment, history connections. We mainly are going to just be sitting on plots, and I'm just going to minimize this for right now out of the way while we dive in. If you haven't yet, you do need to go ahead and install the package Random Forest. I'm not actually going to do that because I've already run that. We don't need to rerun that. But I am going to go ahead and import it into our project with the library and then Random Forest. And we'll do the Control-Enter. You can always hit the Run button up there too. And then now the library has been upload it in there, and you can see down below, it takes this and just copies it and pastes it down below and runs it in our console. And then just a quick troubleshooting thing. My Java happens to be the developer's Java. The latest release of the developer's Java from last week is clashing with my R and rerouting my Java files. So chances are you don't need to look this up or find out where your Java is. But there's a JRE folder. If you do have an error that comes up in the next library, you look that up. It's usually under Program Files, Java, and you'll see JDK, depending on what version you have on there, and then find that JRE folder. And I'm just going to set the environment on there. You have to do that every time you run the script. So with R, there is a place in R where you can set it permanently, but generally it's set to whatever your system variables are set to, so you don't want to mess with that. So you just want to put this in your code if you're having problems, and you can always take it out. And then we need to go ahead and bring in another library, and we're going to be importing the spreadsheet. So it's the XLSX, since it's a Microsoft spreadsheet. And I'll go ahead and run that. Now let's go ahead and create a variable path. We're going to assign to variable path the location of our folder. So this is a very lengthy one. You'll have to copy and paste it off your computer. My name is Richard, and you can see it's under C column users, Richard's documents, docs business, Simplilearn marketing, random forest, and then the actual file, which is winequality-red.xls. So I put in the whole path in here. And you could also set the computer path to whatever folder you have it in, and then just use just the name of the file. But I went ahead and did this because a lot of times it's good to be aware where your paths are going and where you're pulling your data from. And again, I went the Control Enter, so you'll see that pushed the line down below and ran that line, so our path is now set. And then let's create a variable called data, and we'll assign that to a read. And we're going to be reading, let's see, where is it? There it is, on spreadsheet. And before I put in, we need the path, but we also need one more thing on the spreadsheet. Because it is an Excel spreadsheet, we need to know which page we're on. So let's go look that up. And in the spreadsheet, it might be a little hard to see because it's a very tiny font down there. But you'll see the page tabs on the bottom. This actually has two different pages, and we want page 1 for this project. So let's flip back over and put that in our code. And the term they use is sheet index. I always have to look that stuff up. And it was sheet index of 1. We'll go ahead and execute this. So at this point, we've now loaded the data into the variable data. And it's reading those in. I think there was a couple thousand rows of data in there, so it takes it just a moment to pull it in. Once I have my data in there, I always like to do something like this. Data, and I always forget in R it's head data. And we can run that. And you'll see it prints out what we looked at in the spreadsheet. So we have our fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, free sulfur, all the different things. We're actually looking for quality. So you want to keep that in mind, that quality is the final setting. Is it a 3, 4, 5, 6? What is the quality on there? And the first thing we need to do is we're actually going to take the data quality. And let me see, quality, there it is. In R, the $sign means that you're looking at one of the columns in here, or features as it is. So we see data $sign quality in R, that means that's what we're going to be editing. And what we want to do is we want to change the quality just a little bit. And so we're going to set it equal to. Now we're not assigning a variable, we're altering it. So data $sign quality equals, and we want to do as is one of the functions in R. And we're going to do as a factor. And then data quality, because that's what we're actually editing on there. And let's stop just for a second and look at this. Factor takes this and looks at the data as a categorically. So instead of it being on a continual scale of 0 to 100 or something like that, it actually looks at it as category of 5, category of 6, category of A, category of cat, category of dog. They're yes or no categories versus a continual. Now there's a lot of different things in here that we could do the same thing with, but all of these really are linear numbers, 7.4, 0.70. sulfur dioxide 3467. So we really don't need to mess with any of the other variables in there, but we do want to go ahead and set this up. And we'll come up here and we'll do our control enter, and it'll run it down below. And you'll see data quality equals as factor data quality. So we've now turned that into a factor, or into a categorical data. And so let me just bring this down a little bit. The guys in the back did the rest of this next piece of code. There are so many different ways, and if you have been looking at any of our tutorials, this should look kind of familiar. This is one way to do it. And you'll see we have our training data and our testing data. And so what we've done here is we have a data set size equals, and we're just going to do by the row. And so we want 0.8, or 80% of the data is going to be our training set to train our forest. And if you train a forest or any machine learning model, of course want to test it. So we're going to save 20% of the data for testing. And when you look at this, we have the index, which we set at 80%, comma, and then a negative index. So that's the remaining setup. So it goes from that index on. This is our notation for sorting out that data. And then we create the index, and we use the term sample. And this is just going to go in there and set our different samples for our in-row size, data set size, and everything. So we have an index now. So the data is indexed, and we're just going to pull off the first set of index and the end of the index for our data. And we can run all of this in one shot. We'll go into code, and we'll run selected lines. And so now we have our data in here. We have our training set and our testing set. That's what we wanted to get to. So once we've formatted all the data, then we get to the next real easy step, which is a single line to bring in our random forest. So let's go ahead and we'll use the variable rf, standing for random forest, and we're going to assign, if you remember correctly, we brought in our library random. If you wonder why I go up here all the time, it's because I'll forget which letters are capitalized in some of these because I switch between packages so much. But it's random with a capital F for forest, random forest. So the RF is going to equal random forest, and of course we start by telling it which column we're trying to predict. And of course you can always go down here and double check. We're running this on the quality. There we go, quality. And we're using just that column all the way to the end. And then we've added, our team in the back has gone in and played with this a little bit, and we'll go a little bit over what they did. But I'm going to put in the values that they have set for the different options in the random forest. Before I do that, it would help if I tell it what data to use. Data is going to equal our training set. And then we have the variables that they've put together. And let's just talk a little bit about what these different variables mean. So, mtry and ntree. These are some of the variables you play with the random forest. The mtry, not so much. When they first put it out, I think mtry was very common. 4 is a good value. I can't remember what the default is, but it's probably 3, 4, or 5 or something like that, depending. I think it depends on how many features you have going in there. So you could even just leave this as a default without too much troubles. The ntree, this is where it gets important, and I'm going to make this 2001. One of the suggestions is to always make this odd, like a tiebreaker, just in case. The default is like 500 or 501. And then finally we have importance equals true. I can't remember what it defaults to, but generally you want to set the importance equals to true. It actually looks at the correlation between the different features to make sure that there is some kind of correlation as it's doing its calculations. So our one line of code is going to assign our random forest and go ahead and train our random forest all in one execution. So this whole thing has been centered around getting to RF set to the random forest. And let's go ahead and execute this variable, or this line of code. And you'll see it takes a little bit down here to execute as it goes through and sets it up. And you'll see it probably takes a minute or so to execute the code, depending on the size of the data and how good your machine is. And then with all of our data, we can start looking at the answers. We'll just do RF, and we'll execute that. And you'll see that the random forest does a nice job. You can see right here it has our data equals training. It basically goes over everything we talked about. And you come down here and it has a confusion matrix, which is nice. We always like our confusion matrix when we're talking to our shareholders and explaining what the data comes out with and how it trains. And we can go ahead and plot our RF. Let's see what that looks like. And as the number of forests grows, remember we set it to 2001 forest, you can also see how the error comes in, how the different error on the different variables. This is kind of a nice graph that gives you an idea. It might help you adjust whether you really want to do 2,000 different forests. You might actually truncate this off at around maybe 800 because you notice the lines kind of continue on. Again, this is just still on the plot. And of course, the next step is we need to go ahead and predict. Remember, we split our data into two groups. So let's go ahead and get a result. We'll call it result, and we'll assign this one. There we go. We'll set this to a data frame. There we go, there's our data frame. And then, let's call this, we have our test quality, because that's what we're setting up on our test group with the quality on there. And then we want to have a predict, nice little keyword there to go ahead and run our random forest. And then we tell it that we're going to predict using our RF, our random forest, our testing group. 1 to 11 is what we're using. Type equals response. So let's go ahead and execute it. That's a mouthful on there. Somewhere I left out a comma in there, so it gave me an error. But you can see right here, we've set in there, now we have a result. And just real quick, we could do the head of the result, comma 5, and just take a look at the first 5 lines. And you'll see we have the actual value and what we predicted over here. And we could also just do all of the result and just see what that looks like. Oops. And print that out. And so it has all the different data we're going through on there. And finally, let's just go ahead and plot. There we go. We'll put plot up here, plot. And let's plot the result. And just see what that looks like. Maybe not the best one to show to the shareholders, but it does give you an idea. On the left, on the y-axis, you'll see that it predicted 8. And this tells you that a lot of the 8 and the 8 scale was probably gave us about 50% came up there at 8. Really, maybe 50% it didn't guess right, but it did come up there and say that it was at least a 4, 5, or 6, even where it was considered an 8. And so on. You can see these different blocks coming in, so that if you line up the 3 with the 3, 4 with the 4, and you kind of cross-index them, a heat map would probably do better. But for this example, we'll just do a quick plot of the data as far as how it works. And you can again see the results that we predicted over here, and you can look those over. Of course, back in the wine cellar, we're talking to our vineyard owner. And if you remember from before, we looked at this chart right here. The error rate is 29.05%. Therefore, our accuracy is 70.95%. If you're doing a vineyard, that's probably pretty good accuracy. And always check your domain when you're sharing this stuff, because if you're doing something that's life or death, maybe 70% accuracy might not be so good. But if you're looking at where you're going to distribute the bottles to for the wine and who's going to drink it, 70% accuracy is pretty good for that. That's probably a lot better than having no accuracy whatsoever and not even knowing what wine's going out to who. So we have automated the process of predicting the quality of wine. I myself prefer to predict it by sampling it. That's great, thank you. I'd like to visit this guy and sample his wine and find out just how good his different vineyards are. What is clustering? So we'll have a group of people here hanging out at a table or local coffee shop. I'm guessing coffee shop since they all have the same mugs. And one of them is trying to figure out what they're going to do. I have 20 places to cover in 4 days. I guess he's going traveling. That sounds fun. One of those breeze through Costa Rica or visiting the U.S. or going to Europe to go visit all the highlights. So he's got 20 places he wants to go, and he wants to hit them in 4 days. Very ambitious. And how will I manage to cover all of them? That's the question that he's coming up. How am I going to get to all these different places in the short time I have? Maybe he's a sales team, so he has 20 places he's got to do demos for. You can make use of clustering by grouping the places into 4 clusters. Each of these clusters will have places which are close by. So we're going to cluster them together by what is closest to the other one. Then each day you can visit one cluster and cover all the places in the cluster. Great. That's a great idea. If you're going to hit 4 different places, maybe you're going to cluster whatever streets are closest together so you don't have to spend all your time traveling. The method of dividing the objects into clusters, which are similar between them and are dissimilar to the objects belonging to another cluster. So this is a formal definition of clustering. And we have here what we call hierarchical clustering and partial clustering. And we're going to go more into detail on hierarchical clustering, and you'll see the difference between the two, where partial clustering doesn't have the descending graph. It just has groups of things. And under hierarchical clustering, we're going to go over agglomerative and divisive. And you can think of agglomerative of bringing things together and divisive as dividing them apart. And then partial clustering, the two most common ones are k-means. That's probably the most common used for partial clustering. And there's also fuzzy c-means. And there's other ways of clustering and other algorithms out there. But these are the two big ones, k-means really being the most common one used. But we're not going to dig too deep into partial clustering because we're studying hierarchical clustering today. So what is clustering? Well, the applications of clustering are pretty numerous. We have things like customer segmentation, what people kind of belong together, how do we group them together? We have social network analysis. So social networks, we might look at sentiments. What group of people like something? What group of people don't like something? And then we can use that sentiments to suggest new sales for them. This whole group is into Harley-Davidson motorcycles, so we cater to them to sell them Harley-Davidson motorcycle parts. And we find out that people in that group also like leather jackets, they also like motorcycle boots, and they like bandanas. My brother's into Harley-Davidson, so that's why I picked that kind of funny example. But you can kind of see we look for similarities between these people, and then we group them together accordingly. And that's a good sentimental clustering is very common in so many things today, where we want to know the sentiments on stocks. Who is interested in stocks, who's not. Sentimental analysis, we talked about customer segmentation and sales. Well, we want to know what kind of sentimental view people have on different restaurants if we're going to open up a new restaurant or a new putting stores in. And of course, city planning. A lot of this I just kind of aimed at the city planning side. City planning is big with clustering. We want to cluster things together so that they work. We don't want to put an industrial zone in the middle of somebody's neighborhood where they're not going to enjoy it, or have a commercial zone right in the middle of the industrial zone where no one's going to want to go next to a factory to go eat a high-end meal or dinner. So it's very big in city planning. And it's also very big in just pre-processing data into other models. So when we're exploring data, being able to cluster things together, reveal things in the data we never thought about. And then once we have it clustered, we can put that into another model to help us figure out what it is we want for our solution. So let's go a little deeper into hierarchical clustering. Let's consider we have a set of cars and we have a group similar. We want to group similar ones together. So below we have, you'll see 4 different cars down there. And we get 2 clusters of car types, sedan and SUV. So if you're just looking at it, you can probably think, oh yeah, we'll put the sedans together and the SUVs together. And then at last we can group everything into one cluster. So we just have just cars. So you can see as we have this, we make a nice little tree. This is very common when you see anybody talks about hierarchical clustering. This is usually what you see and what comes out of it. We terminate when we are left with only one cluster. So we have, as you can see, we bring them all together. We have one cluster. We can't bring it together anymore because they're all together. Hierarchical clustering is separating data into different groups based on some measure of similarity. So we have to find a way to measure what makes them alike and what makes them different. Agglomerative clustering is known as a bottom-up approach. Remember I said think of that as bringing things together. You see, think the Latin term agglo is together because you have your agglomerate rocks where all the different pieces of rocks are in there. So we want to bring everything together. That's a bottom-up. And then divisive is we're going to go from the top down. So we take one huge cluster and we start dividing it up into 2 clusters, into 3, 4, 5, and so on. Digging even deeper into how hierarchical clustering works, let's consider we have a few points on a plane. So this plane is 2D, so we have an XY coordinates, kind of makes it easy. We're going to start with measure the distance. So we want to figure a way to compute the distance between each point. Each data point is a cluster of its own. Remember, if we're going from the bottom up, agglomerative, then we have each point being its own cluster. We try to find the least distance between 2 data points to form a cluster. And then once we find those with the least distance between them, we start grouping them together. So we start forming clusters of multiple points. This is represented in a tree-like structure called dendrogram. So there's another key word, dendrogram, and you can see it's just a branch that we've looked at before. And we do the second group the same, so it gets its own dendrogram, and the third gets its own dendrogram. And then we might group two groups together. So now those two groups are all under one dendrogram because they're closer together than the P1 and P2. And then we terminate when we are left with one cluster. So we finally bring it all together. You can see on the right how we've come up all the way up to the top. Whoops. And we have the gray hierarchical box coming in there and connecting them. So we have just one cluster, and that's a good place to terminate because there is no way we can bring them together any further. So how do we measure the distance between the data points? I mean, this is really where it starts getting interesting. Up until now, you can kind of eyeball it and say, hey, these look together. But when you have thousands of data points, how are we going to measure those distances? And there is a lot of ways to get the distance measure. So let's go ahead and take a look at that. Distance measures will determine the similarity between two elements, and it will influence the shape of the clusters. And we have Euclidean distance measure, we have squared Euclidean distance measure, which is almost the same thing but with less computations. And we have the Manhattan distance measure, which will give you slightly different results. And we have the cosine distance measure, which again is very similar to the Euclidean, playing with triangles. And sometimes it can compute faster depending on what kind of data you're looking at. So let's start with the Euclidean distance measure. The most common is we want to know the distance between the 2 points. So if we have point P and point Q, the Euclidean distance is the ordinary straight line. It is the distance between the 2 points in Euclidean space. And you should recognize D equals, in this case, we're going to sum all the points. So if there was more than 1 point, we could figure out the distance to the not more than 1 points. This is the sum of more than 2 dimensions. So we can have the distance between each of the different dimensions squared, and that will give us, and then take the square root of that, and that gives us the actual distance between them. And they should look familiar from Euclidean geometry. Maybe you haven't played too much with multiple dimensions, so the summation symbol might not look familiar to you. But it's pretty straightforward as you add the distance between each of the 2 different points squared. So if your y difference was 2 minus 1 squared would be 2, and then you take the difference between the x, again squared, and if there was a z coordinates, it would be z1 minus z2 squared, and then take the square root of that and sum it all together and then take the square root of it. So to make it compute faster, since the difference in distances, whether one is farther apart or closer together than the other, we can do what's called the squared Euclidean distance measurement. This is identical to the Euclidean measurement, but we don't take the square root at the end. There's no reason to. It certainly gives us the exact distance, but as far as doing calculations as to which one's bigger or smaller than the other one, it won't make a difference. So we'll just go with so we just get rid of that final square root. It computes faster, and it gives us pretty much the Euclidean squared distance on there. Now, the Manhattan distance measurement is the simple sum of horizontal and vertical components, or the distance between 2 points measured along axes at right angles. Now this is different because you're not looking at the direct line between them. And in certain cases, the individual distances measured will give you a better result. Now generally that's not true. Most times you go with the Euclidean squared method because that's very fast and easy to see. But the Manhattan distance is you measure just the y value and you take the absolute value of it, and you measure just the x difference and you take the absolute value of it, and just the z. And if you had more, different dimensions in there, A, B, C, D, E, F, however many dimensions, you would just take the absolute value of the difference of those dimensions. And then we have the cosine distance. Similarity measures the angle between the 2 vectors. And as you can see, as the 2 vectors get further and further apart, the cosine distance gets larger. So it's another way to measure the distance. Very similar to the Euclidean, so you're still looking at the same kind of measurement, so it should have a similar result as the first 2. But keep in mind the Manhattan will have a very different result, and you can end up with a bias with the Manhattan if your data is very skewed. If one set of values is very large and another set of values is very small. But that's a little bit beyond the scope of this. It's just important to know that about the Manhattan distance. So let's dig into the agglomerative clustering. And agglomerative clustering begins with each element as a separate cluster, and then we merge them into a larger cluster. How do we represent a cluster of more than 1 point? So we're going to kind of mix the distance together with the actual agglomerative and see what that looks like. And we're actually going to have three key questions that are going to be answered here. So how do we represent a cluster of more than one point? So we want to look at the math, what it looks like mathematically and geometrically. How do we determine the nearness of clusters? When to stop combining clusters. Always important to have your computer script or your whatever you're working on have a termination point so it's not going on eternally. We've all done that if you do any kind of computer programming or writing a script. Let's assume that we have 6 data points in a Euclidean space. So again, we're dealing with x, y, and z. In this case, just x and y. So how do we represent a cluster of more than one point? Let's take a look at that. And first, we're going to make use of centroids. Very common terminology in a lot of machine learning languages when we're grouping things together. So we're going to make use of centroids, which is the average of its points. And you can see here, we're going to take the 1, 2, and the 2, 1, and we're going to group them together because they're close. And if we were looking at all the points, we'd look for those that are closest and start with those. And we're going to take those two, and we're going to compute a point in the middle. And we'll give that point 1.5, 1.5. And that's going to be the centroid of those 2 points. And next we start measuring like another group of points. We got 4, 1, 5, 0. When they're pretty close together, so we'll go ahead and set up a centroid of those 2 points. In this case, it would be the 4.5 and 0.5 would be the measurements on those 2 points. And once we have the centroid of the 2 groups, we find out that the next closest point to a centroid is over on the left. And so we're going to take this and say, oh, 0, 0 is closest to the 1.5, 1.5 centroid. So let's go ahead and group that together. And we compute a new centroid based on those 3 points. So now we have a centroid of 1.1 or 1, 1. And then we also do this again with the last point, the 5, 3, and it computes into the first group. And you can see our dendrogram on the right is growing. So we have each of these points become connected and we start grouping them together. And finally we get a centroid of that group too. And then finally the last thing we want to do is combine the 2 groups by their centroids. And you can see here we end up with one large group and it'll have its own centroid, although usually they don't compute the last centroid, we just put them all together. So when do we stop combining clusters? Well, hopefully it was pretty obvious to you. In this case, when they all got to be 1, but there are actually many approaches to it. So first, pick a number of clusters k up front. And this is done in the fact that we don't want to look at 200 in clusters. We only want to look at the top 5 clusters or something like that. So we decide the number of clusters required in the beginning and we terminate when we reach the value k. So if you looked back on our clustering, let me just go back a couple screens. You'll see how we clustered these all together, and we might want just the 2 clusters. And so we look at just the top 2. Or maybe we only want 3 clusters. And so we would compute which one of these has a wider spread to it or something like that. There's other computations to know how to connect them. And we'll look at that in just a minute. But to note that when we pick the k value, we want to limit the information that's coming in. So that can be very important, especially if you're feeding it into another algorithm that requires 3 values, or you set it to 4 values, and you need to know that value coming in. So we might take the clustering and say, okay, only 3 clusters. That's all we want for k. So the possible challenges, this only makes sense when we know the data well. So when you're clustering with k clusters, you might already know that domain and know that that makes sense. But if you're exploring brand new data, you might have no idea how many clusters you really need to explore that data with. Let's consider the value of k to be 2. So in this case, in our previous example, we stop when we are left with 2 clusters. And you can see here that this is where they came together the best while still keeping separate the data. The second approach is stop when the next merge would create a cluster with low cohesion. So we keep clustering till the next merge of clusters creates a bad cluster low cohesion setup on there. That means the point is so close to being between 2 clusters, it doesn't make sense to bring them together. But how is cohesion defined? Oh, let's dig a little deeper into cohesion. The diameter of a cluster. So we're looking at the actual diameter of our cluster, and the diameter is the maximum distance between any pair of points in the cluster. We terminate when the diameter of a new cluster exceeds the threshold. So as that diameter gets bigger and bigger, we don't want the 2 circles or clusters to overlap. And we have radius of a cluster. Radius is the maximum distance of a point from centroid. We terminate when the radius of a new cluster exceeds the threshold. Again, we don't want things to overlap, so when it crosses that threshold and is overlapping with other data, we stop. So let's look at divisive clustering. Remember, we went from the bottom up, now we want to go from the top down. Divisive clustering approach begins with a whole set and proceeds to divide it into smaller clusters. So we start with a single cluster composed of all the data points. We split it into different clusters. This can be done using monothetic divisive methods. What is a monothetic divisive method? And we'll go backwards and let's consider the example we took in the agglomerative clustering to understand this. So we consider a space with 6 points in it, just like we did before, same points we had before. And we name each point in the cluster. So we have, in this case, we just gave it a letter value, A, B, C, D, E, F. Since we follow top-down approach in divisive clustering, obtain all possible splits into 2 columns. So we want to know where you could split it here. And we could do like a A-B split and a C-D-E-F split. We could do B-C-E, A-D-F. And you can see this starts generating a huge amount of data. A-B-C-D-E-F. And so for each split, we can compute cluster sum of squares. And we can see here, actually have the formula out for us, BJ12 equals N1 of absolute value of x minus absolute value of x squared. So again, we're computing all the different distances in there squared, back to your kind of Euclidean distances on that. And so we can actually compute B of j between clusters 1 and 2. And we have the mean of the cluster and the grand mean, depending on the number of members in the cluster. And we select the cluster with the largest sum of squares. Let's assume that the sum of squared distance is largest for the third split we had up above, and that's where we split the ABC out. And if we split the ABC out, we're left with the DEF on the other side. We again find the sum of squared distances and split it into clusters. So we go from ABC, we might find that the A splits into BC and D into EF. And again, you start to see that hierarchical dendrogram coming down as we start splitting everything apart. And finally, we might have A splits in B and C, and then each one gets their own DEF. And it continues to divide until we get little nodes at the end and every data has its own point. Or until we get to K, if we have set a K value. So we've kind of learned a little bit about the background and some of the math in hierarchical clustering. Let's go ahead and dive into a demo. And our demo today is going to be, for the problem statement, we're going to look at U.S. oil. So a U.S. oil organization needs to know its sales in various states in U.S. and cluster the states based on the sales. So what are the steps involved in setting this problem up? So the steps we're going to look at, and this is really useful for just about any processing of data, although I believe we're going to be doing this in R today. We're going to import the data set. So we'll explore our data a little bit there. Create a scatter plot. It's always good to have a visual if you can. So once you have a visual, you can know if you're really far off in the model you choose to cluster the data in or how many splits you need. And then we're going to normalize the data. So we're going to fix the data up so it processes correctly. We'll talk more detail about normalization when we get there. And then calculate the Euclidean distance. And finally, we'll create our dendrogram so it looks nice and pretty and we have something we can show to our shareholders so that they have something to go on and know why they gave us all that money in salary for the year. So we go ahead and open up R, and we're actually using R Studio, which is really has some nice features in it. It automatically sets up the 3 windows where we have our script file on the upper left, and then we can execute that script and it'll come down and put it into the console bottom left and execute it. And then we have our plots off to the right, and I've got it zoomed in, hopefully not too large a font but large enough that you can see it. And let's just go ahead and take a look at some of the script going in here. It's clustering analysis, and we're going to work, we'll call it my data, and we're going to assign it in R. This is a symbol for assigning. And we're going to go read CSV. Read CSV file. And we'll put that in brackets. And before we go any further, let's just look at the data outside of R. It's always nice to do if you can. And the file is going to be called utilities.csv. This would also be the time to get the full path so you have the right path to your file. And remember that you can always post in the comments down below. And when you post down there, just let us know you want to connect up with Simplilearn so that they can get you this file. So you can get the same file we're working on and you can repeat it and see how this works. This is utilities.csv. It's a comma-separated variable file, so it's pretty straightforward. And you can see here they have the city, fixed charge, and a number of different features to the data. And so we have our ROR, cost, load, demand, cells, nuclear fuel cost on here. And then going down the other side, we have U.S. cities, Arizona, Boston. They have central U.S., so I guess they're grouping a number of areas together. The Commonwealth area, you can see down here, Nevada, New England, northern U.S., Oklahoma, the Pacific region, and so on. So we have a nice little chart of different data they brought in. And so I'm going to take that complete path that ends in the utilities.csv, and we're going to import that file. Let me just enlarge this all the way. Oops, I had an extra set of brackets here somehow. Maybe I missed a set of brackets. This can happen if you're not careful. You can get brackets on one side and not the other, or in this case, I got double brackets on each side. There we go. And then the magic hotkeys in this case are your Control-Enter, which will let me go ahead and run the script. And so I've now loaded the data, and as you can see, I went ahead and shrunk the plot since we're going to be looking at the window down below. And we can simply convert the data to a string. Now, all of us do this automatically the first time. We say, hey, just print it all out as a string. And then we get this huge mess of stuff that doesn't make a whole lot of sense. So, and you can see here they have, you can probably kind of pull it together as looking at it. But let's go ahead and just do the head. And we'll do the head of my data. There we go. And Control-Enter on that. And the head shows the first 5 rows. You'll see this in a lot of different scripts. In R, it's you type in head and then in brackets you put your data. And it comes through and lists the first 5 rows as you can see below. And it shows Arizona, Boston, Central, and it has the same columns we just looked at. So we have the fixed charge, the ROR, the cost, the load, the D demand. I'm not an expert in oil, so I'm not even sure what D demand is. Cells, I'm guessing nuclear, how much of it's supplied by nuclear, and the actual fuel cost. And then the different states that it's in or different areas. And one of the wonders of R is all these cool, easy to use tools that are so quick. So we'll do pairs. And pairs creates a nice graph. So let me go ahead and run this. Whoops. The reason it gave me an error is because I forgot to resize it. So let me bring my plot way out so we can see it. And let's run that again. And you'll see here that we have a nice graph of the different data and how it plots together, how the different points kind of come together. This is neat because if you look at this, I would look at this and say, hey, this is a great candidate for some kind of clustering. And the reason is when I look at any 2 pairs, let's go down to, say, cells and fuel cost towards the bottom right. And when you look at them where they cross over, you sort of see things how they group together, but it's a little confusing. You can't really pinpoint how they group together. You could probably look at these 2 and say, yeah, there's pretty good commonalities there. And if you look at any of the other pairs, you'll start seeing some patterns there also. And so we really want to know what are the patterns on all of them put together, not just any 2 of them, but the whole setup. Let me go ahead and shrink my this down for just a second, just a notch here. And let's create a scatter plot. Oops. And this is simply just use the term plot in brackets, and then which values do we want to plot. And if we remember when we looked at the data earlier, let me just go back this way. In this case, let's go ahead and compare just two values to see how they look. And we'll do fuel cost in cells, and it's in my data. So we got to let it know which 2 columns we're looking at next to each other. And it will open up our plot thing and then go ahead and execute that. And we can see on those close up of what we were just looking at in the pairs. And if I was eyeballing this, I would say, oh look, there's a kind of a cluster up here of 5 items, and this one is hard to tell which cluster it'd be with, but maybe it's 6 to go in the top one, and you have a middle cluster and a bottom cluster, maybe 2 different clusters. So you can sort of group them together, fuel cost and the cells, and see how they connect with each other. And again, that's only 2 different values we're looking at. So in the long run, we want to look at all of them. And then the people in the back, they sent me the script so we can go ahead and add labels. So with my data text, fuel cost cells, the labels equals city, position 4. These are numbers you can kind of play with till they look nice. And oops, again, I forgot to resize my plot. It doesn't like having it too small. And we'll run that. I mistyped something in here. Oh, I did a lowercase d and they did a capital D. There we go. So now we can go in here and do this with my data, and you can see, a little hard to see on my screen with all the different things in there, it plots the actual cities. So we can now see where all the cities are in connection with, in this case, fuel cost and cells. So you have a nice label to go with the graph. And then we can also go ahead and plot, in this case, let's do, the ROR, oops. And we'll do that also with the cells, and do my data. Remember to leave it lowercase this time. So when we plot those two, we'll come over here, and it's going to, I'm surprised it didn't give me an error. And then we'll also add in the with statement, so we put some nice labels in there. And it's going to be the same as before, except instead of doing the fuel cost cells, we want the R cells. And we'll execute that. Oops, and of course it gives me an error because I shrunk it down. So let's redo those two again. There we go. And we can see now we have the ROR with cells. And we'd probably get a slightly different clustering here if I was looking at these cities. They're probably different than what we had before. But you could probably look at this and say, these kind of go together and those kind of go together. But again, we're going to be looking at all of them instead of just one or two. And so at this point, we want to dive into the next step. We're going to start looking at a little bit of coding or scripting here. This is very important because we're going to be looking at normalization. We put that in there, normalization. And if you've done any of the other machine learning skills and setup, this should start to look very normal in your pre-processing of data. Whether you're in R or Python or any of these scripts, we really want to make sure you normalize your data so it's not biased. Remember, we're dealing with distances, and if I have, let's say the ROR is, even look at this graph here on the right, you can see where my ROR varies between 8 and 14. That's a very small variable, and our cells varies between 4,000 and 16,000. So you can imagine the distance between 4,000 and 8,000, which is the distance of 4,000, versus 8 to 10 versus 2, the cells is going to dominate. So if we do any kind of special work on this, it's going to look at cells and it's going to cluster them just by the cells alone. And then ROR might have a little tiny effect of 2 versus 4,000. We want to level the playing field. Turns out there's actually a number of ways in script to normalize. So I'm just going to put in the code that they put together in the back for me. And let's talk about it a little bit. So we have Z, we're going to assign it to my data. And it's go ahead and we're going to do a little reshaping across all rows. Or across all columns. So each of the rows is going to have a little reshaping there. And then we're going to get M, which stands for means. And we're going to apply it to my data. So again, we want to go ahead and create the most common variable in there. And then S is going to be, SD stands for standard deviation. So instead of just doing, a lot of times what they do with normalization of data is we just reshape the data everything between 0 and 1. So that if the lower end is 8, that now becomes 0, and the upper end is 14, that now becomes 1. That doesn't help if it is not a linear set of data. So with this, we're going to look for the means and the standard deviation for reshaping the data. And that way, the most common values now become the kind of like the center point. And then the standard deviation is how big the spread. So we want the standard deviation to be equal amongst all of them. And then finally, we go ahead and take Z. And with the Z, we're going to reassign it, and we're going to scale the original my data, which we reshaped, based on M and based on the standard deviation. And the 2 in here, that just means we're looking at everything in kind of a XY kind of plot. And we can quickly run these. Control Enter, Control Enter, Control Enter, Control Enter. So now we have Z, which is a scaled version of my data. And now we can go ahead and calculate the Euclidean distance. Oops, calcu. There we go. And in R, this is so easy. Once you've gotten to here, we've done all that pre-data processing. We'll call it distance. And we'll assign this to dist. So dist is the computation for getting the Euclidean distance. And we can just put z in there because we've already reformatted and scaled z to fit what we want. Let me go ahead and just hit enter on that. And I'm going to widen my left-hand side again. I'm always curious, what does this data look like? So let's just type in distance, which will print the variable down below. Oops. You have to hit Control-Enter. And this prints out a huge amount of information. As you can see, it just kind of streams down there. And let's go ahead and enlarge this. And I don't know about you, but when I look at something like this, it doesn't mean a whole lot to me, other than I see 2, 3, 4, 5, 6, and then you kind of have the top part, 6, 17, 18. So imagine this is like a huge chart, is what we're looking at. And we can go ahead and use print, distance, digits equal 3. And let's run that. Oops, I keep forgetting that it has to go through the graph on the right. And we see a slightly different output in here. Let me just open this up so we can see what we're looking at. And by cutting down the distance, you can start to see the patterns here of it's looking at the different distances. So if I go to the top, we have the distance between 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, and then 2 and 3, and so on. Obviously, the distance between itself is 0. And it doesn't repeat the data, so we don't care to see 2 versus 1 again, because we already know the distance between 1 and 2. And so we have a nice view of all the distances in the chart, and that's what we're looking at right here. And it's a little easier to read. That's why we did the print statement up here to do digits equals 3, make it a little bit smaller. We could even just do digits. Let's just do 2, see what that looks like. We might lose some data on this one if something's way off. But we have a nice setup and we can see the different distances, and that's what we were computed here between each of the points. And then the whole reason we're doing this is to get ourselves a nice dendrogram going, a nice clustering dendrogram. We'll do a couple of these looking at different things. We'll take a variable hc.l and we're going to assign it h cluster and then distance. That easy. We've already computed the distances. So the H clustering does all the work for us. And let me hit enter on there. So now we have our HCL, which is assigned the H clustering computation based on distances and apart. And then I'm going to expand my graph because we would like to go ahead and see what this looks like. And we can simply plot that and hit the Control Enter so it runs. And look at that. We have a really nice clustering dendrogram. Except when I look at it, the first thing I note, I'm going, what the heck does 3, 9, 14, 19, 1, 18 mean? So let's give it some words there. So let's do the same plot with our HCL. There we go. And let's add in labels. And this is just one of the commands in plots. So we have labels equals my data. And then under my data, we want to know the city. And we'll have it hang -1. That's just the instructions to make it pretty. So we'll run that. Oops, I accidentally ran just hang my 1. Let me try that again. There we go. Okay, so now you can see what it's done. And the hang my 1 turns it sideways. That way we can see central, which is central US and Kentucky. And we start to actually get some information off our clustering setup. And the information you start looking at is that when we put all the information together, you probably want to look at Central America and Kentucky together. Oklahoma and Texas has a lot of commonality, as does Arizona and southern U.S. And you could even group all 5 of those, Florida, Oklahoma, Texas, Arizona, and southern U.S. These regions, for some reason, share a lot of similarities. And so we want to start asking what those similarities are. But this gives us a place to look. It says, hey, these things really go together you should be grouping these together as far as your cells and what you're doing. And then one of the things you might want to do is we can do the dendrogram average. And this changes how we do the clustering. So it looks very similar like we had before. And there's our HCl. We're going to assign it. We're going to do an H cluster. We're still doing it on distance. Oops, distance. And this time we're going to set the method to average. So we can change the methodology in which it computes the values. And before, if you remember correctly, we did median. Median's a little bit different than means. We did the most common one, and then we want the average of the median. And let's go ahead and run that. And then we can plot. And here's our HCl. Oops, there we go. Here's our HCl, and I can run that plot. And you can see that it's changed a little bit. So our way it computes and groups things looks a little different than it did before. And let's go ahead and put the cities back in there and do the hang. Control copy. Let me just real quickly copy that down here, because we want the same labels. And again, you can see Nevada, Idaho, Puget. I remember we were looking at southern U.S. and Arizona, Texas and Oklahoma, Florida. So the grouping really hasn't changed too much. So we still have a very similar grouping. It's almost kind of flipped it as far as the distance based on average has. But this is something you could actually take to the shareholders and say, hey, look, these things are connected. And at which point you want to explore a little deeper as to why they're connected, because they're going to ask you, okay, how are they connected and why do we care? But that's a little bit beyond the actual scope of what we're working on today. But we are going to cover membership, what's called clustering membership on there. And let's create a member. We'll just call it member 1. Oops, there, member.1. And we're going to assign to this, we're going to do cut tree. And cut tree, it limits it. So what that means is I take my hc.l in here. Oops, there we go, .l. And so I'm taking the cluster I just built, and we want to take that cluster, and we want to limit it to just a depth of 3. So we go ahead and do that, and run that one. Oops, let me go run. There we go. So now I've created my member 1. And then, whoops, let me just move this out of the way. We're going to do an aggregate, and we're going to use Z, remember Z from above, and we're going to turn member 1 into a list, and then we're going to aggregate that together based on the mean. Let me go ahead and enter, run that. Oops, I did member L, it's actually member 1. There we go. And if we take a look at this, we now have our group 1 fixed charge and then all your different columns listed there. And most of them should come up kind of looking between 0 and 1, but you'll see a lot of variation because we're varying it based on the means. So it's the means and standard deviation, not just forcing it in between 0 and 1, which is a much better way usually to normalize your data than just doing the 0-1 setup. And finally, we can actually look at the actual values, and the same chart we just did. Oops. I made a mistake on there with my data. There we go. Okay. And again, we now have our actual data. Instead of looking at just the, if you looked up here, it's all between 0 and 1. And when we look down here, we now have some actual connections and how far distance this different data is. Again, because more of a domain issue and understanding the oil company and what these different values means. And you can look at these as being the distances between different items. So a little bit different view, and you have to really dig deep into this data. What we really want you to take away from this is the dendrogram and the charts that we did earlier. And that is the cluster output and our nice dendrogram. So this would be stage 1 in data analysis of the cells. Again, you'd have to have a lot more domain experience to find out what all the individual numbers we looked at mean and what the distance is and what's difference between Central America and Kentucky and why they're similar and why it groups all of Central Kentucky, Florida, Oklahoma, Texas, Arizona, and Southern U.S. together into one larger group. So that'd be way beyond the scope of this. But you can see how we start to explore data and we start to see things in here where things are grouped together in ways we might not have seen before. And this is a good start for understanding and giving advice for sales and marketing, maybe logistics, city development. There's all kinds of things that kind of come together in the hierarchical clustering as you begin to explore data. And we just want to point out that we get 3 clusters of regions with the highest cells, region with average cells, region with the lowest cells. Again, those are some of the things that they clustered it around, and you could actually see where things are going on or lacking. In this case, if you're the lowest cells, no one wants to be in the region of the lowest cells.
Support vector machine is a binary classifier, a supervised machine learning algorithm, and in this video we will learn what all that means. Machine learning algorithms come in 3 major flavors: supervised learning algorithms, unsupervised learning algorithms, and reinforcement learning. And today we'll cover classification under supervised learning. Supervised meaning the data set has known outcomes. If it were unsupervised, it would not have known outcomes, and we wouldn't have the categories or classes necessary for the machine to learn. But under supervised learning, we do have the known outcomes in the data set. And under supervised learning, there are 2 major types of machine learning algorithms: classification, which we'll cover today, support vector machine, and regression. Classification, you predict categories, and in regression, you generally predict values. So while we look at supervised learning, keep in mind that classification can really be considered multidimensional in the sense that sometimes you only have 2 classes, yes or no, true or false, and sometimes you have more than 2 classes. Sometimes you have, say, under risk management or risk modeling, low risk, medium risk, or high risk. And SVM is a binary classifier. It is a classifier used for those true, false, yes, no types of classification problems. And in supervised learning, features are important. If there are a lot of features, SVM may be the better classification algorithm choice as opposed to, say, logistic regression. So with supervised learning, the computer is presented with example inputs and their desired outputs, those known outcomes. And the goal is to learn a general rule that maps inputs to those outputs. For example, bug detection, or customer churn, or stock price prediction. Not the value of the stock price, but whether or not it will rise or fall. And weather prediction, sunny, not sunny, rain, no rain. The classification algorithms generally take past data that we have those known outcomes, train the model, take new data once the model is trained, ingest it into the model, and create predictions. Is it a truck or is it a car? And keep in mind that I said features are important, and the number of features, whether or not those features are applicable to your problem, is a whole different discussion. But in some sense, you know, probably intuitively, that the color of a car really isn't indicative of whether or not it's a car or a truck, but the length of the vehicle, or the number of axles, or the weight, or the amount of seating may be more applicable to the algorithm and to training the model. So what is support vector machine? Support vector machine, or SVM, is a type of classification algorithm which classifies data based on its features. And SVM will classify any new element into one of those 2 classes. So we'll give it some inputs, the algorithm will segregate and classify the data, and then create the outputs. And next, when we ingest new data, an unknown fruit variable in this example, the algorithm will correctly classify the fruit, apple versus orange. So now let's understand what an SVM is. And if you want to understand support vector machine, you really need a good example. And I know that cricket is a wonderful game. I don't know a lot about it, but I know it's very popular around the world, and we're going to use cricket as an example of SVM. So we'll classify cricket players into batsmen or bowlers using the runs to wicket ratio. So a player with more runs would be considered a batsman, and a player with more wickets would be considered a bowler. And if we could take a data set, say of people, cricket players with runs and wickets in columns next to their names, we could create a plot, a two-dimensional plot. In this example, clear separation between cricket players considered bowlers and those cricket players considered batsmen. And you don't always have a data set this clean where there is a clear segregation of data, bowlers versus batsmen. But for the sake of understanding SVM, this example does well. So before we do any separation, before we apply any high-level mathematics, let's just take a look at an unknown value, a new data coming into our data set. And that datum, we don't know what class it belongs to. That datum is a bowler or a batsman, we know that much, but we don't know, should we consider that cricket player a batsman or a bowler? And so we want to draw a decision boundary, some type of line separating the two classes, so that we can use that decision boundary to classify the new data point. Of course, we could draw lines. There's a yellow line, a green line, a blue line. There's actually not just 3 lines, but an infinite number of lines that we could draw between those two classes. So which one do we pick? And this is kind of reminiscent of simple linear regression, where we find the line of best fit. We want the line of best separation. We want a line that clearly separates those two groups as much as possible. Once we have the correct line, we would be able to classify the new data point. But in this example, you can see if we pick yellow, the new data point would be a bowler. But if we picked green or blue, the new data point would be a batsman. So we need the one that best separates the data. What line best separates the data? We'll find the best line by computing the maximum margin from equidistant support vectors. Now, support vectors in this context simply means the 2 points, one from each class, that are closest together, but that maximize the distance between them, or the margin. So the word vector here, you may think, well, he really means points, data points. Well, in 2-dimensional space, yes. And maybe even in 3-dimensional space. But once you get into higher dimensional spaces, when you get more and more features in your data set, you have to consider these as vectors. You can no longer really describe them as points, so we call them vectors. And the reason they're support vectors is because the 2 vectors that are closest together, that maximize the distance between the 2 groups, support the algorithm. So that's why we call them support vectors. So if you look at our example, there are a couple of points at the top that are pretty close to one another, and a couple of points at the bottom of that graph that are pretty close to each other. And I'm not really sure, looking at the graph, which 2 are closest, but clearly those points are the ones we need to consider. The rest of the other points are too far away from the rest of the other points. In other words, the bowler points are far to the right and the batsman data points are far to the left. So we'll look at these 4 points to begin with. Mathematically, we would calculate the distance among all of these points, and we would minimize that distance. Once we pick the support vectors, we'll draw a dividing line and then measure the distance from each support vector to the line. The best line will always have the greatest margin or distance between the support vectors. If we consider the yellow line as a decision boundary, the player with the new data point would be considered a bowler. The margins don't appear to be maximum though. So maybe we can come up with a better line. So let's take 2 other support vectors and we'll draw the decision boundary between those, and then we will calculate the margin. And notice now that the unknown data point, the new value, would be considered a batsman. We would continue doing this, and obviously a computer does it much quicker than a human being, over and over and over again until we found the correct decision boundary with the greatest margin. And in this case, if you look at the green decision boundary, the green line appears to have the maximum margin compared to the other 2. And so let's consider this the boundary of greatest margin, and now classify our unknown data value, and now clearly it belongs in the batsman's class. The green line divides the data perfectly because it has the greatest margin, or the maximum margin, between the support vectors. And now we can have confidence in our classification that the new data point is indeed a batsman. Technically, this dividing line is called a hyperplane. And the reason it's called a hyperplane will become a little bit more evident in a few minutes. Generally, in two-dimensional space, we consider those lines. But in three-dimensional space and higher dimensional spaces, they're considered planes or hyperplanes. So we always tend to refer to them as hyperplanes. And the hyperplane that has the maximum distance from the support vectors is the one we want. So, sometimes called the positive hyperplane, D plus is the shortest distance to the closest positive point, and D minus, sometimes called the negative hyperplane, is the shortest distance to the closest negative point. And the sum of D positive and D negative is called the distance margin. So if you calculate those two distances and add them up, that's the distance margin. And we always want to maximize that. If we don't maximize it, we can have a misclassification. And you can see the yellow margin is much smaller than the green margin. So this problem set is two-dimensional because the classification is only between two classes. And so we would call this a linear SVM. Now we're going to take a look at kernel SVM. And if you notice in this picture, this is a great depiction of a plane, not a line. This is three-dimensional space. So that's the plane that separates those two classes. So what if our two-dimensional data looks like this? What if there's no clear linear separation between the two classes? In machine learning parlance, we would say that these are not linearly separable. How could we get support vector machine to work on data that looks like this? Since we can't separate it into two classes using a line, what we're going to do, and clearly there's no line, I mean, convince yourself, there's no line that goes and separates those two classes. So what we would do is we would apply some type of transformation to a higher dimension. We would apply a function called a kernel function to the data set such that the data set would be transformed into a higher dimension, a dimension high enough where we could clearly separate the two groups, the two classes, in this case with a plane, much the same way you saw the picture a few slides ago where the plane was separating the two classes. Here we clearly could draw some planes between the green dots and the red dots. And of course, we could draw an infinite number of planes separating those two classes, but we would draw the one that would maximize the margin. So if we let R be the number of dimensions, then the kernel function would convert a given two-dimensional space to a three-dimensional space. And as I said, once the data is separated in 3 dimensions, we can apply SVM and separate the two groups using a two-dimensional plane. And this is analogous in the higher dimensions. And that last picture on the right-hand side would be some type of depiction of a higher dimension hyperplane. And there are more than one type of kernel function. There's Gaussian RBF kernel, sigmoid kernel, polynomial kernel, depending on the dimension and how you want to transform the data. There are more than one choice for kernel functions. So now let's go through a use case. Let's take a look at horses and mules and see if we can use SVM to classify some new data. So the problem statement is classifying horses and mules, and we're going to use height and weight as the two features. And obviously, horses and mules typically, in general, tend to weigh differently and tend to stand taller. So we'll take a data set, we'll import the data set, we'll make sure we have our libraries. The E1071 library has support vector machine algorithms built in. We'll compute the support vectors using the library. Once the data is used to train the algorithm, we'll plot the hyperplane, get a visual sense of how the data is separated. And if it's two-dimensional or three-dimensional, that's great. Remember, if it's higher dimensional, it's tough to plot those. And then we'll use the new model, the trained model, to classify new values. In general, we would have a training set, a test set, and then ingest the new data. But for our example, we're just going to use the whole data set to train the algorithm and then see how it performs. And once we see how it performs, we'll see, did we get a horse? Did we predict a horse when we had a horse? Did we predict a mule when we had a mule? So here's the R code. Of course, if you want to run this R code, you'll have to install R and then R Studio. Then you'll have to ingest the data, and then you'll have to create an indicator variable to help us with our plots. We'll install our libraries, install the package if you don't already have it installed. I do. And then call the library up into the R session that you're working. We'll create the data frame from the data that was ingested. We will then view the data frame, and of course we have to explore the data frame hoping that we don't have missing values or we don't have outliers. If we do have missing values or outliers, we'll have to either impute those values or delete those values. But in this case, let's hope we don't have any. And now for a quick demo on support vector machines. So we have a working directory where my data is stored, and I'm going to set the working directory to that data source and read the data file into R. And now I'm going to create a vector that really is just an indicator variable. It's the -1s and the 1s that indicate whether it's a mule or a horse. -1 for a mule, +1 for a horse. So I'll create that vector. And SVM, there's a great package, E1071, great library that has the support vector machine functions that we're going to use. And now I'm going to create the data frame. I'm going to take my data and I'm going to add to it the isHorse vector. And now let's just take a peek, and as you can see, there's the height, weight, and whether or not the animal was a mule or a horse. So remember, machine learning, we take a data source with known outcomes, and we apply our algorithm to that data source, in this case a data frame of heights, weights, and the indicator variable. And then we use the machine learning algorithm to learn from that data with those known results. So now let's plot the data, the height versus weight. And as you can see, the horses tend to be a lot taller and weigh a lot more than the mules. So now let's run our algorithm, our SVM model against the data. And the key here is that it's a linear model, and we've run it, and great, now we have a model. Let's look at the summary of the model. And as you can see, there's the formula that it ran and some of the information about the vectors and the classes. And there are 2 support vectors. So now let's find those 2 support vectors on our graph. And this might be a little hard to see. The orange outline around this point and this point indicate that those are the 2 vectors that will support this model, and thus we call them the support vectors. Now let's get the parameters of the hyperplane from the model, and let's plot a line that will be our hyperplane. There's our hyperplane line, and therefore to the left and below are mules, and to the right and above are horses above that line. Let's take a few new observations, and I've encoded these so that it would be illustrative. We'll take these new observations and we'll plot them, and I'm going to generate a new plot, red being the horses, black dots being the mules. I'll create an X and Y axis. I'm going to plot 3 dots, and you can see one of them, the green dot, the first one, kind of falls near the mules. The blue one kind of falls near the horses, and visually we might conclude, hey, one's a mule, one's a horse. But what about the orange dot? Well, for the orange dot, we really need our hyperplane. We really need something to clearly indicate which side it's on. And of course, by looking at this data visualization, you can tell that the orange dot is probably a mule. And let's verify those results by sticking those observations into our model and predict some outcomes. And down below, you can see that for the 3 data points, 1, 2, and 3, the first one, the green one, was -1. That's a mule. The second one was a +1. That's blue. That's the blue point, which was a horse. And the third one, which we weren't sure about, but clearly the SVM model correctly predicted that that third point would be a -1, would be a mule, and we can visually see that by the hyperplane on the graph. So that's a quick example of SVM. In general, support vector machines are binary classifiers. We don't use them for higher level classification. If you had 3 or more classes, you might want to use something like random forest. What applications? You can use it for face detection, text categorization, image classification, and bioinformatics. Really anywhere that you have the need to classify things into 2 groups.
Today we're going to cover the K nearest neighbors, a lot referred to as KNN. And KNN is really a fundamental place to start in the machine learning. It's a basis of a lot of other things, and just the logic behind it is easy to understand and incorporated in other forms of machine learning. So today, what's in it for you? Why do we need KNN? What is KNN? How do we choose the factor K? When do we use KNN? How does KNN algorithm work? And then we'll dive into my favorite part, The use case. Predict whether a person will have diabetes or not. That is a very common and popular used data set as far as testing out models and learning how to use the different models in machine learning. By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values, our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws, how sharp are their claws, and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those two characteristics. Now tell me if it is a cat or a dog. An odd question. Usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats. It must be a cat. Sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or is not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we've gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put K equals 5. We'll talk about K in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose K? How do we know K equals 5? I mean, that was the value we put in there, so we're going to talk about it. How do we choose the factor K? KNN algorithm is based on feature similarity. Choosing the right value of K is a process called parameter tuning and is important for better accuracy. So at K equals 3, we can classify, we have a question mark in the middle, as either a square or not. Is it a square or is it, in this case, a triangle? And so if we set K equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put K equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the K changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of K? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right K? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other. And in terms of KNN, the number of K, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things, and it's going to pick those things, and you might get a skewed answer. And if your K is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing K, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your k value odd. That helps it select better. So in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the k value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where you might get into a gig of data if it's really clean, doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work? Consider a data set having two variables, height in centimeters and weight in kilograms. And each point is classified as normal or underweight. So we can see right here we have two variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the two edges of a triangle. We're computing the third edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point, and we placed it there in red, and we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13. And distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer. And it's not a really complicated math, so you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the three closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal. Hence, as per KNN algorithm, the class of 57,170 should be normal. So a recap of KNN. Positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what, 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine learning packages. But for a very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. At 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly you can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up here and click on Cell. Actually, we want to go ahead and first insert a cell below, and then I'm going to go back up to the top cell, and I'm going to change the cell type to Markdown. That means this is not going to run as Python. It's a Markdown language. So if I run this first one, it comes up in nice big letters, which is kind of nice. Remind us what we're working on. And by now, you should be familiar with doing all of our imports. We're going to import the pandas as PD, import numpy as NP. Pandas is the pandas data frame, and numpy is a number array. Very powerful tools to use in here. So we have our imports. So we've brought in our pandas, our numpy, our two general Python tools. And then you can see over here we have our train test split. By now you should be familiar with splitting the data. We want to split part of it for training our thing and then training our particular model. And then we want to go ahead and test the remaining data to see how good it is. Pre-processing, a standard scalar preprocessor, so we don't have a bias of really large numbers. Remember in the data we had like number of pregnancies isn't going to get very large, where the amount of insulin they take can get up to 256. So 256 versus 6. That will skew results, so we want to go ahead and change that so that they're all uniform between -1 and 1. And then the actual tool. This is the K-neighbors classifier we're going to use. And finally, the last three are three tools to test, all about testing our model. How good is it? We just put down test on there. And we have our confusion matrix, our F1 score, and our accuracy. So we have our two general Python modules we're importing, and then we have our 6 modules specific from the sklearn setup. And then we do need to go ahead and run this, so that these are actually imported. There we go. And then move on to the next step. And so in this set, we're going to go ahead and load the database. We're going to use pandas. Remember, pandas is PD. And we'll take a look at the data in Python. We looked at it in a simple spreadsheet, but usually I like to also pull it up so that we can see what we're doing. So here's our data set equals pd.readcsv. That's a pandas command. And the diabetes folder I just put in the same folder where my IPython script is. If you put in a different folder, you'd need the full length on there. We can also do a quick length of the data set. That is a simple Python command, len for length. We might even, let's go ahead and print that. We'll go print. And if you do it on its own line, length.dataset in the Jupyter Notebook, it'll automatically print it. But when you're in most of your different setups, you want to do the print in front of there. And then we want to take a look at the actual data set. And since we're in pandas, we can simply do dataset head. And again, let's go ahead and add the print in there. If you put a bunch of these in a row, the dataset 1 head, dataset 2 head, it only prints out the last one. So I usually always like to keep the print statement in there. But because most projects only use one data frame, pandas data frame, doing it this way doesn't really matter. The other way works just fine. And you can see when we hit the run button, we have the 768 lines, which we knew, and we have our pregnancies. It's automatically given a label on the left. Remember, the head only shows the first 5 lines. So we have 0 through 4. And just a quick look at the data, you can see it matches what we looked at before. We have pregnancy, glucose, blood pressure, all the way to age, and then the outcome on the end. And we're going to do a couple things in this next step. We're going to create a list of columns where we can't have 0. There's no such thing as 0 skin thickness or 0 blood pressure, 0 glucose. Any of those you'd be dead. So not a really good factor if they have a 0 in there because they didn't have the data. And we'll take a look at that because we're going to start replacing that information with a couple of different things. And let's see what that looks like. So first we create a nice list. As you can see, we have the values we talked about: glucose, blood pressure, skin thickness. And this is a nice way when you're working with columns, is to list the columns you need to do some kind of transformation on. Very common thing to do. And then for this particular setup, we certainly could use there's some Panda tools that will do a lot of this, where we can replace the NA. But we're going to go ahead and do it as a dataset column equals dataset column.replace. This is still pandas. You can do it direct. There's also one that you look for your NAN. A lot of different options in here. But the NAN, numpy NAN is what that stands for, is doesn't exist. So the first thing we're doing here is we're replacing the 0 with a numpy none. There's no data there. That's what that says. That's what this is saying right here. So put the 0 in, and we're going to replace zeros with no data. So if it's a 0, that means the person's, well, hopefully not dead. Hopefully they just didn't get the data. The next thing we want to do is we're going to create the mean, which is the integer from the data set from the column dot mean, where we skip NAs. We can do that. That is a pandas command there, the skip NA. So we're going to figure out the mean of that data set. And then we're going to take that data set column and we're going to replace all the NP-NAN with the means. Why did we do that? And we could have actually just taken this step and gone right down here and just replaced 0 and skip anything except you could actually, there's a way to skip zeros and then just replace all the zeros. But in this case, we want to go ahead and do it this way. So you can see that we're switching this to a non-existent value. Then we're going to create the mean. Well, this is the average person. So if we don't know what it is, if they did not get the data and the data is missing, one of the tricks is you replace it with the average. What is the most common data for that? This way, you can still use the rest of those values to do your computation, and it kind of just brings that particular value or those missing values out of the equation. Let's go ahead and take this and we'll go ahead and run it. Doesn't actually do anything, so we're still preparing our data. If you wanted to see what that looks like, we don't have anything in the first few lines, so it's not going to show up, but we certainly could look at a row. Let's do that. Let's go into our data set. Let's print a data set, and let's pick, in this case, let's just do glucose. And if I run this, this is going to print all the different glucose levels going down, and we thankfully don't see anything in here that looks like missing data, at least on the ones it shows. You can see it skipped a bunch in the middle. Because that's what it does. If you have too many lines in Jupyter Notebook, it'll skip a few and go on to the next in a data set. Let me go and remove this, and we'll just zero out that. And of course, before we do any processing, before proceeding any further, we need to split the data set into our train and testing data. That way we have something to train it with and something to test it on. And you're going to notice we did a little something here with the pandas database code. There we go, my drawing tool. We've added in this right here off the data set. And what this says is that the first one in pandas, this is from the PD pandas, it's going to say within the data set, we want to look at the iLocation, and it is all rows. That's what that says. So we're going to keep all the rows, but we're only looking at column 0 to 8. Remember, column 9, here it is right up here, we printed it in here, is outcome. Well, that's not part of the training data, that's part of the answer. Yes, column 9, but it's listed as 8, number 8. So 0 to 8 is 9 columns. So 8 is the value. And when you see it in here, 0, this is actually 0 to 7. It doesn't include the last one. And then we go down here to Y, which is our answer, and we want just the last one, just column 8. And you can do it this way with this particular notation. And then if you remember, we imported the train test split. That's part of the sklearn right there. And we simply put in our X and our Y We're going to do random state equals 0. You don't have to necessarily seed it. That's a seed number. I think the default is 1 when you seed it. I'd have to look that up. And then the test size. Test size is 0.2. That simply means we're going to take 20% of the data and put it aside so that we can test it later. That's all that is. And again, we're going to run it. Not very exciting. So far we haven't had any printout other than to look at the data. But that is a lot of this is prepping this data. Once you prep it, the actual lines of code are quick and easy. And we're almost there with the actual running of our KNN. We need to go ahead and scale the data. If you remember correctly, we're fitting the data in a standard scaler, which means instead of the data being from 5 to 303 in one column, and the next column is 1 to 6, we're going to set that all so that all the data is between -1 and 1. That's what that standard scaler does. Keeps it standardized. And we only want to fit the scaler with the training set, but we want to make sure the testing set is, the X test going in is also transformed, so it's processing it the same. So here we go with our standard scaler. We're going to call it sc_x for the scaler, and we're going to import the standard scaler into this variable, and then our x train equals sc_x dot fit transform. So we're creating the scaler on the x train variable, and then our x test, we're also going to transform it. So we've trained and transformed the x train, and then the x test isn't part of that training. It isn't part of training the transformer. It just gets transformed. That's all it does. And again, we're going to go ahead and run this. And if you look at this, we've now gone through these steps, all 3 of them. We've taken care of replacing our zeros for key columns that shouldn't be 0, and we replaced that with the means of those columns. That way that they fit right in with our data models. We've come down here and we split the data, so now we have our test data and our training data, and then we've taken and we've scaled the data. So all of our data going in. Now, no, we don't train the Y part, the Y train and Y test. That never has to be trained. It's only the data going in. That's what we want to train in there. Then define the model using k-neighbors classifier and fit the train data in the model. So we do all that data prep. And you can see down here we're only going to have a couple lines of code where we're actually building our model and training it. That's one of the cool things about Python and how far we've come. It's such an exciting time to be in machine learning because there's so many automated tools. Let's see, before we do this, let's do a quick length of, and let's do Y. Let's just do length of Y. And we get 768. And if we import math, we do math dot square root. Let's do Y train. There we go. It's actually supposed to be X train. Before we do this, let's go ahead and do import math and do math square root length of Y test. And when I run that, we get 12.409. I wanted to show you where this number comes from we're about to use. 12 is an even number, so if you're ever voting on things, remember the neighbors all vote, don't want to have an even number of neighbors voting, so we want to do something odd. And let's just take one away and we'll make it 11. Let me delete this out of here. That's one of the reasons I love Jupyter Notebook, because you can flip around and do all kinds of things on the fly. So we'll go ahead and put in our classifier. We're creating our classifier now, and it's going to be the k-neighbors classifier. N neighbors equal 11. Remember we did 12 minus 1 for 11, so we have an odd number of neighbors. P equals 2, because we're looking for are they diabetic or not, and we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of measure this, but the Euclidean's the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll jump into the F1 score. And finally, accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, Y test, Y predict. So those are the 2 values we're going to put in there. And let me go ahead and run that and print it out. And the way you interpret this is you have the Y predicted, which would be your title up here. We could do, let's just do PRED. Predicted across the top, and actual going down. Actual. It's always hard to write in here, actual. That means that this column here down the middle, that's the important column. And it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like three different, if you're looking at this across three different variables instead of just two, you'd end up with the third row down here and the column going down the middle. So in the first case we have and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an sklearn and running the KNN, the K nearest neighbor on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and we can pretty much round that off and just say we have an accuracy of 80%. Tells us it is a pretty fair fit in the model.
Introducing Naive Bayes Classifier. Have you ever wondered how your mail provider implements spam filtering, or how online news channels perform news text classification, or how companies perform sentimental analysis of their audience on social media? All of this and more is done through a machine learning algorithm called Naive Bayes Classifier. We'll start with what is Naive Bayes, a basic overview of how it works. We'll get into Naive Bayes and machine learning, where it fits in with our other machine learning tools. Why do we need Naive Bayes? And understanding Naive Bayes Classifier, a much more in-depth of how the math works in the background. Finally, we'll get into the advantages of the Naive Bayes Classifier in the machine learning setup. And then we'll roll up our sleeves and do my favorite part. We'll actually do some Python coding and do some text classification using the Naive Bayes. What is Naive Bayes? Let's start with a basic introduction to the Bayes theorem, named after Thomas Bayes from the 1700s, who first coined this in the Western literature. Naive Bayes classifier works on the principle of conditional probability as given by the Bayes theorem. Before we move ahead, let us go through some of the simple concepts in the probability that we will be using. Let us consider the following example of tossing two coins. Here we have two quarters, and if we look at all the different possibilities of what they can come up as, we get that they could come up as heads, they can come up as head-tail, tail-head, and tail-tail. When doing the math on probability, we usually denote probability as a P, a capital P. So the probability of getting two heads equals 1/4. You can see on our data set we have two heads, and this occurs once out of the four possibilities. And then the probability of at least one tail occurs 3/4 of the time. You'll see on 3 of the coin tosses we have tails in them, and out of 4 that's 3/4. And then the probability of the second coin being head given the first coin is tail is 1/2, and the probability of getting two heads given the first coin is a head is 1/2. We'll demonstrate that in just a minute and show you how that math works. Now when we're doing it with two coins it's easy to see, but when you have something more complex you can see where these formulas really come in and work. So the Bayes theorem gives us the conditional probability of an event A given another event B has occurred. In this case the first coin toss will be B and the second coin toss A. This could be confusing because we've actually reversed the order of them and go from B to A instead of A to B. You'll see this a lot when you work in probabilities. The reason is we're looking for event A. We want to know what that is. So we're going to label that A since that's our focus. And then given another event B has occurred. In the Bayes theorem, as you can see on the left, the probability of A occurring given B has occurred equals the probability of B occurring given A has occurred times the probability of A over the probability of B. This simple formula can be moved around just like any algebra formula. And we could do the probability of A after a given B times probability of B equals the probability of B given A times probability of A. You can easily move that around and multiply it and divide it out. Let us apply Bayes' theorem to our example. Here we have our 2 quarters, and we'll notice that the first 2 probabilities of getting 2 heads and at least 1 tail we compute directly off the data. So you can easily see that we have one example, HH, out of 4, 1/4, and we have 3 with tails in them, giving us 3/4, or 3/4, 75%. The second condition, the second set, 3 and 4, we're going to explore a little bit more in detail. Now we stick to a simple example with 2 coins because you can easily understand the math. The probability of throwing a tail doesn't matter what comes before it, and the same with the heads. So it's still going to be 50% or 1/2. But when that probability gets more complicated, let's say you have a D6 dice or some other instance, then this formula really comes in handy. But let's stick to the simple example for now. In this sample space, let A be the event that the second coin is head and B be the event that the first coin is tails. Again, we reversed it because we want to know what the second event's going to be, so we're going to be focusing on A. And we write that out as the probability of A given B. And we know this from our formula that equals the probability of B given A times the probability of A over the probability of B. And when we plug that in, we plug in the probability of the first coin being tails given the second coin is heads, and the probability of the second coin being heads given the first coin being over the probability of the first coin being tails. When we plug that data in, and we have the probability of the first coin being tails given the second coin is heads times the probability of the second coin being heads over the probability of the first coin being tails. You can see it's a simple formula to calculate. We have 1/2 times 1/2 over 1/2, or 1/2 equals 0.5, or 1/4. So the Bayes' theorem basically calculates the conditional probability of the occurrence of an event based on prior knowledge of conditions that might be related to the event. We will explore this in detail when we take up an example of online shopping further in this tutorial. Understanding naive Bayes and machine learning. Like with any of our other machine learning tools, it's important to understand where the naive Bayes fits in the hierarchy. So under the machine learning, we have supervised learning, and there is other things like unsupervised learning. There's also a reward system. This falls under the supervised learning. And then under the supervised learning, there's classification. There's also regression, but we're going to be in the classification side. And then under classification is your naive Bayes. Let's go ahead and glance into where is naive Bayes used. Let's look at some of the use scenarios for it. As a classifier, we use it in face recognition. Is this Cindy or is it not Cindy or whoever? Or it might be used to identify parts of the face that they then feed into another part of the face recognition program. This is the eye, this is the nose, this is the mouth. Weather prediction, is it going to be rainy or sunny? Medical recognition, news prediction. It's also used in medical diagnosis. We might diagnose somebody as either as high risk or not as high risk for cancer or heart disease or other ailments. And news classification. When you look at the Google News and it says, well, is this political or is this world news? Or a lot of that's all done with the naive Bayes. Understanding naive Bayes classifier. Now, we already went through a basic understanding with the coins and the 2 heads and 2 tails and head tail, tail heads, etc. We're going to do just a quick review on that and remind you that the naive Bayes classifier is based on the Bayes theorem, which gives a conditional probability of event A given event B. And that's where the probability of A given B equals the probability of B given A times probability of A over probability of B. Remember, this is an algebraic function, so we can move these different entities around. We can multiply by the probability of B, so it goes to the left-hand side, and then we could divide by the probability of A given B, and just as easily come up with a new formula for the probability of B. To me, staring at these algebraic functions kind of gives me a slight headache. It's a lot better to see if we can actually understand how this data fits together in a table. And let's go ahead and start applying it to some actual data so you can see what that looks like. So we're going to start with the shopping demo problem statement. And remember, we're going to solve this first in table form so you can see what the math looks like, and then we're going to solve it in Python. And in here we want to predict whether the person will purchase a product. Are they going to buy or don't buy? Very important if you're running a business, you want to know how to maximize your profits, or at least maximize the purchase of the people coming into your store. And we're going to look at a specific combination of different variables. In this case, we're going to look at the day, the discount, and the free delivery. And you can see here under the day, we want to know whether it's on the weekday. You know, somebody's working, they come in after work, or maybe they don't work. Weekend, you can see the bright colors coming down there, celebrating not being in work, or holiday. And did we offer a discount that day? Yes or no? Did we offer free delivery that day? Yes or no? And from this, we want to know whether the person's going to buy based on these traits so we can maximize them and find out the best system for getting somebody to come in and purchase our goods and products from our store. Now, having a nice visual is great, but we do need to dig into the data. So let's go ahead and take a look at the data set. We have a small sample data set of 30 rows. We're showing you the first 15 of those rows for this demo. Now, the actual data file you can request. Just type in below under the comments on the YouTube video, and we'll send you some more information and send you that file. As you can see here, the file is very simple, columns and rows. We have the day, the discount, the free delivery, and did the person purchase or not. And then we have under the day whether it was a weekday, a holiday, was it the weekend. This is a pretty simple set of data, and long before computers, people used to look at this data and calculate this all by hand. So let's go ahead and walk through this and see what that looks like when we put that into tables. Also note, in today's world, we're not usually looking at 3 different variables in 30 rows. Nowadays, because we're able to collect data so much, we're usually looking at 27, 30 variables across hundreds of rows. The first thing we want to do is we're going to take this data and based on the data set containing our 3 inputs, day, discount, and free delivery, we're going to go ahead and populate that to frequency tables for each attribute. So we want to know if they had a discount, how many people buy and did not buy. Did they have a discount, yes or no? Did we have a free delivery, yes or no? On those days, how many people made a purchase, how many people didn't? And the same with the 3 days of the week. Was it a weekday, a weekend, a holiday? And did they buy, yes or no? As we dig in deeper to this table for our Bayes theorem, let the event buy be A. Now remember, when we looked at the coins, I said we really want to know what the outcome is. Did the person buy or not? And that's usually event A is what you're looking for. And the independent variables, discount, free delivery, and day, be B. So we'll call that probability of B. Now let us calculate the likelihood table for one of the variables. Let's start with day, which includes weekday, weekend, and holiday. And let us start by summing all of our rows. So we have the weekday row, and out of the weekdays there's 9 plus 2, so it's 11 weekdays. There's 8 weekend days and 11 holidays. Wow, that's a lot of holidays. And then we want to sum up the total number of days. So we're looking at a total of 30 days. Let's start pulling some information from our chart and see where that takes us. And when we fill in the chart on the right, you can see that 9 out of 24 purchases are made on the weekday, 7 out of 24 purchases on the weekend, and 8 out of 24 purchases on a holiday. And out of all the people who come in, 24 out of 30 purchase. You can also see how many people do not purchase. On the weekday, it's 2 out of 6 didn't purchase, and so on and so on. We can also look at the totals, and you'll see on the right we put together some of the formulas. The probability of making a purchase on the weekend comes out at 11 out of 30. So out of the 30 people who came into the store throughout the weekend, weekday, and holiday, 11 of those purchases were made on the weekday. And then you can also see the probability of them not making a purchase. And this is done for, doesn't matter which day of the week. So we call that probability of no buy. It would be 6 over 30 or 0.2. So there's a 20% chance that they're not going to make a purchase no matter what day of the week it is. And finally, we look at the probability of B if A. In this case, we're going to look at the probability of the weekday and not buying. 2 of the no buys were done out of the weekend out of the 6 people who did not make purchases. So when we look at that, probability of the weekday without a purchase is going to be 0.33 or 33%. Let's take a look at this at different probabilities, and based on this likelihood table, let's go ahead and calculate conditional probabilities as below. The first 3 we just did. The probability of making a purchase on the weekday is 11 out of 30, or roughly 36 or 37%, 0.367. The probability of not making a purchase at all, doesn't matter what day of the week, is roughly 0.2 or 20%. And the probability of a weekday no purchase is roughly 2 out of 6. So 2 out of 6 of our no purchases were made on the weekday. And then finally we take our P of AB. If you look, we've kept the symbols up there. We got P of probability of B, probability of A, probability of B if A. We should remember that the probability of A if B is equal to the first one times the probability of no buys over the probability of the weekday. So we could calculate it both off the table we created. We can also calculate this by the formula, and we get the 0.367 which equals, or 0.33 times 0.2 over 0.367, which equals 0.179, or roughly 17 to 18%. And that'd be the probability of no purchase done on the weekday. And this is important because we can look at this and say, as the probability of buying on the weekday is more than the probability of not buying on the weekday, we can conclude that customers will most likely buy the product on a weekday. Now, we've kept our chart simple and we're only looking at one aspect. So you should be able to look at the table and come up with the same information or the same conclusion. That should be kind of intuitive at this point. Next, we can take the same setup. We have the frequency tables of all three independent variables. Now we can construct the likelihood tables for all three of the variables we're working with. We can take our day like we did before. We have weekday, weekend, and holiday. We filled in this table. And then we can come in and also do that for the discount, yes or no. Did they buy, yes or no? And we fill in that full table. So now we have our probabilities for a discount and whether the discount leads to a purchase or not, and the probability for free delivery. Does that lead to a purchase or not? And this is where it starts getting really exciting. Let us use these three likelihood tables to calculate whether a customer will purchase a product on a specific combination of day, discount, and free delivery, or not purchase. Here, let us take a combination of these factors. Day equals holiday, discount equals yes, free delivery equals yes. Let's dig deeper into the math and actually see what this looks like. And we're going to start with looking for the probability of them not purchasing on the following combinations of days. We're actually looking for the probability of A equal no buy, no purchase. And our probability of B we're going to set equal to, is it a holiday? Did they get a discount? Yes. And was it a free delivery? Yes. Before we go further, let's look at the original equation. The probability of A if B equals the probability of B given the condition A and the probability times the probability of A over the probability of B occurring. Now this is basic algebra, so we can multiply this information together. So when you see the probability of A given B, in this case the condition is B, C, and D, or the three different variables we're looking at. And when you see the probability of B, that would be the conditions. We're actually going to multiply those three separate conditions out. Probability of, you'll see that in just a second in the formula, times the full probability of A over the full probability of B. So here we are back to this, and we're going to have let A equal no purchase, and we're looking for the probability of B on the condition A, where A sets for three different things. Remember that equals the probability of A given the condition B. And in this case, we just multiply those three different variables together. So we have the probability of the discount times the probability of free delivery times the probability is the day equal a holiday. Those are our three variables of the probability of A if B. And then that is going to be multiplied by the probability of them not making a purchase. And then we want to divide that by the total probabilities, and they're multiplied together. So we have the probability of a discount, the probability of a free delivery, and the probability of it being on a holiday. When we plug those numbers in, we see that 1 out of 6 were no purchase on a discounted day, 2 out of 6 were a no purchase on a free delivery day, and 3 out of 6 were a no purchase on a holiday. Those are our three probabilities of A if B multiplied out. And then that has to be multiplied by the probability of a no purchase. And remember, the probability of a no buy is across all the data. So that's where we get the 6 out of 30. We divide that out by the probability of each category over the total number. So we get the 20 out of 30 had a discount, 23 out of 30 had a yes for free delivery, and 11 out of 30 were on a holiday. We plug all those numbers in, we get 0.178. So in our probability math, we have a 0.178 if it's a no buy for a holiday, a discount, and a free delivery. Let's turn that around and see what that looks like if we have a purchase. I promise this is the last page of math before we dig into the Python script. So here we're calculating the probability of the purchase using the same math we did to find out if they didn't buy. Now we want to know if they did buy. And again, we're going to go by the day equals a holiday, discount equals yes, free delivery equals yes, and let A equal buy. Now right about now you might be asking, why are we doing both calculations? Why would we want to know the no buys and buys for the same data going in? Well, we're going to show you that in just a moment, but we have to have both of those pieces of information so that we can figure it out as a percentage as opposed to a probability equation. And we'll get to that normalization here in just a moment. Let's go ahead and walk through this calculation. And as you can see here, the probability of A on the condition of B being all three categories. Did we have a discount with a purchase? Did we have a free delivery with a purchase? And is a day equal to holiday? And when we plug this all into that formula and multiply it all out, we get our probability of a discount, probability of a free delivery, probability of the day being a holiday, times the overall probability of it being a purchase, divided by, again, multiplying the three variables out, the full probability of there being a discount, the full probability of being a free delivery, and the full probability of there being a day equal holiday. And that's where we get this 19 over 24 times 21 over 24 times 8 over 24 times the P of A, 24 over 30, divided by the probability of the discount, the free delivery times the day, or 20 over 30, 23 over 30 times 11 over 30, and that gives us our 0.986. So, what are we going to do with these two pieces of data we just generated? Well, let's go ahead and go over them. We have a probability of purchase equals 0.986. We have a probability of no purchase equals 0.178. So, finally, we have a conditional probabilities of purchase on this day. Let us take that, we're going to normalize it, and we're going to take these probabilities and turn them into percentages. This is simply done by taking the sum of probabilities, which equals 0.986 plus 0.178, and that equals the 1.164. If we divide each probability by the sum, we get the percentage. And so the likelihood of a purchase is 84.71%, and the likelihood of no purchase is 15.29%, given these three different variables. So if it's on a holiday, if it's with a discount and has free delivery, then there's an 84.71% chance that the customer is going to come in and make a purchase. Hooray! They purchased our stuff. We're making money. If you're owning a shop, that's is the bottom line, is you want to make some money so that you can keep your shop open and have a living. Now, I promised you that we were going to be finishing up the math here with a few pages. So we're going to move on and we're going to do two steps. The first step is I want you to understand why you want to use the naive Bayes. What are the advantages of naive Bayes? And then once we understand those advantages, we'll just look at that briefly, then we're going to dive in and do some Python coding. Advantages of naive Bayes classifier. So let's take a look at the 6 advantages of the naive Bayes classifier, and we're going to walk around this lovely wheel. It looks like an origami folded paper. The first one is very simple and easy to implement. Certainly you could walk through the tables and do this by hand. You got to be a little careful because the notations can get confusing. You have all these different probabilities, and I certainly mess those up as I put them on, is it on the top or the bottom? You got to really pay close attention to that. When you put it into Python, it's really nice because you don't have to worry about any of that. You let the Python handle that, the Python module. But understanding it, you can put it on a table and you can easily see how it works, and it's a simple algebraic function. It needs less training data, so if you have smaller amounts of data, this is a great, powerful tool for that. Handles both continuous and discrete data. It's highly scalable with number of predictors and data points. So as you can see, you can just keep multiplying different probabilities in there, and you can cover not just 3 different variables or sets. You can now expand this to even more categories. Number 5, it's fast. It can be used in real-time predictions. This is so important. This is why it's used in a lot of our predictions on online shopping carts, referrals, spam filters, is because there's no time delay as it has to go through and figure out a neural network or one of the other many setups where you're doing classification. And certainly there's a lot of other tools out there in the machine learning that can handle these, but most of them are not as fast as the naive Bayes. And then finally, it's not sensitive to irrelevant features. So it picks up on your different probabilities, and if you're short on data on one probability, you can it automatically adjust for that. Those formulas are very automatic, and so you can still get a very solid predictability even if you're missing data or you have overlapping data for 2 completely different areas. We see that a lot in doing census and studying of people and habits, where they might have one study that covers one aspect and another one that overlaps, and because the two overlap, they can then predict the unknowns for the group that they haven't done the second study on, or vice versa. So it's very powerful in that it is not sensitive to the irrelevant features, and in fact you can use it to help predict features that aren't even in there. So now we're down to my favorite part. We're going to roll up our sleeves and do some actual programming. We're going to do the use case text classification. Now, I would challenge you to go back and send us a note on the notes below underneath the video and request the data for the shopping cart. So you can plug that into Python code and do that on your own time so you can walk through it, since we walk through all the information on it. But we're going to do a Python code doing text classification, very popular for doing the naive Bayes. So we're going to use our new tool to perform a text classification of news headlines and classify news into different topics for a news website. As you can see here, we have a nice image of the Google News, and then related on the right, subgroups. I'm not sure where they actually pulled the actual data we're going to use from. It's one of the standard sets. But certainly this can be used on any of our news headlines and classification. So let's see how it can be done using the naive Bayes classifier. Now we're at my favorite part. We're actually going to write some Python script. Roll up our sleeves. And we're going to start by doing our imports. These are very basic imports, including our news group. And we'll take a quick glance at the target names. Then we're going to go ahead and start training our data set and putting it together. We'll put together a nice graph, because it's always good to have a graph to show what's going on. And once we've trained it and we've shown you a graph of what's going on, then we're going to explore how to use it and see what that looks like. Now, I'm going to open up my favorite editor, inline editor for Python. You don't have to use this. You can use whatever your editor that you like, whatever interface IDE you want. This just happens to be the Anaconda Jupyter Notebook. And I'm going to paste that first piece of code in here so we can walk through it. Let's make it a little bigger on the screen so you have a nice view of what's going on. And we're using Python 3, in this case 3.5. So this would work in any of your 3x. If you have it set up correctly, it should also work in a lot of the 2x. You just have to make sure all of the versions of the modules match your Python version. And in here, you'll notice the first line is your percentage matplot library in line. Now, 3 of these lines of code are all about plotting the graph. This one lets the notebook know, since it's an inline setup, that we want the graphs to show up on this page. Without it in a notebook like this, which is an Explorer interface, it won't show up. Now, a lot of IDEs don't require that. A lot of them, like if I'm working on one of my other setups, it just has a pop-up and the graph pops up on there. So you have that setup also. But for this, we want the matplot library inline. And then we're going to import numpy as np. That's NumberPython, which has a lot of different formulas in it that we use for both of our sklearn module. And we also use it for any of the upper math functions in Python. And it's very common to see that as np, numpy as np. The next 2 lines are all about our graphing. Remember I said 3 of these were about graphing? Well, we need our matplotlibary.pyplot as PLT, and you'll see that PLT is a very common setup, as is the SNS, and just like the NP. And we're going to import Seaborn as SNS, and we're going to do the SNS.set. Now, Seaborn sits on top of pyplot, and it just makes a really nice heat map. It's really good for heat maps. And if you're not familiar with heat maps, that just means we give it a color scale. The term comes from the brighter red it is, the hotter it is in some form of data, and you can set it to whatever you want. And we'll see that later on. So you'll see that those 3 lines of code here are just importing the graph function so we can graph it. And as a data scientist, you always want to graph your data and have some kind of visual. It's really hard just to shove numbers in front of people and they look at it and it doesn't mean anything. And then from the sklearn.datasets, we're going to import the fetch 20 news groups. Very common one for analyzing, tokenizing words and setting them up and exploring how the words work and how do you categorize different things when you're dealing with documents. And then we set our data equal to fetch 20 news groups. So our data variable will have the data in it. And we're going to go ahead and just print the target names, data.target names. And let's see what that looks like. And you'll see here we have alt atheism, comp graphics, comp os ms windows.miscellaneous. And it goes all the way down to talkpolitics.miscellaneous, talkreligion.miscellaneous. These are the categories they've already assigned to this news group. And it's called Fetch 20 because you'll see I believe there's 20 different topics in here, or 20 different categories as we scroll down. Now, we've gone through the 20 different categories, and we're going to go ahead and start defining all the categories and set up our data. So we're actually going to go ahead and get the data all set up and take a look at our data. And let's move this over to our Jupyter notebook, and let's see what this code does. First, we're going to set our categories. Now, if you noticed up here, I could have just as easily set this equal to data.target_names, because it's the same thing. But we want to kind of spell it out for you so you can see the different categories. It kind of makes it more visual so you can see what your data is looking like in the background. Once we've created the categories, we're going to open up a train set. So this training set of data is going to go into fetch 20 news groups, and it's a subset in there called train, and categories equals categories. So we're pulling out those categories that match. And then if you have a train set, you should also have the testing set. We have test equals fetch 20 news groups, subset equals test, and categories equals categories. Let's go down one size so it all fits on my screen. There we go. And just so we can really see what's going on, let's see what happens when we print out one part of that data. So it creates train, and under train it creates train.data, and we're just going to look at data piece number 5. And let's go ahead and run that and see what that looks like. And you can see when I print train.data number 5 under train, it prints out one of the articles. This is article number 5. You can go through and read it on there. And we can also go in here and change this to test, which should look identical because it's splitting the data up into different groups, train and test. And we'll see test number 5 is a different article, but it's another article in here. And maybe you're curious and you want to see just how many articles are in here. We could do length of train.data. And if we run that, you'll see that the training data has 11,314 articles. So we're not going to go through all those articles. That's a lot of articles. But we can look at one of them just so you can see what kind of information is coming out of it and what we're looking at. And we'll just look at number 5 for today. And here we have it. Rewording the Second Amendment IDs, VTT, lines 58, in article, etc. And you can scroll all the way down and see all the different parts to there. Now, we've looked at it, and that's pretty complicated when you look at one of these articles to try to figure out how do you weight this. If you look down here, we have different words, and maybe the word from. Well, from is probably in all the articles, so it's not going to have a lot of meaning as far as trying to figure out whether this article fits one of the categories or not. So trying to figure out which category it fits in based on these words is where the challenge comes in. Now that we've viewed our data, we're going to dive in and do the actual predictions. This is the actual naive Bayes. And we're going to throw another model at you, or another module at you here in just a second. We can't go into too much detail, but it deals specifically working with words and text and what they call tokenizing those words. So let's take this code and let's skip on over to our Jupyter notebook and walk through it. And here we are in our Jupyter notebook. Let's paste that in there. And I can run this code right off the bat. It's not actually going to display anything yet, but it has a lot going on in here. So at the top, we had the print module from the earlier one. I didn't know why that was in there. So we're going to start by importing our necessary packages. And from the sklearn features extraction.txt, we're going to import tf-idf vectorizer. I told you we're going to throw a module at you. We can't go too much into the math behind this or how it works. You can look it up. The notation for the math is usually tf.idf. And that's just a way of weighing the words. And it weighs the words based on how many times they're used in a document, how many times or how many documents they're used in. And it's a well-used formula. It's been around for a while. It's a little confusing to put this in here, but let's let it know that it just goes in there and weights the different words in the document for us. That way we don't have to wait. And if you put a weight on it, if you remember I was talking about that up here earlier, if these are all emails, they probably all have the word from in them. From probably has a very low weight. It has very little value in telling you what this document's about. Same with words like in article, in articles, in, cost of, un, maybe cost might, or where words like criminal, weapons, destruction, these might have a heavier weight because they describe a little bit more what the article's doing. Well, how do you figure out all those weights in the different articles? That's what this module does. That's what the tf-idf vectorizer is going to do for us. And then we're going to import our sklearn.naive Bayes, and that's our multinomial NB. Multinomial naive Bayes. Pretty easy to understand that, where that comes from. And then finally we have the sklearn pipeline import make pipeline. Now the make pipeline is just a cool piece of code because we're going to take the information we get from the tf-idf vectorizer and we're going to pump that into the multinomial in B. So a pipeline is just a way of organizing how things flow. It's used commonly. You probably already guessed what it is if you've done any businesses. They talk about the sales pipeline. If you're on a work crew or a project manager, you have your pipeline of information that's going through, or your projects and what has to be done in what order. That's all this pipeline is. We're going to take the TF-ID vectorizer and then we're going to push that into the multinomial in B. Now, we've designated that as the variable model. We have our pipeline model. And we're going to take that model, and this is just so elegant. This is done in just a couple lines of code. Model.fit. And we're going to fit the data, and first the train data, and then the train target. Now, the train data has the different articles in it. You can see the one we were just looking at. And the train.target is what category they already categorized that particular article as. And what's happening here is the train data is going into the TF-ID vectorizer. So when you have one of these articles, it goes in there, it weights all the words in there. So there's thousands of words with different weights on them. I remember once running a model on this, and I literally had 2.4 million tokens go into this. So when you're dealing like large document bases, you can have a huge number of different words. It then takes those words, gives them a weight, and then based on that weight, based on the words and the weights, and then puts that into the multinomial in B. And once we go into our naive Bayes, we want to put the train target in there. So the train data that's been mapped to the TF-ID vectorizer is now going through the multinomial in B, and then we're telling it, well, these are the answers. These are the answers to the different documents. So this document that has all these words with these different weights from the first part is going to be whatever category it comes out of. Maybe it's the talk show or the article on religion, miscellaneous. Once we fit that model, we can then take labels, and we're going to set that equal to model.predict. Most of the sklearn use the term .predict to let us know that we've now trained the model and now we want to get some answers. And we're going to put our test data in there because our test data is the stuff we held off to the side. We didn't train it on there and we don't know what's going to come up out of it, and we just want to find out how good our labels are. Do they match what they should be? Now, I've already run this through. There's no actual output to it to show. This is just setting it all up. This is just training our model, creating the labels so we can see how good it is, and then we move on to the next step to find out what happened. To do this, we're going to go ahead and create a confusion matrix and a heat map. So the confusion matrix, which is confusing just by its very name, is basically going to ask how confused is our answer. Did it get it correct, or did it miss some things in there or have some missed labels? And then we're going to put that on a heat map so we'll have some nice colors to look at to see how that plots out. Let's go ahead and take this code and see how that, take a walk through it and see what that looks like. So back to our Jupyter notebook, I'm going to put the code in there, and let's go ahead and run that code. Take it just a moment. And remember, we had the inline, that way my graph shows up on the inline here. And let's walk through the code and then we'll look at this and see what that means. So, make it a little bit bigger. There we go. No reason not to use the whole screen. Too big. So we have here, from sklearn metrics, import confusion matrix. And that's just going to generate a set of data that says the prediction was such, the actual truth was either agreed with it or is something different. And it's going to add up those numbers so we can take a look and just see how well it worked. And we're going to set a variable mat equal to confusion matrix. And we have our test target, our test data that was not part of the training. Very important in data science, we always keep our test data separate. Otherwise, it's not a valid model if we can't properly test it with new data. And this is the labels we created from that test data. These are the ones that we predict it's going to be. So we go in and we create our SN heat map. The SNS is our seaborne, which sits on top of the pie plot. So when we create a SNS.heatmap, we take our confusion matrix, and it's going to be mat.t. And do we have other variables that go into the SNS.heatmap? We're not going to go into detail what all the variables mean. The annotation equals true. That's what tells it to put the numbers here. So you have the 166, the 1, the 0001. Format D and C bar equals false have to do with the format. If you take those out, you'll see that some things disappear. And then the X tick labels and the Y tick labels, those are our target names. And you can see right here, that's the alt atheism, comp graphics, comp OS, MS Windows, .miscellaneous. And then finally, we have our plt.x label. Remember, the SNS, or the seaborn, sits on top of our matplot library, our plt. And so we want to just tell it x label equals a true is true. The labels are true, and then the y label is prediction label. So when we say a true, this is what it actually is, and the prediction is what we predicted. And let's look at this graph, because that's probably a little confusing the way I rattled through it. And what I'm going to do is I'm going to go ahead and flip back to the slides, because they have a black background they put in there that helps it shine a little bit better so you can see the graph a little bit easier. So in reading this graph, what we want to look at is how the color scheme has come out. And you'll see a line right down the middle, diagonally, from upper left to bottom right. What that is if you look at the labels, we have our predicted label on the left and our true label on the right. Those are the numbers where the prediction and the true come together. And this is what we want to see, is we want to see those lit up. That's what that heat map does. As you can see that it did a good job of finding those data. And you'll notice that there's a couple of red spots on there where it missed. You know, it's a little confused when we talk about talk religion miscellaneous versus talk politics miscellaneous, social religion Christian versus alt atheism. It mislabeled some of those. And those are very similar topics, so you could understand why it might mislabel them. But overall, it did a pretty good job. If we're going to create these models, we want to go ahead and be able to use them. So let's see what that looks like. To do this, let's go ahead and create a definition, a function to run. And we're going to call this function, let me just expand that just a notch here. There we go. I like mine in big letters. Predict categories. We want to predict the category. We're going to send it s, a string. And then we're sending it train equals train. We have our training model. And then we had our pipeline, model equals model. This way we don't have to resend these variables each time. The definition knows that because I said train equals train, and I put the equal for model. And then we're going to set the prediction equal to the model.predict s. So it's going to send whatever string we send to it. It's going to push that string through the pipeline, the model pipeline. It's going to go through and tokenize it and put it through the TF, IDF, convert that into numbers and weights for all the different documents and words, and then it'll put that through our naive Bayes. And from it, we'll go ahead and get our prediction. We're going to predict what value it is. And so we're going to return train.targetNames predict of 0. And remember that the train.targetNames, that's just categories. I could have just as easily put categories in there .predict of 0. So we're taking the prediction, which is a number, and we're converting it to an actual category. We're converting it from, I don't know what the actual numbers are, but let's say 0 equals alt atheism. So we're going to convert that 0 to the word, or 1, maybe it equals comp graphics. So we're going to convert number 1 into comp graphics. That's all that is. And then we got to go ahead and then we need to go ahead and run this. So I load that up. And then once I run that, we can start doing some predictions. I'm going to go ahead and type in predict category. And let's just do predict category Jesus Christ. And it comes back and says it's social, religion, Christian. That's pretty good. Now note, I didn't put print on this. One of the nice things about the Jupyter Notebook Editor and a lot of inline editors is if you just put the name of the variable out as returning the variable train.target_names, it'll automatically print that for you. In your own IDE, you might have to put in print. Let's see where else we can take this. And maybe you're a space science buff. So how about sending load to International Space Station? And if we run that, we get science space. Or maybe you're a automobile buff. And let's do, they were going to tell me Audi is better than BMW, but I'm going to do BMW is better than an Audi. So maybe you're a car buff. And we run that, and you'll see it says recreational. I'm assuming that's what REC stands for. Autos. So I did a pretty good job labeling that one. How about if we have something like a caption running through there? President of India. And if we run that, it comes up and says talk, politics, miscellaneous. So when we take our definition or our function and we run all these things through, kudos, we made it. We were able to correctly classify texts into different groups based on which category they belong to using the naive Bayes classifier. Now, we did throw in the pipeline, the TF IDF vectorizer. We threw in the graphs. Those are all things that you don't necessarily have to know to understand the naive Bayes setup or classifier. But they're important to know. One of the main uses for the naive Bayes is with the TF IDF tokenizer or vectorizer, where it tokenizes the word and adds labels. And we use the pipeline because you need to push all that data through, and it makes it really easy and fast. You don't have to know those to understand naive Bayes, but they certainly help for understanding the industry and data science. And we can see our categorizer, our naive Bayes classifier. We were able to predict the category religion, space, motorcycles, autos, politics, and properly classify all these different things we pushed into our prediction and our trained model.
Hello and welcome to this session on K-means clustering. I'm Mohan Kumar from Simplilearn. So what is K-means clustering? K-means clustering is an unsupervised learning algorithm. In this case, you don't have labeled data, unlike in supervised learning. So you have a set of data and you want to group them. And as the name suggests, you want to put them into clusters, which means objects that are similar in nature, similar in characteristics, need to be put together. So that's what K-means clustering is all about. The term K is basically a number. So we need to tell the system how many clusters we need to perform. So if K is equal to 2, there will be 2 clusters. If K is equal to 3, it's 3 clusters, and so on and so forth. That's what the K stands for. And of course, there is a way of finding out what is the best or optimum value of K for a given data. We will look at that. So that is K-means clustering. So let's take an example. K-means clustering is used in many scenarios, but let's take an example of cricket, the game of cricket. Let's say you received data of a lot of players from maybe all over the country or all over the world, and this data has information about the runs scored by the people or by the player and the wickets taken by the player. And based on this information, we need to cluster this data into 2 clusters, batsmen and bowlers. So this is an interesting example. Let's see how we can perform this. So we have the data which consists of primarily 2 characteristics, which is the runs and the wickets. So the bowlers basically take wickets and the batsmen score runs. There will be, of course, a few bowlers who can score some runs, and similarly there will be some batsmen who would have taken a few wickets. But with this information, we want to cluster those players into batsmen and bowlers. So how does this work? Let's say this is how the data is. So there is information on the y-axis about the runs scored, and on the x-axis about the wickets taken by the players. So if we do a quick plot, this is how it would look. And when we do the clustering, we need to have the clusters like shown in the third diagram out here. So we need to have a cluster which consists of people who have scored high runs, which is basically the batsmen, and then we need a cluster with people who have taken a lot of wickets, which is typically the bowlers. There may be a certain amount of overlap, but we will not talk about it right now. So with K-means clustering, we will have here, that means K is equal to 2, and we will have 2 clusters, which is batsmen and bowlers. So how does this work? The way it works is, the first step in K-means clustering is the allocation of 2 centroids randomly. So 2 points are assigned as so-called centroids. So in this case, we want 2 clusters, which means K is equal to 2. So 2 points have been randomly assigned as centroids. Keep in mind, these points can be anywhere. They are random points. They are not really the centroids. Centroid means it's a central point of a given data set, but in this case, when it starts off, it's not really the centroid. Okay, so these points, though in our presentation here we have shown them 1 point closer to these data points and another closer to these data points, they can be assigned randomly anywhere. Okay, so that's the first step. The next step is to determine the distance of each of the data points from each of the randomly assigned centroids. So for example, we take this point and find the distance from this centroid, and the distance from this centroid. This point is taken and the distance is found from this centroid and this centroid, and so on and so forth. So for every point, the distance is measured from both the centroids, and then whichever distance is less, that point is assigned to that centroid. So for example, in this case, visually it is very obvious that all these data points are assigned to this centroid and all these data points are assigned to this centroid. And that's what is represented here in blue color and in this yellow color. The next step is to actually determine the central point or the actual centroid for these two clusters. So we have this one initial cluster, this one initial cluster, but as you can see, these points are not really the centroid. Centroid means it should be the central position of this data set, central position of this data set. So that is what needs to be determined as the next step. So the central point or the actual centroid is determined and the original randomly allocated centroid is repositioned to the actual centroid of these new clusters. And this process is actually repeated. Now what might happen is some of these points may get reallocated. In our example, that is not happening probably, but it may so happen that the distance is found between each of these data points once again with these centroids. And if it is required, some points may be reallocated. We will see that in a later example, but for now we will keep it simple. So this process is continued till the centroid repositioning stops, and that is our final cluster. So this is so after iteration, we come to this position, this situation where the centroid doesn't need any more repositioning, and that means our algorithm has converged. Convergence has occurred, and we have the cluster, two clusters, we have the clusters with a centroid. So this process is repeated. The process of calculating the distance and repositioning the centroid is repeated till the repositioning stops, which means that the algorithm has converged and we have the final cluster with the data points and the centroids. So this is what you're going to learn from this session. We will talk about the types of clustering, what is k-means clustering, application of k-means clustering. K-means clustering is done using distance measure, so we will talk about the common distance measures, and then we will talk about how k-means clustering works and go into the details of k-means clustering algorithm, and then we will end with a demo and a use case for k-means clustering. So let's begin. First of all, what are the types of clustering? There are primarily two categories of clustering: hierarchical clustering and then partitional clustering. And each of these categories are further subdivided into agglomerative and divisive clustering and k-means and fuzzy c-means clustering. Let's take a quick look at what each of these types of clustering are. In hierarchical clustering, the clusters have a tree-like structure, and hierarchical clustering is further divided into agglomerative and divisive. Agglomerative clustering is a bottom-up approach. We begin with each element as a separate cluster and merge them into successively larger clusters. So for example, we have A, B, C, D, E, F. We start by combining B and C, form one cluster, D, E, and E, form one more. Then we combine D, E, and F, one more bigger cluster, and then add B, C to that, and then finally A to it. Compared to that, divisive clustering or divisive clustering is a top-down approach. We begin with the whole set and proceed to divide it into successively smaller clusters. So we have A, B, C, D, E, F. We first take that as a single cluster and then break it down into A, B, C, D, E, and F. Then we have partitional clustering split into two subtypes, k-means clustering and fuzzy c-means. In k-means clustering, the objects are divided into the number of clusters mentioned by the number k. That's where the k comes from. So if we say k is equal to 2, the objects are divided into two clusters, C1 and C2. And the way it is done is the features or characteristics are compared and all objects having similar characteristics are clubbed together. So that's how k-means clustering is done. We will see it in more detail as we move forward. And fuzzy c-means is very similar to k-means in the sense that it clubs objects that have similar characteristics together, but while in k-means clustering two objects cannot belong to, or any object, a single object cannot belong to two different clusters, in C-means objects can belong to more than one cluster. So that is the primary difference between K-means and fuzzy C-means. So what are some of the applications of K-means clustering? K-means clustering is used in a variety of examples or variety of business cases in real life, starting from academic performance, diagnostic systems, search engines, and wireless sensor networks, and many more. So let us take a little deeper look at each of these examples. Academic performance. So based on the scores of the students are categorized into A, B, C, and so on. Clustering forms a backbone of search engines. When a search is performed, the search results need to be grouped together. The search engines very often use clustering to do this. And similarly, in case of wireless sensor networks, the clustering algorithm plays the role of finding the cluster heads, which collects all the data in its respective cluster. So clustering, especially K-means clustering, uses distance measure. So let's take a look at what is distance measure. So while these are the different types of clustering, in this video we will focus on K-means clustering. So distance measure tells how similar some objects are. So the similarity is measured using what is known as distance measure. And what are the various types of distance measures? There is Euclidean distance, there is Manhattan distance, then we have squared Euclidean distance measure and cosine distance measure. These are some of the distance measures supported by K-means clustering. Let's take a look at each of these. What is Euclidean distance measure? This is nothing but the distance between 2 points. So we have learnt in high school how to find the distance between 2 points. This is a little sophisticated formula for that, but we know a simpler one is square root of y2 minus y1 whole square plus x2 minus x1 whole square. So this is an extension of that formula. So that is the Euclidean distance between 2 points. What is the squared Euclidean distance measure? It's nothing but the square of the Euclidean distance, as the name suggests. So instead of taking the square root, we leave the square as it is. And then we have Manhattan distance measure. In case of Manhattan distance, it is the sum of the distances across the x-axis and the y-axis. And note that we are taking the absolute value so that the negative values don't come into play. So that is the Manhattan distance measure. Then we have cosine distance measure. In this case, we take the angle between the two vectors formed by joining the points from the origin. So that is the cosine distance measure. Okay, so that was a quick overview about the various distance measures that are supported by K-means. Now let's go and check how exactly K-means clustering works. Okay, so this is how K-means clustering works. This is like a flowchart of the whole process. There is a starting point, and then we specify the number of clusters that we want. Now there are a couple of ways of doing this. We can do by trial and error. So we specify a certain number, maybe k is equal to 3 or 4 or 5 to start with, and then as we progress we keep changing until we get the best clusters. Or there is a technique called elbow technique whereby we can determine the value of k. What should be the best value of k? How many clusters should be formed? So once we have the value of k, we specify that, and then the system will assign that many centroids. So it picks randomly, that to start with, randomly that many points that are considered to be the centroids of these clusters. And then it measures the distance of each of the data points from these centroids and assigns those points to the corresponding centroid from which the distance is minimum. So each data point will be assigned to the centroid which is closest to it. And thereby we have k number of initial clusters. However, this is not the final clusters. The next step it does is, for the new groups, for the clusters that have been formed, it calculates the mean position, thereby calculates the new centroid position. The position of the centroid moves compared to the randomly allocated one. So it's an iterative process. Once again, the distance of each point is measured from this new centroid point, and if required, the data points are reallocated to the new centroids, and the mean position or the new centroid is calculated once again. If the centroid moves, then the iteration continues, which means the convergence has not happened. The clustering has not converged. So as long as there is a movement of the centroid, this iteration keeps happening. But once the centroid stops moving, which means that the cluster has converged or the clustering process has converged, that will be the end result. So now we have the final position of the centroid, and the data points are allocated accordingly to the closest centroid. I know it's a little difficult to understand from this simple flowchart, so let's do a little bit of visualization and see if we can explain it better. Let's take an example. If we have a data set for a grocery shop. So let's say we have a data set for a grocery shop, and now we want to find out how many clusters this has to be spread across. So how do we find the optimum number of clusters? There is a technique called the elbow method. So when these clusters are formed, there is a parameter called within sum of squares, and the lower this value is, the better the cluster is. That means all these points are very close to each other. So we use this within sum of squares as a measure to find the optimum number of clusters that can be formed for a given data set. So we create clusters, or we let the system create clusters of a variety of numbers, maybe of 10 clusters, and for each value of k, the within SS is measured, and the value of k which has the least amount of within SS or WSS, that is taken as the optimum value of k. So this is the diagrammatic representation. So we have on the y-axis the within sum of squares or WSS, and on the x-axis we have the number of clusters. So as you can imagine, if you have k is equal to 1, which means all the data points are in a single cluster, the within SS value will be very high because they are probably scattered all over. The moment you split it into 2, there will be a drastic fall in the within SS value. And that's what is represented here. But then as the value of k increases, the rate of decrease will not be so high. It will continue to decrease, but probably the rate of decrease will not be high. So that gives us an idea. So from here, we get an idea, for example, the optimum value of k should be either 2 or 3 or at the most 4. But beyond that, increasing the number of clusters is not dramatically changing the value in WSS, because that pretty much gets stabilized. Okay, now that we have got the value of k, and let's assume that these are our delivery points, the next step is basically to assign two centroids randomly. So let's say C1 and C2 are the centroids assigned randomly. Now the distance of each location from the centroid is measured, and each point is assigned to the centroid which is closest to it. So for example, these points are very obvious that these are closest to C1, whereas this point is far away from C2. So these points will be assigned, which are close to C1 will be assigned to C1, and these points or locations which are close to C2 will be assigned to C2. And then, so this is how the initial grouping is done. This is part of C1 and this is part of C2. Then the next step is to calculate the actual centroid of this data, because remember, C1 and C2 are not the centroids. They've been randomly assigned points, and only thing that has been done was the data points which are closest to them have been assigned to them. But now in this step, the actual centroid will be calculated, which may be for each of these data sets somewhere in the middle. So that's like the mean point that will be calculated. And the centroid will actually be positioned or repositioned there. Same with C2. So the new centroid for this group is C2 in this new position, and C1 is in this new position. Once again, the distance of each of the data points is calculated from these centroids. Now remember, it's not necessary that the distance still remains or each of these data points still remain in the same group. By recalculating the distance, it may be possible that some points get reallocated, like so. You see this? So this point earlier was closer to C2 because C2 was here, but after recalculating, repositioning, it is observed that this is closer to C1 than C2. So this is the new grouping. So some points will be reassigned. And again, the centroid will be calculated, and if the centroid doesn't change, so that is a repetitive process, iterative process. And if the centroid doesn't change, once the centroid stops changing, that means the algorithm has converged. And this is our final cluster, with this as the centroid, C1 and C2 as the centroids, these data points as a part of each cluster. So I hope this helps in understanding the whole process, iterative process of k-means clustering. So let's take a look at the k-means clustering algorithm. Let's say we have x1, x2, x3, n number of points as our inputs, and we want to split this into k clusters, or we want to create k clusters. So the first step is to randomly pick k points and call them centroids. They are not real centroids because centroid is supposed to be a center point, but they are just called centroids. And we calculate the distance of each and every input point from each of the centroids. So the distance of x1 from C1, from C2, C3, each of the distances we calculate. And then find out which distance is the lowest and assign x1 to that particular random centroid. Repeat that process for x2. Calculate its distance from each of the centroids C1, C2, C3 up to Ck, and find which is the lowest distance and assign x2 to that particular centroid. Same with x3 and so on. So that is the first round of assignment that is done. Now we have k groups because we have assigned the value of k. So there are k centroids, and so there are k groups. All these inputs have been split into k groups. However, remember, we pick the centroids randomly, so they are not real centroids. So now what we have to do, we have to calculate the actual centroids for each of these groups, which is like the mean position, which means that the position of the randomly selected centroids will now change, and they will be the mean positions of these newly formed k groups. And once that is done, we once again repeat this process of calculating the distance, right? So this is what we are doing as a part of step 4. We repeat step 2 and 3. So we again calculate the distance of x1 from the centroid C1, C2, C3, and then see which is the lowest value and assign x1 to that. Calculate the distance of x2 from C1, C2, C3 or whatever up to Ck, and find whichever is the lowest distance and assign x2 to that centroid, and so on. In this process, there may be some reassignment. x1 was probably assigned to cluster C2, and after doing this calculation, maybe now x1 is assigned to C1. So that kind of reallocation may happen. So we repeat the steps 2 and 3 till the position of the centroids don't change or stop changing, and that's when we have convergence. So let's take a detailed look at each of these steps. So we randomly pick k cluster centers. We call them centroids because they are not really the centroids. So let us name them C1, C2 up to Ck. And then step 2, we assign each data point to the closest center. So what we do, we calculate the distance of each x value from each c value. So the distance between x1, c1, distance between x1, c2, x1, c3, and then we find which is the lowest value, right? That's the minimum value we find, and assign x1 to that particular centroid. Then we go next to x2, find the distance of x2 from c1, x2 from c2, x2 from c3, and so on up to ck, and then assign it to the point or to the centroid which has the lowest value, and so on. So that is step number 2. In step number 3, we now find the actual centroid for each group. So what has happened? As a part of step number 2, we now have all the points, all the data points grouped into k groups, because we wanted to create k clusters, right? So we have k groups. Each one may be having a certain number of input values. They need not be equally distributed, by the way. Based on the distance, we will have k groups. But remember, the initial values of the C1, C2 were not really the centroids of these groups, right? We assigned them randomly. So now in step 3, we actually calculate the centroid of each group, which means the original point which we thought was the centroid will shift to the new position, which is the actual centroid for each of these groups. Okay. And we again calculate the distance. So we go back to step 2, which is what? We calculate again the distance of each of these points from the newly positioned centroids. And if required, we reassign these points to the new centroids. So as I said earlier, there may be a reallocation. So we now have a new set or a new group. We still have k groups, but the number of items and the actual assignment may be different from what was in step 2 here. Okay, so that might change. Then we perform step 3 once again to find the new centroid of this new group. So we have again a new set of clusters, new centroids, and new assignments. We repeat this step 2 again. Once again we find, and then it is possible that after iterating through 3 or 4 or 5 times, the centroid will stop moving, in the sense that when you calculate the new value of the centroid, that will be same as the original value, or there will be very marginal change. So that is when we say convergence has occurred, and that is our final cluster. That's the formation of the final cluster. Alright, so let's see a couple of demos of k-means clustering. We will actually see some live demos in Python Notebook, using Python Notebook. But before that, let's find out what's the problem that we are trying to solve. The problem statement is, let's say Walmart wants to open a chain of stores across the state of Florida, and it wants to find the optimal store locations. Now the issue here is, if they open too many stores close to each other, obviously they will not make profit. But if the stores are too far apart, then they will not have enough sales. So how do they optimize this? Now, for an organization like Walmart, which is an e-commerce giant, they already have the addresses of their customers in their database. So they can actually use this information or this data and use k-means clustering to find the optimal location. Now, before we go into the Python Notebook and show you the live code, I wanted to take you through very quickly a summary of the code in the slides, and then we will go into the Python Notebook. So in this block, we are basically importing all the required libraries like NumPy, Matplotlib, and so on. And we are loading the data that is available in the form of, let's say, the addresses. For simplicity's sake, we will just take them as some data points. Then the next thing we do is quickly do a scatter plot to see how they are related to each other with respect to each other. So in the scatter plot, we see that there are a few distinct groups already being formed. So you can actually get an idea about how the cluster would look and how many clusters, what is the optimal number of clusters. And then starts the actual k-means clustering process. So we will assign each of these points to the centroids and then check whether they are the optimal distance, which is the shortest distance, and assign each of the points, data points, to the centroids, and then go through this iterative process till the whole process converges. And finally, we get an output like this. So we have 4 distinct clusters, and which is if we can say that this is how the population is probably distributed across Florida state, and the centroids are like the location where the store should be, the optimum location where the store should be. So that's the way we determine the best locations for the store, and that's how we can help Walmart find the best locations for their stores in Florida. So now let's take this into Python notebook. Let's see how this looks when we are running the code live. Alright, so this is the code for k-means clustering in Jupyter Notebook. We have a few examples here which we will demonstrate how k-means clustering is used, and even there is a small implementation of k-means clustering as well. Okay, so let's get started. Okay, so this block is basically importing the various libraries that are required, like matplotlib and numpy and so on and so forth, which would be used as a part of the code. Then we are going and creating blobs which are similar to clusters. Now this is a very neat feature which is available in scikit-learn. Make blobs is a nice feature which creates clusters of data sets. So that's a wonderful functionality that is readily available for us to create some test data kind of thing. Okay, so that's exactly what we are doing here. We are using make blobs, and we can specify how many clusters we want. So centers we are mentioning here. So it will go ahead, and so we just mentioned 4. So it will go ahead and create some test data for us. And this is how it looks. As you can see visually also, we can figure out that there are 4 distinct classes or clusters in this data set, and that is what make blobs actually provides. Now from here onwards, we will basically run the standard k-means functionality that is readily available. So we really don't have to implement k-means itself. The k-means functionality or the function is readily available. You just need to feed the data and it will create the clusters. So this is the code for that. We import k-means, and then we create an instance of k-means, and we specify the value of k. This n underscore clusters is the value of k. Remember, k-means, in k-means, k is basically the number of clusters that you want to create, and it is a integer value. So this is where we are specifying that. So we have k is equal to 4, and so that instance is created. We take that instance, and as with any other machine learning functionality, fit is what we use. The function, or the method rather, fit is what we use to train the model. Here there is no real training kind of thing, but that's the call. Okay, so we are calling fit, and what we are doing here, we are just passing the data. So x has these values, the data that has been created, right? So that is what we are passing here. And this will go ahead and create the clusters, and then we are using, after doing fit, we run the predict, which basically assigns for each of these observations which cluster it belongs to. All right, so it will name the clusters. Maybe this is cluster 1, this is 2, 3, and so on, or I will actually start from 0. Cluster 0, 1, 2, and 3 maybe, and then for each of the observations, it will assign based on which cluster it belongs to, it will assign a value. So that is stored in y underscore k-means. When we call predict, that is what it does. And we can take a quick look at these y underscore k-means, or the cluster numbers that have been assigned for each observation. So this is the cluster number assigned for observation 1, maybe this is for observation 2, observation 3, and so on. So we have how many? About, I think, 300 samples, right? So all the 300 samples, there are 300 values here. Each of them, the cluster number is given, and the cluster number goes from 0 to 3. So there are 4 clusters, so the numbers go from 0, 1, 2, 3. So that's what is seen here. Okay, now, so this was a quick example of generating some dummy data and then clustering that. Okay, and this can be applied if you have proper data. You can just load it up into X, for example, here, and then run the k-means. So this is the central part of the k-means clustering program example. So you basically create an instance and you mention how many clusters you want by specifying this parameter n underscore clusters, and that is also the value of k, and then pass the data to get the values. Now, the next section of this code is the implementation of a k-means. Now, this is kind of a rough implementation of the k-means algorithm. So we will just walk you through. I will walk you through the code at each step what it is doing, and then we will see a couple of more examples of how k-means clustering can be used in maybe some real life examples, real life use cases. All right. So in this case here, what we are doing is basically implementing the k-means clustering. And there is a function or a library calculates for a given two pairs of points. It will calculate the distance between them and see which one is the closest and so on. So this is pretty much like what k-means does, right? So it calculates the distance of each point or each data set from predefined centroid, and then based on whichever is the lowest, this particular data point is assigned to that centroid. So that is basically available as a standard function, and we will be using that here. So as explained in the slides, the first step that is done in case of k-means clustering is to randomly assign some centroids. So as a first step, we randomly allocate a couple of centroids, which we are calling as centers. And then we put this in a loop and we take it through an iterative process. For each of the data points, we first find out using this function pairwise distance argument. For each of the points, we find out which center or which randomly selected centroid is the closest. And accordingly, we assign that data or the data point to that particular centroid or cluster. And once that is done for all the data points, we calculate the new centroid by finding out the mean position with the center position, right? So we calculate the new centroid. And then we check if the new centroid is the coordinates or the position is the same as the previous centroid. The positions we will compare. And if it is the same, that means the process has converged. So remember, we do this process till the centroids or the centroid doesn't move anymore, right? So the centroid gets relocated each time this reallocation is done. So the moment it doesn't change anymore, the position of the centroid doesn't change anymore, we know that convergence has occurred. So till then, so you see here, this is like an infinite loop. While true is an infinite loop. It only breaks when the centers are the same. The new center and the old center positions are the same. And once that is done, we return the centers and the labels. Now, of course, as explained, this is not a very sophisticated and advanced implementation, very basic implementation, because one of the flaws in this is that sometimes what happens is the centroid, the position will keep moving, but the change will be very minor. So in that case, also that is actually convergence, right? So for example, the change is 0.0001. We can consider that as convergence. Otherwise, what will happen is this will either take forever or it will be never ending. So that's a small flaw here. So that is something, additional checks may have to be added here. But again, as mentioned, this is not the most sophisticated implementation. This is like a kind of a rough implementation of the k-means clustering. Okay, so if we execute this code, this is what we get as the output. So this is the definition of this particular function, and then we call that find underscore clusters, and we pass our data x and the number of clusters, which is 4. And if we run that and plot it, this is the output that we get. So this is, of course, each cluster is represented by a different color. So we have a cluster in green color, yellow color, and so on and so forth. And these big points here, these are the centroids. This is the final position of the centroids. And as you can see visually also, this appears like a kind of a center of all these points here, right? Similarly, this is like the center of all these points here, and so on. So this is the example, or this is an example of an implementation of k-means clustering. And next we will move on to see a couple of examples of how k-means clustering is used in maybe some real life scenarios or use cases. In the next example or demo, we are going to see how we can use k-means clustering to perform color compression. We will take a couple of images, so there will be 2 examples, and we will try to use k-means clustering to compress the colors. This is a common situation in image processing when you have an image with millions of colors, but then you cannot render it on some devices which may not have enough memory. So that is the scenario where something like this can be used. So before again we go into the Python notebook, let's take a look at quickly the code. As usual, we import the libraries and then we import the image, and then we will flatten it. So the reshaping is basically we have the image information is stored in the form of pixels, and if the image is like, for example, 427 by 640 and it has 3 colors, so that's the overall dimension of the initial image. We just reshape it and then feed this to our algorithm, and this will then create clusters of only 16 clusters. So this colors, there are millions of colors, and now we need to bring it down to 16 colors. So we use k is equal to 16, and this is how, when we visualize, this is how it looks. These are all about 16 million possible colors. The input color space has 16 million possible colors, and we just compress it to 16 colors. So this is how it would look when we compress it to 16 colors, and this is how the original image looks, and after compression to 16 colors, this is how the new image looks. As you can see, there is not a lot of information that has been lost, though the image quality is definitely reduced a little bit. So this is an example which we are going to now see in Python notebook. Let's go into the Python notebook. And once again, as always, we will import some libraries and load this image called flower.jpg. Okay, so we'll load that, and this is how it looks. This is the original image, which has, I think, 16 million colors, and this is the shape of this image, which is basically what is the shape is nothing but the overall size, right? So this is 427 pixel by 640 pixel, and then there are 3 layers, which is this 3 basically is for RGB, which is red, green, blue. So color image will have that, right? So that is the shape of this. Now what we need to do is data. Let's take a look at how data is looking. So let me just create a new cell and show you what is in data. Basically, we have captured this information. So data is what, let me just show you here. All right, so let's take a look at China. What are the values in China? And if we see here, this is how the data is stored. This is nothing but the pixel values. Okay, so this is like a matrix, and each one has about for this 427 by 640 pixels. All right, so this is how it looks. Now the issue here is these values are large, the numbers are large, so we need to normalize them to between 0 and 1. Right, so that's why we will basically create one more variable, which is data, which will contain the values between 0 and 1, and the way to do that is divide by 255. So we divide China by 255 and we get the new values in data. So let's just run this piece of code, and this is the shape. So we now have also, what we have done is we changed using reshape, we converted into the 3-dimensional into a 2-dimensional data set. And let us also take a look at how, let me just insert probably a cell here and take a look at how data is looking. All right, so this is how data is looking, and now you see this is the values are between 0 and 1. Right, so if you earlier noticed, in case of China, the values were large numbers. Now everything is between 0 and 1. This is one of the things we need to do. All right, so after that, the next thing that we need to do is to visualize this, and we can take random set of maybe 10,000 points and plot it and check and see how this looks. So let us just plot this, And so this is how the original, the pixel distribution is. These are two plots. One is red against green and another is red against blue. And this is the original distribution of the color. So then what we will do is we will use k-means clustering to create just 16 clusters for the various colors and then apply that to the image. Now, what will happen is, since the data is large because there are millions of colors, using regular k-means may be a little time consuming. So there is another version of k-means which is called mini batch k-means. So we will use that, which processes in the overall concept remains the same, but this basically processes it in smaller batches. That's the only thing. Okay, so the results will pretty much be the same. So let's go ahead and execute this piece of code and also visualize this so that we can see that there are this is how the 16 colors would look. So this is red against green and this is red against blue. There is quite a bit of similarity between this original color schema and the new one, right? So it doesn't look very completely different or anything like that. Now we apply the newly created colors to the image, and we can take a look how this is looking now. We can compare both the images. So this is our original image and this is our new image. So as you can see, there is not a lot of information that has been lost. It pretty much looks like the original image. Yes, we can see that, for example, here there is a little bit, it appears a little dullish compared to this one, right? Because we kind of took off some of the finer details of the color, but overall, the high-level information has been maintained. At the same time, the main advantage is that now this is an image which can be rendered on a device which may not be that very sophisticated. Now let's take one more example with a different image. In the second example, we will take an image of the summer palace in China, and we repeat the same process. This is a high definition color image with millions of colors and also three-dimensional. Now we will reduce that to 16 colors using k-means clustering, and we do the same process like before. We reshape it and then we cluster the colors to 16, and then we render the image once again, and we will see that the quality of the image slightly deteriorates. As you can see here, this has much finer details in this which are probably missing here, but then that's the compromise because there are some devices which may not be able to handle this kind of high density images. So let's run this code in Python notebook. Alright, so let's apply the same technique for another picture which is even more intricate and has probably much complicated color schema. So this is the image. Now once again, we can take a look at the shape, which is 427 by 640 by 3. And this is the new data would look somewhat like this compared to the flower image. So we have some new values here, and we will also bring this. As you can see, the numbers are much big, so we will much bigger. So we will now have to scale them down to values between 0 and 1, and that is done by dividing by 255. So let's go ahead and do that and reshape it. Okay, so we get a two-dimensional matrix, and we will then, as a next step, we will go ahead and visualize this, how it looks, the 16 colors, and this is basically how it would look, 16 million colors. And now we can create the clusters out of this. The 16 k-means clusters we will create. So this is how the distribution of the pixels would look with 16 colors, and then we go ahead and apply this and visualize how it is looking for with the new just the 16 colors. So once again, as you can see, this looks much richer in color, but at the same time, and this probably doesn't have, as we can see, it doesn't look as rich as this one, but nevertheless the information is not lost, the shape and all that stuff. And this can be also rendered on a slightly a device which is probably not that sophisticated. Okay, so that's pretty much it. So we have seen two examples of how color compression can be done using k-means clustering. And we have also seen in the previous examples of how to implement k-means, the code to roughly how to implement k-means clustering. And we use some sample data using blob to just execute the k-means clustering. In this video, we are going to talk about what time series forecasting is. And this is a two-part series. And in this first video, we will explain what is time series analysis, and in the second part, we will actually demonstrate it in RStudio. So this is what we're going to cover in this video. First of all, why time series? And then we'll talk about what exactly is time series data. And then what are the components of a time series data, like for example, the trend, seasonality, and so on. And then we will explain what each of these components are. We'll also talk about when we should not use time series analysis, and we will then explain what is stationary data in terms of time series, what is the significance of stationary data, and typically time series data is not stationary, so how to make time series data stationary. And then we will take you through an example of a car sales data, and we will show you how to solve the time series or how to perform the time series analysis manually without using a tool. And then we will do in the second part, we will actually use R, and we will do the same thing once again in R. Okay, so without any further delay, let's get started. And so why exactly do we need to do time series analysis? Typically, we would like to predict something in the future. And it could be stock prices, it could be the sales, or anything that needs to be predicted into the future. That is when we use time series analysis. So it is, as the name suggests, it is forecasting. And typically when we say predict, it need not be into the future. In machine learning and data analysis, when we talk about predicting, we are not necessarily talking about the future. But in time series analysis, we typically predict the future. So we have some past data and we want to predict the future. That is when we perform time series analysis. So what are some of the examples? It could be daily stock price, the shares as we talk about, or it could be the interest rates, weekly interest rates, or sales figures of a company. So these are some of the examples where we use time series data. We have historical data, which is dependent on time. And then based on that, we create a model to predict the future. So what exactly is time series? So time series data has time as one of the components, as the name suggests. So in this example, let's say this is the stock price data, and one of the components, so there are two columns here. Column B is price, and column A is basically the time information. In this case, the time is a day. So that primarily the closing price of a particular stock has been recorded on a daily basis. So this is the time series data, and the time interval is obviously a day. Time series or time intervals can be daily, weekly, hourly, or even sometimes there is something like a sensor data. It could be every few milliseconds or microseconds as well. So the size of the time intervals can vary, but they are fixed. So if I'm saying that it is daily data, then the interval is fixed as daily. If I'm saying this data is an hourly data, then it is the data is captured every hour, and so on. So the time intervals are fixed. The interval itself you can decide based on what kind of data we are capturing. So this is a graphical representation. The previous one here we saw the tabular representation, and this is how to plot the data. So on the y-axis is, let's say, the price or the stock price, and x-axis is the time. So against time, if you plot it, this is how a time series graph would look. So as the name suggests, what is time series data? Time series data is basically a sequence of data that is recorded over a specific intervals of time and based on the past values. So if we want to do an analysis of time series past data, we try to forecast a future, and again, as the name suggests, it is time series data, which means that it is time dependent. So time is one of the components of this data. Time series data consists of primarily 4 components. One is the trend, then we have the seasonality, then cyclicity, and then last but not least, irregularity or the random component. Sometimes it is also referred to as the random component. So let's see what each of these components are. So what is trend? Trend is overall change or the pattern of the data, which means that the data may be, let me just pull up a pen and show you. So let's say you have a data set somewhat like this, a time series data set somewhat like this. All right. So what is the overall trend? There is an overall trend which is upward trend, as we call it here, right? So it is not like it is continuously increasing. There are times when it is dipping, then there are times when it is increasing, then it is decreasing, and so on. But overall, over a period of time, from the time we start recording to the time we end, there is a trend, right? There is an upward trend in this case. So the trend need not always be upwards. There could be a downward trend as well. So for example, here there is a downward trend, right? So this is basically what is a trend. Overall, whether the data is increasing or decreasing. All right, then we have the next component, which is seasonality. What is seasonality? Seasonality, as the name suggests once again, changes over a period of time and periodic changes, right? So there is a certain pattern. Let's take the sales of warm clothes, for example. So if we plot it along the months, so let's say January, February, March, April, May, June, July, and then let's say it goes up to December. Okay, so this is our December, a D. I will just mark it as D. And then you again have Jan, Feb, March, and then you get another December. Okay, and just for simplicity, let's mark these as Decembers as the end of the year, and then one more December. Okay, so what will happen when, if you're talking about warm clothes, what happens? The sales of warm clothes will increase probably around December when it is cold, and then they will come down. And then again around December again they will increase, and then the sales will come down. And then there will be again an increase, and then they will come down. And then again an increase, and then they will come down. Let's say this is the sales pattern. So you see here there is a trend as well. There is an upward trend, right? The sales are increasing over, let's say these are multiple years. This is for year 1, this is for year 2, this is for year 3, and so on. So for multiple years, overall the trend, there is an upward trend. The sales are increasing, but it is not a continuous increase, right? So there is a certain pattern. So what is happening? What is the pattern? Every December, the sales are increasing or they are peaking for that particular year, right? Then there is a new year. Again, when December approaches, the sales are increasing. Again, when December approaches, the sales are increasing, and so on and so forth. So this is known as seasonality. So there is a certain fluctuation which is periodic in nature. So this is known as seasonality. Then cyclicity. What is cyclicity? Now cyclicity is somewhat similar to seasonality, but here the duration between two cycles is much longer. So seasonality typically is referred to as an annual kind of a sequence. Like for example, we saw here. So it is pretty much like every year in the month of December, the sales are increasing. However, cyclicity, what happens is, first of all, the duration is pretty much not fixed, and the duration or the gap length of time between two cycles can be much longer. So recession is an example. So we had, let's say, recession in 2001 or 2002 perhaps, and then we had one in 2008, and then we had probably in 2012, and so on and so forth. So it is not like every year this happens probably. So there is usually when we say recession, there is a slump, and then it recovers, and then there is a slump, and then it recovers, and probably there is another bigger slump, and so on, right? So you see here, this is similar to seasonality, but first of all, this length is much more than a year, right? That is number one. And it is not fixed as well. It is not like every 4 years or every 6 years. That duration is not fixed. So the duration can vary. At the same time, the gap between two cycles is much longer compared to seasonality. Alright, so then what is irregularity? Irregularity is like the random component of the time series data. So there is like you have part which is the trend, which tells whether the overall it is increasing or decreasing. Then you have cyclicity and seasonality, which is like kind of a specific pattern, right? Then there is a cyclicity, which is again a pattern but at much longer intervals. Plus there is a random component, so which cannot be accounted for very easily, right? So there will be a random component which can be really random, as the name suggests, right? So that is the irregularity component. So these are the various components of time series data. Yes, there are conditions where we cannot use time series analysis, right? So can we do time series analysis with any kind of data? No, not really. So what are the situations where we cannot do time series analysis? So there will be some data which is collected over a period of time, but it's really not changing. So it will not make sense to perform any time series analysis over it, right? For example, like this one. So if we take X as the time and Y as the value of whatever the output we are talking about, and if the Y value is constant, there is really no analysis that you can do, leave alone time series analysis, right? So that is one. Another possibility is, yes, there is a change, but it is changing as per a very fixed function like a sine wave or a cos wave. Again, time series analysis will not make sense in this kind of a situation because there is a definite pattern here, there is a definite function that the data is following. So it will not make sense to do a time series analysis. Now, before performing any time series analysis, the data has to be stationary. And typically time series data is not stationary, so in which case you need to make the data stationary before we apply any models like ARIMA model or any of these, right? So what exactly is stationary data and what is meant by stationary data? Let us take a look. First of all, what is non-stationary data, time series data? If you recall from one of my earlier slides, we said that time series data has the following four components: the trend, seasonality, cyclicity, and random component or irregularity, right? So if these components are present in time series data, it is non-stationary, which means that typically these components will be present. Therefore, most of the time a time series data that is collected raw data is non-stationary data. So it has to be changed to stationary data before we apply any of these algorithms. Alright, so a non-stationary time series data would look like this, which means, like for example here there is an upward trend, the seasonality component is there, and also the random component and so on. So if the data is not stationary, then the time series forecasting will be affected. So you cannot really perform a time series forecasting on a non-stationary data. So how do we differentiate between a stationary and a non-stationary time series data? Typically or technically, one is, of course, you can do it visually. In non-stationary data, the data will be more flattish. Seasonality will of course be there, but the trend will not be there. So the data may, if we plot that, it may appear somewhat like this, right? It's a horizontal line. Along the horizontal line you will see, compared to the original data, which was, there was an upward trend, so it was changing somewhat like this, right? So this is non-stationary data, and this is how a stationary data would look visually. What does this mean? Technically, this means that the stationarity of the data depends on a few things: the mean, the variance, and the covariance. So these are the three components on which the stationarity of the data depends. So let's take a look at what each of these are. For stationary data, the mean should not be a function of time, which means that the mean should pretty much remain constant over a period of time, right? So there shouldn't be any change. So this is how the stationary data would look, and this is how a non-stationary data would look. I've shown in the previous slide as well. So here the mean is increasing, that means there is an upward trend. Okay, so that is one part of it. And then the variance of the series should not be also a function of time. So the variance also should be pretty much common, or should be constant rather. So this is if we visually take a look, this is how time series stationary data would look, where the variance is not changing. Here the variance is changing, therefore this is non-stationary, and we cannot apply time series forecasting on this kind of data. Similarly, the covariance, which is basically of the ith term and the I plus mth term, should not be a function of time as well. So covariance is nothing but not only the variance at the ith term, but the relation between the variance at the ith term and the I plus mth or the I plus nth term. So once again, visually this is how it would look if the covariance is also changing with respect to time. So these are all three components should be pretty much constant, and that is when you have stationary data, and in order to perform time series analysis, the data should be stationary. Okay, so let's take a look at the concept of moving average, or the method of moving average, and let's see how it works. We'll do simple calculations. So let's say this is our sample data. We have the data for 3 months, January, February, March. The sales in thousands rather, not hundreds, thousands of dollars is given here, and now we want to find the moving average. So how do we find the moving average? We call it as moving average 3. So moving average 3 is nothing but you take 3 of the values or the readings, add them up and divide by 3. Basically the way we take a mean or average of the 3 values. So that is as simple as that. So that's the average first of all. So what is moving average? Moving average is if you now have a series of data, you keep taking the 3 values, the next 3 values, and then you take the average of that, and then the next 3 values, and so on and so forth. So that is how you take the moving average. So let's take a little more detailed example of car sales. So this is how we have the car sales data for the entire year, let's say. So rather for 4 years. So year 1 we have for each quarter 1, 2, 3, 4, and then year 2, quarter 1, 2, 3, 4, and so on and so forth. So this is how we have sales data of a particular car, let's say, or a showroom. And we want to forecast for year 5. So we have the data for 4 years. We now want to forecast for the 5th year. Let's see how it works. First of all, if we plot the data as it is taken, the raw data, this is how it would look. And what do you think? Is it stationary? No, right? Because there is a trend, upward trend. So this is not a stationary data. So we need to, later we will see how to make it stationary. But to start with, just an example. We will not worry about it for now. We will just go ahead and manually do the forecasting using what is known as moving average method. Okay, so we are not applying any algorithm or anything like that. In the next video we will see how to apply an algorithm, how to make it stationary, and so on. Alright, so here we see that all the 3 or 4 components that we talked about are there. There is a trend, there is a seasonality, and then of course there is some random component as well. Cyclicity may not be, it is possible that cyclicity is not applicable in all the situations. For sales especially, there may not be, or unless you're taking a sales for maybe 20-30 years, cyclicity may not come into play. So we will just consider primarily the trend, seasonality, and irregularity, right? So random, it is also known as random irregularity, right? So we were kind of calling the random or irregularity component. So these are the 3 main components typically in this case we will talk about. So this is the trend component, and we will see how to do these calculations. So let's take a look, redraw the table including the time code. We will add another column which is the time code, and this is the column, and we'll just number it like 1, 2, 3, 4 up to 16. The rest of the data remains the same. Okay, so we will do the calculations now. Now let us do the moving average calculations, or MA4 as we call it, for each year. So we take all the 4 quarters and we take an average of that. So if we add up these 4 values and divide by 4, you get the moving average of 3.4. So we start by putting the value here. So that will be for the 3rd quarter, let's say 1, 2, 3, the 3rd quarter. Then we will go on to the next one. So we take the next 4 values as you see here and take the average of that, which is the moving average for the next quarter, and so on and so forth. Now if we just do the moving average, it is not centered. So what we do is we basically add one more column and we calculate the centered moving average as shown here. So here what we do is we take the average of 2 values and then just adding these values here. So for example, the first value for the 3rd quarter is actually the average of the 3rd and the 4th quarter. So we have 3.5. Now it gets centered. So similarly, the next value would be be 3.6 plus 3.9 divided by 2, so which is 3.7, and so on and so forth. Okay, so that is the centered moving average. This is done primarily to smoothen the data so that there are not too many rough edges. So that is what we do here. So if we visualize this data now, this is how it looks. Right, so if we take the centered moving average, as you can see, there is a gradual increase. If this was not the case, if we had not centered it, the changes would have been much sharper. So that is basically the smoothing that we are talking about. Now let's go and do the forecast for the 5th year. So in order to do the forecast, what we will do is we will take the centered moving average as our baseline and then start doing a few more calculations that are required in order to come up with the prediction. So what we are going to do is we are going to use this multiplicity or multiplicative model in this case, and this is how it looks. So we take the product of seasonality and the trend and the irregularity components, and we just multiply that. And in order to get that, this product of these two, we have basically the actual value divided by CMA. YT value divided by CMA will give you the predicted value, or YT is equal to the product of all three components. Therefore, ST into YT is equal to YT by CMA. So this is equal to YT, right? So therefore, if we want ST into YT, the product of seasonality and irregularity, it is equal to YT by CMA. So that is how we will work it out. I also have an Excel sheet of the actual data. So let me just pull that up. Alright, so this is how the data looks in Excel. As you can see here, year 1, quarter 1, 2, 3, 4, year 2, quarter 1, 2, 3, 4, and so on. And this is the sales data. And then this is the moving average. As I mentioned, this is how we calculate. And this is the centered moving average. So this is the primary component that we will start working with. And then we will calculate, since we want the product of ST into YT, that is equal to YT by CMA. So if you see, these values are nothing but the YT value divided by CMA. So in this case it is 4 by 3.5, which is 1.14. Similarly 4.5 by 3.7, 1.22, and so on and so forth. So we have the product ST into YT, and then the next step is to calculate the average of respective quarters. So that is what we are doing here, average of respective quarters. And then we need to calculate the deseasonalized values. So in order to get deseasonalized value, we need to divide YT by ST that was calculated. So for example, here it is 2.8 by 0.9. So we got the deseasonalized value here, and then we get the trend, and then we get the predicted values. So in order to get the predicted value, which is basically we predict the values for known values as well. Like for example, year 1, quarter 1, we know the value, but now that we have our model, we predict ourselves and see how close it is. So we predicted as 2.89, whereas the actual value is 2.8. Then we have 2.59, the actual value is 2.1, and so on, just to see how our model works, and then continue that into the 5th year, because for 5th year we don't have a reference value. Okay, and if we plot this, we will come to know how well our calculations are, how well our manual model. In this case, we did not really use a model, but we did on our own manually. So it will tell us the trend. So for example, the predicted value is this gray color here, and you can see that it is actually pretty much following the actual value, which is the blue color, right? And the gray color is the predicted value. So wherever we know the values up to year 4, we can see that our predicted values are following or pretty much very close to the actual values. And then from here onwards, when the year 5 starts, the blue color line is not there because we don't have the actual values, only the predicted value. So we can see that since it was following the trend pretty much for the last 4 years, we can safely assume that it has understood the pattern and it is predicting correctly for the next 1 year, the next 4 quarters, right? So that is what we are doing here. So these 4 quarters we did not have actual data, but we have the predicted values. So let's go back and see how this is working in this using the slides. So this is, we already saw this part, and I think it was easier to see in the Excel sheet. So we calculated the ST, IT, the product of ST and IT using the formula like here, Y by YT by CMA, we got that, and then we got ST, which is basically YT. So this is average of the first quarters for all the 4 years. And similarly, this is the average of the second quarter for all the 4 years, and so on. So these values are repeating. They are calculated only once. They get repeated, as you can see here. And then we get the deseasonalized data, and that is basically YT by ST. So we calculated ST here, and we have YT. So YT by ST will give you the deseasonalized data. And we have got rid of the seasonal and the irregular components so far. Now what we are left with is the trend. And before we start the time series forecasting or time series analysis, as I mentioned earlier, we need to completely get rid of the non-stationary components. So we are still left with the trend component. So now let us also remove the trend component. In order to do that, we have to find we have to calculate the intercept and slope of the data, because that is required to calculate the trend. And how are we going to do that? We will actually use what is known as a regression tool or analytics tool that is available in Excel. So you remember we have our data in Excel. So let me take you to the Excel, and here we need to calculate the intercept and the slope. In order to do that, we have to use the regression mechanism, and in order to use the regression mechanism, we have to use the analytics tool that comes with Excel. So how do you activate this tool? So this is how you would need to activate the tool. From Excel, you need to go to options, and in options there will be add-ins, and in add-ins you will have analysis tool pack, and you select this, and you just say go. It will open up a box like this. You say analysis tool pack, and you say okay. And now when you come back into the regular view of Excel, in the data tab, you will see data analysis activated. So you need to go to file, options, and add-ins, and then analysis tool pack. Typically, since I've already added it, it is coming at the top, but it would come under inactive application add-ins. So when you're doing it for the first time. So don't use VBA, you just say analysis tool pack. There are two options, one with VBA like this one and one without VBA. So just use the one without VBA. And then instead of just saying okay, just take care that you click on this go and not just okay. So you say go, then it will give you these options. Only then you select just the analysis tool pack, and then you say okay. Alright, so and then when you come back to the main view, you click on data. Okay, so this is your normal home view perhaps. So you need to come to data, and here is where you will see data analysis available to you. And then if you click on that, there are a bunch of possibilities. What kind of data analysis you want to do? There are options are given. Right now we just want to do regression because we want to find the slope and the intercept. So select regression and you say okay, and you will get these options for input Y range and input X range. Input Y range is the value YT, so you just select this and you can select up to here and press enter. And input X range, you can, for now you start with the baseline, or you can also start with the deseasoned values. So you can just click on these and say okay. I have already calculated it. So these are the intercept and the coefficients that we are getting for these values, and we will actually use that to calculate our trend here, right? So which is in the J column. So our trend is equal to intercept plus slope into the time code. So the intercept is out here, as we can see in our slide as well. So if you see here, this is our intercept, and the lower value is the slope. So we have calculated here and it's shown in the slides as well. So intercept, so the formula is shown here. So our trend is equal to intercept plus slope into time code. Time code is nothing but this one, T, column A, 1, 2, 3, 4. Okay. So that's how you calculate the trend, and that's how you use the data analysis tool from Excel. Using these two, we calculate the predicted values, and using this formula, which is basically trend is equal to intercept plus slope into time code. And then we can go and plot it, see how it is looking, and therefore, so we see here that the predicted values are pretty close to the actual values, and therefore we can safely assume that our calculations, which are like our manual model, is working, and hence we go ahead and predict for the 5th year. So till 4 years we know the actual value as well, so we can compare how our model is performing. And for the 5th year we don't have reference values, so we can use our equations to calculate the values or predict the values for the 5th year, and we can go ahead and safely calculate those values. And when we plot for the 5th year as well, the predicted values, we see that they are pretty much, they captured the pattern, and we can safely assume that the predictions are fairly accurate, as we can also see from the graph in the Excel sheet that we have already seen. Okay, so let's go and plot it. So this is how the plot looks. This is the CMA, or the centered moving average, the green color, and then the blue color is the actual data, red color is the predicted value, predicted by our handcrafted model. Okay, so remember, we did not use any regular forecasting model or any tool. We have done this manually, and the actual tool will be used in the next video. This is just to give you an idea about how behind the scenes or under the hood, how forecasting works, or time series analysis, how it is performed. Okay, so it looks like it has captured the trend properly. So up to here is the known reference, we have reference, and from here onwards is purely predicted. And as I mentioned earlier, we can safely assume that the values are accurate and predicted properly for the 5th year. Let's go ahead and implement a time series forecast in R. So in this section, what are we going to do? We are going to use ARIMA model. There are different models and algorithms for performing time series forecasts. So we will use ARIMA, which is the most common one. And we will also talk about what is autocorrelation and partial autocorrelation. And we will see that in RStudio as well. And then we will take you through a use case where we will forecast the air ticket sales for the future. And then we will end with the model validation using the junk box text. Okay, so with that, let's get started. First of all, as I mentioned, we will be using the ARIMA model to do the forecast of this time series data. So let us try to understand what is ARIMA model. So ARIMA is actually an acronym. It stands for Autoregressive Integrated Moving Average. So that is what is ARIMA model. And it is specified by 3 parameters, which is P, D, and Q. P stands for autoregressive. So let me just mark this. So there are 3 components here: autoregressive, integrated, moving average. Okay. So these 3 parameters correspond to those 3 components. So the P stands for autoregressive, D for integrated, and Q for moving average. So let us see what exactly this is. So these 3 factors are: P is the number of autoregressive terms, or AR. We will see that in a little bit. And D is how many levels of differences that we need to do, or differentiation we need to do. And Q is the number of lagged forecast errors. So we'll see what exactly each of these are. So AR is the number of autoregressive terms, and which is basically denoted by the P. And then we have D, which is for the number of times it has to be differentiated. And then we have Q, which is for the moving average. So what exactly AR terms. So in terms of the regression model, autoregressive components refer to the prior values of the current value. Well, what we mean by that is, here when we talk about time series data, focus on the fact that there is regression. So what exactly happens in regression? We try to do something like, if it is simple linear regression, we do some equation like y is equal to mx plus c, where there are two variables. One is the dependent variable and then there is an independent variable. Let me just complete this equation as well, mx plus c. Right? So this is a normal regression curve or a simple regression curve. Now here we are talking about autoregression or autoregressive. So autoregressive, as the name suggests, is regression of itself. So which means that here you have only one variable, which is your maybe the cost of the flights or whatever it is, right? And the other variable is basically time dependent, and therefore the value at any given time, and that we will denote as yt, for example. So there is no x here, there is only one variable, and which is y, and we say yt, which is basically the predicted value at a time interval t, for example, is dependent on the previous value. So for example, there may be a1 and then yt minus 1, and then there will be like plus a2 and right plus a2 and yt minus 2 and all right, and then plus a3 into yt minus 3. Alright, so basically here what we are saying is there's only one variable here, but there is a regression component. So we are doing a regression on itself. So that's how the term autoregression comes into play. So only thing is that it is dependent on the previous time values. So there is a lag, let's say this is the first lag, second lag, third lag, and so on. So the current value, which is yt, is dependent on the previous time lag values. So that is what is autoregression component. So this is what is shown here. For example, in this case, instead of y, we are calling it as x. So that's the same, and this is represented by some equation of that sort depending on how many lags we take. So that is the AR component, and the term P is basically determines how many lags we are considering. So that's the term P for. Now what is D? D is the degree of differencing. So here differencing is like for the non-seasonal differences, right? So for example, if you take the values like this, which are given for 5, 4, 6, and so on and so forth, if you take the differencing of one after another, like for example 5 minus 4 or 4 minus 5, the next value with the previous value, so 4 minus 5. So this is known as the first order differencing. So the result is minus 1. Similarly, 6 minus 4 is 2. 7 minus 6 is 1. So this is first order differencing, and here we call it as D is equal to 1. Okay, and same way we can have second order, third order, and so on. Then the last one is Q. Q is the actually we call it moving average, but in reality it is actually the error of the model. So we also sometimes represent as ET. Alright, so now ARIMA model works on the assumption that the data is stationary, which means that the trend and seasonality of the data has been removed. That is correct. Okay, so this we have discussed in the first part, what exactly is stationary data and how do we remove the non-stationary part of it. Now, in order to test whether the data is stationary or not, there are two important components that are considered. One is the autocorrelation function and the other is the partial autocorrelation function. So this is referred to as ACF and PACF. Right. So what is autocorrelation and what is the definition? Autocorrelation is basically the similarity between values of a same variable across observations, as the name suggests. Now, how do we actually find the autocorrelation function, the value, right? So this is basically done by plotting, and autocorrelation function also tells you how correlated points are with each other based on how many time steps they are separated by and so on. That is basically the time lag that we were talking about, and it is also used to determine how past and future data points are related. And the value of the autocorrelation function can vary from -1 to 1. So if we plot, this is how it would look. Autocorrelation function would look somewhat like this, and there is actually a readily available function function in R, so you will see that, and you can use that to plot your autocorrelation function. Okay, so that is ACF, and we will see that in our RStudio in a little bit. And similarly, you have partial autocorrelation function. So partial autocorrelation function is the degree of association between two variables while adjusting the effect of one or more additional variables. So this again can be measured, and it can also be plotted, and its value once again can go from -1 to 1, and it gives the partial correlation of time series with its own lagged values. So lag again we have discussed in the previous couple of slides. This is how a PSEF plot would look in RStudio. We will see that as well, and once we get into the RStudio. And with that, let's get into RStudio and take a look at our use case. Before we go into the code, let's just quickly understand what exactly is the objective of this use case. So we are going to predict some values or forecast some values, and we have the data of the airline ticket sales of the previous years, and now we will try to find or predict or forecast the values for the future years. All right, so we will basically identify the time series components like trend, seasonality, and random behavior. We will actually visualize this in RStudio, and then we will actually forecast the values based on the past values or history data, historical data. So these are the steps that we follow. We will see in RStudio in a little bit. Just quickly, let's go through what are the steps. We load the data, and it is a time series data. If we try to find out what class it belongs to, the data is actually air passengers data that is already comes preloaded with RStudio. So we will be using that, and we can take a look at the data, and then what is the starting point, what is the end point. So these are all functions that are readily available we'll be using, and then what is the frequency. So it's basically the frequency is 12, which is like yearly data, right? So every month the data has been collected. So for each year it is 12. And then we can check for any missing values if there are any. And then we can take a look at summary of the data. This is what we do in exploratory data analysis. And then we can plot the data, visualize the data, how it is looking, and we will see how the data has some trend, seasonality, and so on and so forth. All right, then we can take a look at the cycle of the data using the cycle function, and we can see that it is every month. That's the cycle. End of every 12 months, a new cycle begins. So each month of the year is the data is available. Then we can do box plots to see for each month how the data is varying over the various 10 or 12 years that we will be looking at this data. And from exploratory data analysis, we can identify that there is a trend, there is a seasonality component, and how the seasonality component varies also we can see from the box plots. And we can decompose the data. We can use the decompose function rather to see the various components like the seasonality, trend, and the irregularity part. Okay, so we will see all of this in RStudio. This is how they will look. This is the once you decompose, and this is how you will actually you can visualize the data. This is the actual data, and this is the trend. As you can see, it's going upwards. This is the seasonal component, and this is your random or irregularity, right? So we call it irregularity, or we can also call it random, as you can see here. Yes, so the data must have a constant variance and mean, which means that it is stationary before we start any analysis, time series analysis. And so basically, yeah, if it is stationary, only then it is easy to model the data, perform time series analysis. So we can then go ahead and fit the model. As we discussed earlier, we'll be using ARIMA model. There are some techniques to find out what should be the parameters. So we will see that when we go into RStudio. So the auto ARIMA function basically tells us what should be the parameters, right? So these parameters are the P, D, and Q that we talked about. That's what is being shown here. So if we use auto ARIMA, it will basically take all possible values of this P, D, Q, these parameters, and it will find out what is the best value, and then it will recommend. So that is the advantage of using auto ARIMA. All right. So like in this case, it will tell us if we use this parameter trace, we set the parameter trace is equal to true, then it will basically tell us what is the value of this AIC, which has to be minimum. So the lower the value, the better. So for each of these combinations of P, D, and Q, it will give us the values here, and then it will recommend to us which is the best model. Okay, because whichever has the lowest value of this AIC, it will recommend that as our best PDQ values. So once we have that, we can see that we can potentially get a model or the equation. Model is nothing but the equation, and based on the parameters that we get. And we can do some diagnostics, we can do some plotting to see whether there is a plot for the residuals, so which shows the stationarity. And then we can also take a look at the ACF and PACF. We can plot the ACF and PACF, and then we can do some forecasting for the future years. So in this case we have up to 1960, and then we can see how we can forecast for the next 10 years, which is 1970, up to 1970. And once we have done this, can we validate this model? Yes, definitely we can validate this model. And to validate the findings, we use junk box test, and this is how you just call box.test, and then you pass these parameters, and you will get the values that will be returned, which will tell us whether how accurate this model is, how accurate the predictions are. So the values of P are quite insignificant in this case. We will see that, and that also indicates that our model is free of autocorrelation, and that will basically be it. So let's go back and into our RStudio and go through these steps in real time. So we have to import this library. Forecast package is not installed. You have to go here and install the forecast package. Okay, so that's the easy way to install rather than, so click on this install. I will not do it now because I've already installed. So the first time, that's only one time. Then after that you just have to load it into memory and then keep going. So we will load this data called air passengers, so by calling this data method. And if you see the data air passengers is loaded here, and if we check for the class, it is a time series data, TS data. So we can check for the dates. We can also view the data in a little bit, and start date is 1949 and January, and our end date is 1960 December, and the frequency is 12, which is like collected monthly. So that is the frequency, which is 12 here. And then we check if there are any missing values. There are no missing values. And then we take a look at the summary of the data. This is all exploratory data analysis. And then if you just display the data, this is how it looks. And then we need to decompose this data. So we will kind of store this in an object TS data, and then use that to decompose and store the new values. So let me just clear this for now. And if we decompose, basically as we have seen in the slides, decomposing is breaking it into the trend, seasonality, and irregular or random components. Then you can go ahead and plot it. So when you plot it, you can see here, let me zoom this. This is our original plot, or observed value as it is known as. Then we have decomposed the three parts, which is basically the trend. As you can see, there is an upward trend. Then the seasonal component. So this is some regularly occurring pattern. And then there is a random value, which is basically you cannot really give any equation or function or anything like that. So that's what this plotting has done. And then you can actually plot them individually as well. So these are the individual plots for the trend, for the seasonal component, and the random component. All right. So now let's take a look at the original data and see how the trend is in a way. So if we do this linear regression line, it will show that it is going upwards. And we can also take a look at the cycles that are there, which is nothing but we have a frequency of 12, right? So the cycles will display that it is January, February to December, and then back to January, February, and so on and so forth. And if we do box plots for the monthly data, you will see that for each of the months, right? And over the 10 years that the data that we have, we will see that there is a certain pattern, right? This is also in a way to find the seasonality component. So while January, February sales are relatively low, around July, August, the sales pick up. So especially in July, I think the sales are the highest. And this seems to be happening pretty much every year, right? So this is every year here in July there seems to be a peak in the sales, and then it goes down and slightly higher in December and so on. So that is again part of our exploratory data analysis. And once again, let's just plot the data. Now, as I said, in order to fit into an ARIMA model, we need the values of P, D and Q. Now, one way of doing it is, there are multiple ways actually of doing it. The earlier method of doing it was you draw the autocorrelation function plot and then partial autocorrelation function plot and then observe that and where does this change, and then identify what should be the values of P and Q and so on. Now, R really has a very beautiful method which we can use to avoid all that manual process that we used to do earlier. So what R will do is, there is a method called auto ARIMA, and if we just call this auto ARIMA method, and it will basically go and test the ARIMA model for all possible values of these parameters P, D, Q, and then it will suggest to you what should be the best model, and it will return that best model with the right values of P, D and Q. So we as data scientists don't have to do any manual, trial and error kind of stuff. Okay, so we got the model now, and this is the model. It has PDQ values are 211 PDQ, and this is the seasonal part of it, so we can ignore it for now. And so if we want to actually understand how this has returned these values 211 as the best one, there is another functionality or feature where we can use this trace function or trace parameter. So if you pass to auto ARIMA the trace parameter, what it will do is it will show you how it is doing this calculation. What is the value of the AIC? Basically, AIC is what defines the accuracy of the model. The lower, the better. Okay. So for each combination of PDQ, it will show us the value of AIC. So let's run it instead of me talking so much. Let's run this. If we run auto ARIMA with trace, you see here there is a red mark here. That means it is performing. It's executing this, and here we see the display, right? So it starts with certain values of PDQ, and then it finds that value is too high, so it starts with some 0, 1, 1, 0 and so on and so forth, and ultimately it tells us, okay, this is our best model. You see here, so it says this is our best model 211. Let's go back and see, did we get the same one? Yes, we got the same one when we ran without trace as well, right? Now, why is 211? Let us see, where is 211? Here is our 211, and if you compare the values, you see that 1017 is pretty much the lowest value, and therefore it is saying this is our best model. All other values are higher. So that's how you kind of get your model. And now that you have your model, what you have to do, you need to predict the values, right? So before that, let us just do some test of these values. So for that, you install T-series. Again, if you are doing it for the first time, you would rather use this package and install and say T-series and install it. And then you just use this library function to load it into your memory. Alright, so now that we got our model using auto ARIMA, let us go ahead and forecast and also test the model and also plot the ACF and PACF. Remember, we talked about this, but we did not really use it. We don't have to use that, but at least we will visualize it. And for some of the stuff, we may need this T-series library. So if you are doing this for the first time, you may have to install it. And my recommendation is, don't use it in the code. You go here and install T-series. And I will not do it now because I have already installed it, but this is a preferred method. And once you install it, you just load it using this libraries function, and then you can plot your residuals, and this is how the residuals look, and you can plot your ACF and PACF. Okay, so this is how your PACF looks, and this is how your ACF looks. For now, there is really nothing else we need to do with ACF and PACF. This is just to visualize how it looks. But as I mentioned earlier, we were actually using these visualizations or these graphs to identify the values of P, D, and Q. And how that was done, it's out of scope of this video, so we will leave it at that. And then we will forecast for the next 10 years. How do we forecast that? So we call forecast, and we pass the model, and we pass what is the level of accuracy that you need, which is 95%, and for how many periods, right? So basically we want for 10 years, which is like 10 into 12 time periods. So that's what we are doing here. And now we can plot the forecast value. So you see this is the original value up to I think 62 or whatever, and then it goes up to 72. This blue color is the predicted value. Let's go and zoom it up so that we can see it better. So from here onwards we are forecasting, and you can see that it looks like our model has kind of learned the pattern, and this pattern looks very similar to what we see in the actual data. Now, how do we test our model? So we can do what is known as a box test, and we pass our model here, residuals basically, with different lags, and from those values here, the p-values here, we find that they are reasonably low, the p-values, which means our model is fairly accurate.
With that note, we have reached to the end of this session. Thanks to our training experts. Hope you found this tutorial helpful. If you have any queries regarding this tutorial, or if you feel you have a suggestion for us, then please feel free to drop it down in the comment section below, and our experts team will be happy to reach you out. This is Ravi signing off. Until next time, thank you.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.